Welcome back to AlgoJS. Today we are solving every single question in the LeetCode blind 75 list. I recently prepped for interviews with this list along with the contents from algojs.dev, and this allowed me to secure multiple job offers, which I then used to negotiate a senior position at my current company. So if you're a junior or mid-level engineer who wants to further their career as a software engineer, you're definitely in the right place. With that being said, I hope you enjoy the video. Let's get into it. So we're given an array nums, find a contiguous non-empty subarray with the array that has the largest product and return that product. A subarray is a contiguous sequence of the array. So contiguous sequence follows one after the other. So in example 1, the maximum product we can achieve from this is 6, so it's 2 times 3. And then in example 2, the maximum product is 0 because any other solutions are either negative or 0. So as soon as this question is asking for a maximum, we can start by looking at dynamic programming. And what makes this problem slightly more difficult is the array contains negative values. So what are the ways that we can generate a maximum from any of these values? Well, we can have the current value by itself. We can have a positive times a positive, or we can have a negative times a negative. One of these will generate the maximum. With dynamic programming, we're going to have to keep track of the maximum, and we're going to have to keep track of the minimum. So if we have a variable called prevmax and prevmin, and we initialize both of them to the value at index of 0, so 2 and 2, and then we have a res which is equal to 2 to begin with, because this is a valid option, then we can loop through this array and build out from this information here. So if we start at index 1, what is the current max? Well, the current max can either be 3, so it can be the current value, it can be the current value times the previous max, so both positives, so 3 times 2, which is equal to 6, or it could be negative times a negative, right? So we don't have any negatives here, so we can say that the maximum from this is going to be 6, which is 3 times 2. Then we need to have the current minimum. So what is the current minimum at this position? Well, it can be the current value, which is 3, or it can be the current value times the previous max, or the current value times the previous minimum, right? So the previous max and previous min at this point in time are the same, so the value we're going to add to current min is going to be 3. Now if we update the previous max and the previous min with these values, 6 and 3, we can now update the results. Okay, so we've updated the results to the maximum between the previous result, which was 2, and this max here. Then we rinse and repeat. So if we go to -2, what's the maximum we can get from this? Well, it's -2, the current value, or -2 times 3. So the maximum between those two is -2. The minimum is going to be the minus value times the largest positive value. So that's going to be -6. Then we update these values, -2, -6. Obviously, -2 is not greater than 6. So we move along. So at 4, what is the current max we can get? Well, it'll be the current value, so the value of 4, or it'll be 4 times the previous max, which is -2, so that'd be -8, or it'll be 4 times the previous min, which is -6. So the maximum from this is going to be 4. Likewise, for the current min, it's either the current value, or the current value times the previous max, or the current value times the previous minimum. So the current min will be 4 times -6, which is equal to -24. So if we update prevmax and prevmin, then we can update results. So we compare results to the current max. Result is still greater than current max, so we carry on. Now we're outside the loop, we can just return this as our result. And as you can see, by using dynamic programming, we've simplified the solution from, say, the time complexity of O(n) squared, if we had to loop through each and every possible solution, to O of n, because we're only iterating over this array exactly once. So let's start off by creating our prevmin, prevmax, and our result variable. Then if we loop through from index of 1 up to the end of nums.length, we work out the current max and the current min. So current max is equal to the maximum between nums at I, so the current value times the previous max, or the current value times the previous min. Likewise for current min, it's just going to be the same, but looking for the minimum. So nums at I, the current value times previous max, sorry, or the current value times previous min. Once we've generated those, we can update prevmax to equal current max and prevmin to equal current min. As soon as we still have access to the current max, we can update result. So that'll be the maximum between our current result and current max. Then return result. Let's run it. Given an integer array nums, return an array answer such that answer I is equal to the product of all the elements of nums except nums at I. The product of any prefix or suffix of nums is guaranteed to fit in a 32-bit integer. You must write an algorithm that runs in on time and without using the division operation. So the product of array except self, here we have 1, so 24 is equal to the product of the nums except nums at I, so it would be 2 times 3 times 4. 12 is equal to 1 times 3 times 4. 8 is equal to 1 times 2 times 4. And 6 is equal to 1 times 2 times 3. So let's try and figure out how we're going to work this out. So we need to do it in O n time complexity. That means no nested for loops, and we aren't allowed to include division. So in order to do this without division and keep it at on time complexity, we could loop through this array once forwards and then once backwards and calculate the product at each index, and then use those two arrays to computate the answer. We could have something called like a forward array, and this will be equal to, we'll start off with 1, we'll place 1 as a placeholder, then the product of 1 here is 1, the product of 1 and 2 is 2, the product of 1, 2, and 3 is 6. And then we have 4 values in there, so we don't need to carry on. Now if we did it in reverse order, we have rev array. We add 1 as a placeholder at the end. We start at 4, so the product of 4 itself is just 4. The product of 4 and 3 is equal to 12. The product of 4, 3, and 2 is equal to 24. Now can we use this and this to work out this? Well, if you look at each value, 1 and 24, 24 down here, we could times those together, right? If we look at the next value, 1 and 12, we could times those together to get 12. If we look at the next values, we've got 2 and 4. If we times those together, we'll get 8. And if we've got 6 and 1, we can times those together to give 6. In terms of time complexity, here we have O to n, because we're looping through the nums array twice. But this here, this 2 becomes irrelevant. So it's simplified to on. Base complexity, however, is n plus m, because we have two arrays here that are going to be stored, and then we need to turn them into an output array. So it's going to be on plus m, where n is the number of integers in the for array and m is the number of integers in the rev array. And if we look at the question, one of the follow-ups is, can you solve the problem in O1 extra space complexity? So in order to do that, we need to remove these two arrays, and the output array does not count towards space complexity. So what we could just simply say is, we could say result is equal to this array, and then we could just update this as we go through the process. So we need a forward array, we need a starting position as a kind of placeholder, and we need to loop through nums. So to begin with in here, what we can do is we can push. So to begin with in here, we can push into the forward array start, and then we need to update start to work out the product. So it'll be start times nums at I. And then the next loop is going to go at index 1, and then it's going to be 1 times 1, 1, and I'll put that into the forward array. And then I'll move on to the next index, which is 2 times 1, which is 2, and it'll push that into the forward array. And then we'll only go up to 3, so we won't include 4 in this loop. So next is we could have a reverse array, or we could just call it res here. We need to have a start placeholder, so we'll say that's equal to 1, and we need to loop through the array backwards. So I is equal to nums.length minus 1, I is greater than or equal to 0, I minus minus. Now we need to add to the end, so we need to unshift into res. We need to pass in start2, which is 1 at this moment in time, times forward array at position I. That's going to grab the integer for position at the index I, and it's going to times that, so we can get the product. So we need to add to res at the end of its array. So we unshift into res, and we're going to have start2 times forward r at I. So that's going to grab 1 from here, it's going to grab I from here, and it's going to use the last value in forward array and it's going to times them together to give us the result. And then we need to update start2, because as we did before, we're updating the product. Okay, and we can return res. So let's just see if that's worked. Let's submit it. Okay, great. The only issue is that we haven't utilized O1 space complexity because we have forward array here. So the way around this is to just say let res equal an empty array and initialize that at the start instead of forward array. We can remove this res. Then in our for loop, we can push start into res instead of the forward array. And then down here, rather than res unshift, we can just say res at I is equal to start2 times res at I. And if we get rid of that, run the code. Given an integer array nums, find the contiguous subarray containing at least one number which has the largest sum and return its sum. A subarray is a contiguous part of an array. Okay, so in the example here we have a nums array, which is just an array full of integers, and our output is 6 because we have a subarray here which equals 6. So that's the maximum subarray within this nums array. And contiguous here, that just means that these numbers follow one after the other. So let's work out a way to solve this. So because it's asking for an optimal number, the maximum, this should lead us to think of a DP solution. So DP uses the smallest possible solution to carry out a larger solution, to carry out a larger solution until you have completed the nums array and you have found your answer. So let's work through a DP solution. So in order to work out the total maximum, we need to work out the current maximum. So we need to work out the maximum from this point. So let's call this DP array we have here, let's call this current max. Okay. Now what is the maximum value at nums at 0 index? Well, it's -2, right? So the maximum at this point is also -2. If we move on to the next position, the current max here can either be 1 or it can be 1 plus -2 because we're using this value to help computate this value. So in this case it's going to be 1, right? Because that's going to be greater, and we're working out the max here, than -2 plus 1. So here the maximum will be updated to 1. Then we move along, we have -3 here. So we can use -3 as the maximum, or we can use 1 plus -3 as the maximum. So we'll use 1 plus -3, which is -2. And as you can see, a trend is growing here. We look at the maximum here. The maximum between 1 and -2 is 1, so we leave that the same. But there is a trend, and that is the recurrence relation of this DP program. So current max is going to be equal to the maximum between nums at I, or current max plus nums at I. So current max. And this will then be used to computate the rest of the current maxes. And as you can see, we're going to be updating the max as we go along, and then we'll be able to return the maximum. So let's just fill in the rest. So at this point, we have a maximum between 4 and 4 plus -2. So it's going to be 4. So we can update the max here. That'd be 4. Moving along, we've got -1. So the maximum between -1 and -1 plus 4 is 3. Here we don't need to update the maximum, so we move along. At this point, we have a maximum between 2 and 2 plus 3. So that is going to become 5. We update the max here. 5. At this point, we have a maximum between 1 and 1 plus 5, so that's going to be 6. Maximum is updated again to 6. At this point, we have -5 or -5 plus 6, so that's going to be 1. And at this point, we have a maximum between 4 or 4 plus 1, so that's going to be 5. So the maximum didn't update on the last two, and then we can just return this value, which is what we're looking for. So in terms of time complexity, this is going to be O of n because we're looping through the nums array once. So n is the integers within the nums array, and we're going to be doing this in place. So space complexity is going to be O of 1. Okay, so let's start off this dynamic programming solution. So we said that we'd have a current max variable, right? And that's going to be initially set at nums at 0, and then we're going to have a maxima variable, which is going to also be set at nums at 0. So we're going to loop through nums starting from 1. And the reason for this is because we already set this value here. So this is the initial value which we have set, so we don't need to loop through that, okay? I is less than nums.length, I++. Then we just need to update current max and maximum. And current max is going to be the recursive relation within this dynamic programming solution. So it's going to be the maximum between nums at I and current max plus nums at I. And then we just need to update the maxima, which is going to be equal to the maximum between maxima and current max. And then we can just return maxima and give this a go. So it's been accepted, let's submit it. So you're given an array of prices where price I is the price of a given stock on ith day. You want to maximize your profit by choosing a single day to buy one stock and choosing a different day in the future to sell that stock. Return the maximum profit you can achieve from this transaction. If you cannot achieve any profit, return 0. What we need to do is we need to return max profit. When anything concerns max profit or an optimal, what we usually go for is dynamic programming. So in this example, what we need to do is we need to find the smallest value. So in this case, it's 1, and then just determine where the next largest value is. In this case, we can easily see that it's 6, and then we just return that profit, which is 5. The difficulty comes in when trying to program that out. So the best way to look at it is if you draw it out. Okay, so here's the graph, and what I've done is I've plotted each point. So we have 7, 1, 5, 3, 6, and 4. And the points that we really need to take into consideration is this point and this point. So we need to assign a variable to this point. Let's just call it current min. And then with this, let's just call it current max. Right, so with this problem, what we can do is we can kind of set current min to this value here. So to the first price in the array. So that will equal 7. And then current max we can set to 0, because what we're going to end up doing is we're going to end up returning this. And remember, as it said in the question, if you cannot achieve any profit, you need to return 0. So starting off at 0 is great because it covers that. And then what we'll do is we'll loop through the prices, right? So we'll loop through the prices and we'll update the current min and the current max. So at this point, the current min is 7. Current max at initial position is going to stay 0, right? So then we move on to the next one. Current min is currently 7. What we'll do is we'll change that to 1 because 1 is definitely smaller than 7. And with current max, what we can do, leave that at 0 because we haven't got anything to compare it to yet because this is the new current min. So we move along to 5. Now current minimum is still 1. So this is where the interesting part is. In order to get the current max here, is we take this point, take the price at this point, and we minus the current min. So it's going to be 5 minus 1. And then we do this consecutively throughout. So 3 is going to give us 2. So what we need to do is we need to work out the maximum. Current max is going to be equal to math.max current max and the current value we're on minus the minimum. So it would be prices at I minus min, or current min, sorry. And that would be the comparison there. So this is the dynamic approach here. So we're always using previous values in order to computate the current max. So then we'll move along. We'll go to 6 and we'll subtract 1 from that. And that becomes the new max because the current max is 4. 6 minus 1 is 5. 5 is greater than 4. So 5 goes there. Move along. 4 minus 1 is 3, so that doesn't matter. And then we just return this value, and that is the answer we're looking for. So let's jump into the code and see how it's implemented. Okay, so we need to set the variables for the current min and current max. So current min is equal to prices at 0. So the first value of prices, so we can start the comparison, and then current max is set to 0. And the reason for this is because the question asks us that if we don't find a maximum profit, return 0. And at the end, we're going to be returning current max. So that covers us there with the for loop. We go to the last value, and then within the for loop, we are just going to be updating current min and current max. So current min is the minimum between prices at I and current min, and then current max is going to be the maximum between current max and prices at I minus current minimum. Now in terms of time and space complexity, we've only got one loop or one pass over this entire array. So that's going to be O of n, and space complexity is going to be O1 constant space because we aren't allocating any extra space, and that should hopefully run. Okay, so that's passed, let's submit it. So given an integer array nums, return true if any value appears at least twice in the array, and return false if every element is distinct. Very simple, straightforward question. What we need to do is we need to just decide whether there is a duplicate in the array. And so one way of solving this is to use a set data structure. And what the set data structure does is when you initialize it with, say, this nums array, it's only going to pass in unique values. So it's going to look something like this: 1, 2, and 3. And then we can just compare a property of set, which is size. So set.size, we can compare where it doesn't equal nums.length. So if set.size is different to nums.length 3, 4, then we can return this. So this is going to return true here. With respect to time and space complexity, time is going to be O of n, where n is the values of nums, and then space is also going to be O of n because we need to store the values within this set. And in worst case, this could be 4, and then we'd have to store it in the set as well. So let's initialize the set and pass in the nums, and then return set.size. So grab the property for set does not equal nums.length, and then try this out. True, it's been accepted. Let's submit it. Given an array of integers nums and an integer target, return indices of 2 numbers such that they add up to the target. So indices 0, 1, 2, 3. You may assume that each input would have exactly one solution, and you may not use the same element twice. Okay, so we got to go through this num array, and we got to decide on 2 values that add up to give target, and we need to do it in the most optimized way possible. So if we just think about it, you could go for 2 for loops and compare each value and add them together, but a very efficient way of doing it would be to use some kind of data structure that would have O1 constant lookup, and that would be using the map data structure. So what we need to do is we need to look through this array. We need to find 2 values. In this case, it's going to be 2 and 7. That make 9. And we need to return the indices in array format. Okay, so how we'd do that is we'd use a map data structure. And what we'd map together are the nums and their indices, because we want to be able to look up the indices with constant time, right? So it'll look something like this. And then what we can do is we can just loop through the nums, and we can look for what's called the complement. So when we're looping through, if we say is 9 minus 2 in map, right? Check in the map. Is 9 minus 2 in the map? Goes through, there's 2, there's 7. Yes, 7 is in the map. And then what we can do is we can return this index here. So return 0 and the index found in here, which is 1. And that will give us the answer that we're looking for. In terms of time and space complexity, time for this will be O of n, because we have one for loop and the map data structure is constant lookup. So it will be O of n. And then in terms of space, well, we have this map data structure to make time complexity more efficient, but this actually allocates space. So we have to allocate each value in the nums array into the map. So in that case, the space complexity will be O of n as well. So let's jump into the code and see how this is implemented. Okay, great. We're here in the code editor. So the first thing we said was to create some kind of map that we can store the values in. So if we initialize a new map, then we can start looping through the elements. Okay, so I equals 0, I is less than nums.length. So we want to go up to the last value in this loop. And now we can check, right? So we can say if the map has the complement, and by complement we can define that here as nums at I target minus nums at I. If the map has complement, then what we can do is we can return, like we said, we need to return the indices. So we can return I and map.get and get the complement. Else, in this case, what we're going to do is we're going to have to set the values in the map. So map.set nums at I and I. And that should work. Okay, it's been accepted. Let's submit it. So we have an array that has been rotated a number of times. So here we have 4, 5, 6, 7, 0, 1, 2. It's been rotated 4 times, so the minimum is now here. This has been rotated 7 times, so the minimum is back at the start. So there is some information here about it being rotated. But what we need to do is, given the sorted array nums of unique elements, return the minimum element of this array. You must write an algorithm that runs in O log n time. So firstly, this information about it being rotated is pretty much irrelevant. All we really need to know is the nums array and that we need to return with log n time complexity. We know that it's a sorted array. That means binary search. So here are the examples. Now with binary search, what we need is we need a left pointer, we need a right pointer, and then we'll have some kind of while loop, which allows these to loop through each point within the nums array. Once we've created that, once we've created the left and right pointer, we need to grab the middle value in this nums array. And then in order to find the minimum, which as we can see is this, we need to compare the middle value with the right value because it contains the minimum here. So let's just say nums at right. If nums at right is less than nums at mid, which in this case it is, we want to remove a portion of the nums array so that it only contains the minimum and a shorter amount of numbers. In this case, nums at R is less than nums at mid, so allocate left to middle plus 1. And then we can discard this section. Left equals mid plus 1. Now we're currently on the minimum and we have only 2 points here. So we can say while left is less than right, and at the end of this we can return nums at left. But we still need to have an else statement just in case nums at right is greater than nums at mid. So if we look at the next example, we've got left, right, mid. The minimum value is here. So is num at right less than nums at mid? Yes, it is. So we reallocate left to mid plus 1 and we discard the rest. Now we've got 3 points left. So we need to check again, is nums at right less than nums at mid, which is going to be this value. No, it's not. So we want to contain this area here as our new search area. And in order to do that, we have to reallocate right to mid. So this goes to here. This area is discarded, and then we can return nums at left. So the else portion here, right, is equal to mid. And let's just check with the last example whether our solution works. Mid is math.floor, so it'll be that point. We know the minimum is this point, so we check is right. Nums at right is this point less than this point? No, it's not. So we need to reallocate right to mid. So right goes here. This portion is discarded. And then we've got left and right, and we just return nums at left. So first we need to define left and right pointers. So left equals 0. Right equals nums.length minus 1, while left is less than right. If we grab the middle value, mid equals math.floor, right plus left, divide by 2. Now we say if nums at right is less than nums at mid, left equals mid plus 1, else right equals mid. And then we just return nums at left. Let's check to see if that's worked. Code's been accepted. Let's submit it. So there is an integer array nums sorted in ascending order with distinct values, so there will be no duplicates. Prior to being passed to your function, nums is possibly rotated at an unknown pivot index, such that the resulting array is nums k plus 1, all the way up to nums n minus 1, and nums 0, nums 1, all the way up to nums k minus 1, 0 indexed. So given the array nums after the possible rotation and integer target, return the index of target if it is in nums, or -1 if it is not in nums. You must write an algorithm with O log n runtime complexity. So straight off the bat, it's asking for O log n time complexity. We have a rotated sorted array. So sorted is the key word here. So this means we're going to be utilizing binary search to solve this problem. So the examples are pretty straightforward. The target is 0 and the output is 4. So the index here is 4. The target in example 2 is 3. It's not in the nums array, so we return -1. And same with example 3. So as we mentioned, we're going to be using binary search to find the solution to this question. And binary search is searching through a sorted array. Now, as you can see with this array, if we look at the graph to this array, we have an incremental change up until this point, and then all of a sudden there is a drop, and then it goes to the incremental change again. So we have this area here and this area here, which are both sorted. So we're not going to be able to run binary search on the entire array. So we're going to have to run 2 binary searches. We're going to have to check which side is sorted, and then we're going to run a binary search either on the left side or the right side and adjust accordingly. So let's do that. We've got left, we've got right, and we've got mid. Now to work out which side is sorted, the way you could go about doing this is to check whether the nums at mid is less than nums at right. If it is, then we can say that the right side is sorted. If it isn't, we can say the left side is sorted. So in this case, nums at right, which is 2, is not greater than nums at mid. So we look in the left side for the target. And in this case, target is equal to 0. So we check on the left side whether target can be found in there. So if target is less than nums at mid and greater than or equal to nums at right, neither of those are true. What we can do is we can increment left to mid plus 1. So left goes here. We can update this, and now we can search in this section of the array. So mid is here. Is mid less than right? Yes, it is. So we can look for the target. Is target greater than nums at mid and less than or equal to nums at right? Well, it isn't greater than nums at mid, but it is less than nums at right. So we can just update right to be mid minus 1. Now that we're on here, mid is this value. If nums at mid is equal to target, we can return that value then. So we can return this index, which is 4. Let's run through another example. So let's say we have, and target is equal to 8. Well, the first thing, we get the left and right. Make sure we have the mid, and we check to see which side is sorted. So if mid, nums at mid is less than nums at right, we know that the right side is sorted. But in this case, again, it's not sorted, so we'll go to the left side. Yeah, because the right side, we have 8, 0, and 1. We know for a fact that's not sorted. And then on the left side, we have 4, 5, 6, 7, which is sorted. Then we can check for the target in the left side. Okay, so we check, is target less than nums at mid? No, it's not. So we can increment left to nums at mid plus 1. So we update mid now. So mid is here. We check if this is sorted. So is nums at right greater than nums at mid? Yes, it is. So now that the right side is sorted, we can look for the target in this area. So is target greater than nums at mid? It is greater than nums at mid. And is target less than or equal to nums at right? No, it's not. So what do? We decrement right to mid minus 1. So right comes here to clean this up. Now update mid, so mid comes here, and then we just return the index of mid. Okay, so when we're writing this out, we need a left pointer, we need the right pointer, and we need to create that while loop for the binary search. So while left is less than or equal to right, we need to grab the mid, now we work out the mid this way rather than doing math.floor right plus left divide by 2 because this avoids stack overflow. We can check if nums at mid is equal to target. If it is, we need to return the index of mid. Now we need to check which side is sorted. So as we said in the solution, so nums at right, if nums at right is greater than nums at mid, we know that the right side is sorted. So we can check in the right side. So if target is greater than nums at mid, and target is less than or equal to nums at right, we'll increment left. So we'll say left is equal to mid plus 1, else we'll change right to mid minus 1. So that's if the right side is sorted. Else, we need to make the check in the left side. So if the left side is sorted, we need to carry out the binary search on that side. So if target is less than nums at mid, and target is greater than or equal to nums at left, then we change right. So right becomes mid minus 1, else left equals mid plus 1. And remember at the end to return minus 1, just in case the target is not within the array. Let's give this a run. Okay, that's been accepted. Let's submit it. Given an integer array nums, return all the triplets nums I, nums j, nums k, such that I does not equal j, I does not equal k, and j does not equal k. And nums I plus nums j plus nums k is equal to 0. Notice that the solution set must not contain duplicate triplets. So here we have a nums array of random numbers, and our output is an array of arrays containing 3 values or 3 integers that add up to 0, and they do not include duplicate triplets. So we need to find all the different combinations of triplets within this nums array that equal 0 that aren't duplicates. So when thinking about this, a brute force approach would be to loop through this array 3 times, then compare the values, and if they equal 0, push it into the array and then remove the duplicates. But the time complexity on that would be quite heavy. It would be n to the power of 3. So an optimized approach would be to have, say, a for loop and a 2-pointer technique. However, the first stage would be, in that case, to sort this nums array. And the reason we need to sort it is because the 2-pointer technique relies on sorting so that we can determine which integer to go to next based on whether it's below 0 or above 0. We need to sort this array, so let's just sort it. So we have -4, -1, -1, 0, 1 and 2, and we can do this in place so it won't take up any extra space. So the 2 loops will have the for loop, which starts at this position, starts at I, and we'll have j and k that are acting as our 2-pointer technique. So j and k will move across depending on whether the total summation of the current numbers in here add up to less than 0 or add up to greater than 0. So let's walk through this process. So we've got -4, -1 and 2 as our first example. That is less than 0. So we can increment j. -4, -1, 2 is less than 0. So we can increment j. -4, 0 and 2 is less than 0. So we increment j, and that is also less than 0. So at this stage, we increment I. So I goes there, j is I plus 1, and then we repeat the process. So we have -1, -1 and 2. At this point, this is equal to 0, which is what we want. So we can push this value into res. Now at this point we need to check for duplicates. So we can say while nums at j is equal to nums at j plus 1, continue. So increment j. So if this value here is equal to this value, then we continue. If it isn't, we just increment j. So j will go here. So at this point we have -1, 0, and 2. That's going to equal 1, which is greater than 0. So at this point we need to decrement k. So k comes this way. We can remove that. Now we have -1, 0, and 1, which gives us 0 again. So we can add that into our res array. At this point j and k can't go any further, so I moves forward. But at this point we need to check. We need to check whether I is equal to I minus 1, because if those are the same, we're going to get a duplicate triplet. So we need to check this value, and if that is true, then we need to increment again. So we need to continue. So I goes along again. Then we have j and k, 0, 1, and 2. That is greater than 0, and j and k have nowhere else to go. So we just return res. So the hardest part of this question is definitely in removing the duplications, but we'll go through that in writing out the solution. But for now, let's discuss the time and space complexity. So the time complexity of this, we have the sorting, which is going to be on log n. We have a 2-pointer, which is on, and that is looped through n number of times, so it becomes on squared. So time complexity is O log n times n squared, which simplifies to on squared. And space is O1 because we aren't allocating any extra space for the sorted array, we're just updating nums. So let's sort this out. So firstly we can look at the constraint. Nums.length can be greater than or equal to 0. So let's cover that edge case. So if num.length is equal to 0, just return an empty array because that's what it's asking for. Now we need to sort nums. So nums equals nums.sort AB A minus B. This is JavaScript syntax in order to sort the array. Let res equal an empty array. So now we can start the loop. So we loop from I is equal to 0, I is less than nums.length minus 2, because remember there are going to be two values at the end, j and k, which are the 2 pointers. And at this point we need to write something to stop duplicates from occurring. So if I is greater than 0, and remember we said if nums at I is equal to nums at I minus 1, then continue. Remember I was at this point, we moved over to this point, they were the exact same, so we compare I with I minus 1 if they're the same, so we move along and we avoid duplicates. Let j equals I plus 1, let k equal nums.length minus 1. So the 2-pointer technique, j is always initialized as I plus 1 and k is always the last value. So let's start the loop with the 2 pointers. So while j is less than k, so we'll add those values up. Nums at I plus nums at j plus nums at k. If sum is equal to 0, so if we have found a potential solution, we can push into res the results, and we need to make sure that it's an array. Now we need to again stop duplicates with j and k. So while nums at j equals nums at j plus 1, we increment j. And while nums at k is equal to nums at k plus 1, we decrement k because k is the endpoint. If they aren't equal, we still need to increment j and decrement k. Else, if sum is less than 0, so in the case where summation of all the triplets is less than 0, we need to increment j to move j pointer right. If it's greater than 0, then we need to decrement k. Finally, we need to return results, and then we can check to see if this has worked. Okay, let's submit it. So you're given an array height of length n. There are n vertical lines drawn such that the two endpoints of ith line are i0 and I height at index I. Find two lines that together with the x-axis form a container such that the container contains the most water. return the maximum amount of water a container can store. So the basic idea of this is to carry out some kind of two-pointer technique where we only have one pass throughout this entire height array, keeping the time complexity at O of n. And what we'll do throughout the iteration is we'll compare the height to left and right and then work out the overall area that it stores, and then we'll store it in a maxima variable, constantly update it as we go through working out the values. So let's have a quick look at how that would be worked out. So here we have the height, here we have the amount, and here we have the height array values. Okay, so what we'll have is we'll have a left pointer here, we'll have a right pointer here, left at the start, right at the end, and what we want to do is we want to work out the area that is stored between the left and the right value. So if we ignore all of these values in the middle for now, and we've only got this one and this one, if we poured water in this container, once it reaches this level, it's going to start overflowing, right? So we only want to take into consideration the height of the smallest height value when considering working out the area. So area is going to be equal to, and it'll be equal to math.min, height at left, height at right. So that's the first part of the area, but we also need to times it by the width. So we've worked out the height, and area is height times width. So in order to work out the width, it's just the right minus the left. So it'll be 9 minus 1. So right minus left. And that works out the area. So what we're going to do then is we're going to add it to a maximum variable. So say like we have a variable called maxima, and it starts off at 0. We calculate this area. It's 9 minus 1, which is 8, times by 1. So this will be increased to 8 because we can work that out. And then we need to move one of the pointers inwards based on the smallest value, really. So the height with the smallest value, if it's the left side, we're going to increment inwards. If the right side is the smallest value, we're going to decrement inwards, okay? So with this one, left is definitely smallest, so we increment inwards. And now we can compare this one. Let's have a look at the area. So we've got 8 and 7. If we worked out the area, if we filled this in with water, it's going to reach this level before it starts overflowing. So the height is 7, yeah? And then the width is 9 minus 2, which is 7. So the maximum is going to be equal to 49. And now the right side is smallest value, so we're going to decrement inwards. Okay, so we can then calculate this one. So ignore all the rest. The smallest height here is 4, so that's going to be 4. And then in terms of the width, it's 8 minus 2, which is 6. So 6 times 4 is 24. And is that greater than 49? No, it's not. So we move inwards. So the smallest value again is right. The right pointer moves inwards, and we are now here at this point. So we focus on this area. So the smallest height is 8, and the width is 7 minus 2, which is 5. So 8 times 5 is 40. Is 40 greater than 49? No, it is not. So then we move inwards. And as you can see, there isn't going to be another area that is greater than 49. So at the end, we will be returning maxima. So that's the general idea of how to calculate this. Let's jump into the code and see how it's implemented. Okay, so let left equals 0. Let right equal height.length minus 1 because we want the last value. Let maxima equals 0. So we'll have the while loop. While left is less than right, what we can do is we can work out a number of things. So the width equal to right minus left. Then max area is equal to math.min. And it was the minimum between the height on the left and the height on the right. And it was times by the width. Then we can update maxima, passing in the maxima, so the current max, and the max area that was just calculated. Then what we need to do is we need to increment the left or decrement the right based on some constraints that we pass in. So if height at left is less than or equal to height at right, I say less than or equal to just in case both values are the same. Then what we're going to do is we're going to increment left. Else we can decrement right. And finally, we need to return the maximum value which we've worked out. So let's see if this works. Okay, so it's been accepted. Let's submit it. Given a string S, find the length for the longest substring without repeating characters. So we have a string here, the output is 3, and the explanation is the answer is ABC. And here we have a string which is all B's, the output is 1, the answer is B, because we aren't allowed any repeating characters. So we need to determine what a substring is first of all. So a substring is just a value or a group of letters that are adjacent to each other within the original string. This is a substring, this is a substring, this is a substring. However, this is not a substring, this is not a substring. You get the idea. So off the bat, we know straight away that we're going to have to loop through strings. So we could brute force it, and we could have multiple loops, which would give a time complexity of on to the power of 2. But we want to make this as efficient as possible. So firstly, in order to see whether we've visited certain values within the string, we can use a set. So a set is a data structure that allows for constant lookup, and what we'll use is we'll use a slide-in window technique. So we'll have a left pointer, a right pointer. This way, we only need to loop through this once, so we can keep the time complexity relatively small on this. So let's walk through how this slide-in window approach will work. At the first point, we're going to check A. We're going to see if that's in the set. If it's not, we're going to add it to the set, and then we need to update the longest substring variable. So this will begin as 0, and what we're going to do is we're going to say the longest substring is equal to the max between the longest and set.size. We've looked at the first value, we've added it to the set, we update the longest because the longest will be the maximum between longest, which is 0, and set.size, which is currently 1. So we can update that to 1. We can move the right pointer over, so right moves here. We add B to the set, we update longest to 2, we move right along. We add C to the set, we update longest to 3, we move right along. Now we've reached A. A is in the set. So what do we do here? Well, you would think we could just delete A from the set. But say for example, so with this, we'll add P to the set, we'll increment the longest by 1, we'll add W to the set, increment longest, then we get to the second W. So if we just delete W from the set, what's going to happen here? And say we add W again here, we're still going to be including P here. So this value plus this value is no longer a substring because they aren't adjacent to one another. So what we need to do in this instance is just delete the letter at the left pointer and then increment the left pointer to here. So that will remove A from the set. Then we can begin this loop again. So we've got B, C, and A. So the right pointer is on A. Is A in the set? No, it's not. So we can add it into the set. We can check against the longest. So we have 3 and 3, so that can stay the same. And now we can increment the right pointer and it's reset. So we have B here and we have B here. So B is already in the set. What do? Well, we delete the letter at the left pointer and then we increment the left pointer by 1. So we remove B from the set, increment the left pointer, and then carry on with the loop. At this point, B is not in the set, so we can add it into the set. We can check against the longest. They're still the same, so we can increment the right pointer. So right moves here. C is now in the set. We delete it from the set. We move the left pointer over, and we start again. So we check, is C in the set? No, C is not in the set. We add it into the set. We compare it with the longest. They're both the same. We move the right pointer forward. Now we check here. Is B in the set? Yes, B is in the set. So we need to delete the value at the left pointer. So A can be removed from the set. We need to increment the left pointer, and then we need to repeat the process. So again, is B in the set? Yes, B is still in the set. So we delete the value at the left pointer, which is B. We increment the left pointer, which is now C, and then we move along and we repeat the process. So is B now in the set? No, it's not. So we can add it into the set. We can compare it to the longest. 2 is smaller than 3, so we increment right pointer again. We add another B. So what happens here? Well, we need to delete the value at the left pointer, which is C. Increment the left pointer, so it moves to B. Then we can compare again. So is B in the set? Yes, it is. So we delete the letter at the left pointer, so B can be removed from the set. We increment the left pointer. Now we can check, is B in the set? B is not in the set, so we can add it into the set. We can compare it to the longest. Longest stays at 3. Now we move right, and this is now out of bounds. So we've covered the entire string, and the longest value is 3, which we return. So in terms of time and space complexity, time complexity is O to n, where the left and right pointer have to go through each value in the string, and this can be simplified to O of n. Space complexity is O of n, where in the worst case scenario, we are storing all values of the string within the set. So let's begin by creating the longest string variable, which we'll set as 0. Let's create the new set. Let's create the 2 pointers that are both going to be equal to 0. And then let's create this slide-in window technique. So that's going to be a while loop. So while right is less than string.length, firstly we can extract the letter to make it easier to read, so it's going to be s at right. And then we need to check within the set. So we need to see if the set doesn't have the letter. If that is the case, then we need to add the letter to the set, and we need to update the longest string variable. And that is going to be math.max, longest string, compared to set.size property. And then after that, we need to increment the right pointer to avoid an infinite loop. Else, we need to start deleting from the left pointer if the letter is within the set, and then we need to increment the left pointer. And then we can just return the string. Okay, let's give that a go. Okay, let's submit it. So in this question, we have to return the length of the longest substring that contains the same letters, and you're only allowed to perform k operations or k updates. So we have 2 updates that we can perform in example 1, and we have this string of A, B, A, B. So we can update one of these strings for one of these operations. So if we update A to B, k will decrement to 1. And then if we move along and update A to B again, then k will be equal to 0. We've used up all our operations, and the longest substring we can generate from that is 4. Okay, so we know what we need to do in this question. We have a string right here, and we can see from this, if we choose this substring, we'll have to update this character right here to an A in order to get a value of 4. So how would we go about doing that? Well, we can loop through this array using a left and right pointer. So left and right. We can map out the indices. We want to get the length of this string. So it'll be right minus left plus 1 to get it, right? Because 3 minus 0 plus 1 is equal to 4. The length of this substring is 4. So right minus left plus 1. Now, in order to get the amount of B's within this substring, because we want to update the B, right? In order to get this B, we need to subtract the A's. So we need to grab the frequency of the A's, right? So if we say minus A frequency, which is essentially going to be 3, this will give us the value of B, right? So this is going to give us B. Now, if B is less than or equal to K, then we can update the longest to the length of this substring, right? So if this is less than or equal to K, we can update the longest to equal this substring. So this is the equation we're going to be using for this solution, but how are we going to map this out? Well, we're going to need a map data structure. We're going to use a 2-pointer technique along with this, and this map is going to store how many times we see each character. So up to this level, we have A is pointing to 3 and B is pointing to 1. We're also going to need a top frequency, right? And this variable is just going to be the character that we have seen the most throughout this. So at this point in time, it's going to be 3, right? Because A is mapping to 3, B is mapping to 1, the greatest is 3. Now we can slightly adjust this equation. So rather than A frequency, we can add top frequency, and this is going to equal smallest frequency. So let's run through this solution. We start off here, we have a left and right pointer. Let's map out the indices. So the first thing we do is we look at the right point. We see that we're at an A. Is A within the map? No, it's not. So we update the map to contain A and add a value of 1. We update the top frequency to 1, and we can use this equation down here in order to work out whether we can update the longest. And we already know we can update the longest in this case, so the longest is going to go to 1. We move across, we update the map to 2, top frequency is going to be 2. Again, we can update the longest. We move the right pointer to B. Now we add B into the map. Top frequency is going to be the maximum between top frequency and the value we just added in. And now we make a check. So it's 2 minus 0 plus 1 minus top frequency of 2. This is equal to 1. Right, so the smallest frequency, as we can see in the map, is equal to 1. Is this less than or equal to k? Yes, it is. So we can update the longest to right minus left plus 1. Right, because the longest is going to be the maximum between the current longest and this value here, which we've worked out is valid. So we'll update longest to 3 and we'll move our right pointer along. The right pointer is at an A. We can update the map at key of A to 3, and also we can update the top frequency to 3 now. Now we can look into this equation, right minus left, so 3 minus 0 plus 1, which is equal to 4 minus the top frequency of 3 is going to equal 1. This is equal to k, so this is a valid substring. So we can update the longest to right minus left plus 1, which is going to be 4. And then we move the right pointer along. So the right pointer is at a B, so we update B within the map to 2. Top frequency is still 3, and now we make the check. So right minus left, so 4 minus 0 plus 1 minus the top frequency of 3 is equal to 2. This is greater than k. So here we need to decrement the value of A from map. So A goes to 2, decrement the map before moving the left pointer, then we update the left pointer by shifting it across by 1. So now that we've updated the map, we've decremented the value and moved the left pointer across, we also need to update the top frequency, which is going to be 2, the highest frequency within the map that is. And now we can update this equation. So it's going to be 4 minus 1 plus 1 minus top frequency of 2. Well, what is that equal to? That is still equal to 2. So again, we need to update the map. We decrement the value of A, we move the left pointer along. Top frequency is still 2, so we're at BAB. So it's going to be 4 minus 2 plus 1 minus top frequency of 2. Now that is going to be 1. So this is valid, right? Because the smallest value is A in this case. So now we can compare this substring with the longest value. The longest value is still 4, so we keep that, and then we iterate across. So we move the right pointer across, we repeat the process. We update the value of B in the map to 3. Top frequency goes to 3, and then we look into this equation. So right is equal to 5, left is equal to 2 plus 1. This minus the top frequency of 3 is going to give us a value of 1. This is valid because it's equal to the number of operations that we can carry out within this substring. And as we can see, the only value we need to remove is A. So this substring is equal to length 4. We check it against the longest value. They're equal, so we keep 4. And then we repeat the process. So we move the right pointer along, check the map, check the top frequency, update this equation, and as you can see, for the rest of the string, we're not going to get anything longer than 4. So that is the solution to this question. And time complexity for this solution is going to be O of n, where n is the length of the string, and space is going to be O of n, where n is the amount of keys within the map. So let's code this out. We're going to initialize a map, our top frequency, the longest string, and the left and right pointer. So while right is less than string.length, we need to carry this out. So let's first extract the right character, which is going to be s at right. Then we need to update the map. So look into the map to see if we have the right character. If we do, then we just add 1 to the value that is within the right character. Otherwise, we set it to 1. Then we update the top frequency, which is going to be math.max between top frequency and map at right character. And this is where we implement the equation. So it's going to be a while loop, and it's going to be while right minus left plus 1, so the length of the substring, minus the top frequency, so the character that has been seen the most. If this is greater than k, then we need to update the left pointer. So let's get the left character, which is s at left. Let's decrement it from the map. And then let's update the left pointer. So this will iterate through the string until we have a valid substring, and then we can update the longest, which is going to be the maximum between the current longest and the current length of the substring, which is right minus left plus 1. And finally, we need to update the right pointer. Then all we need to do is return the longest and give this a run. Submit it. So given two strings s and t of lengths m and n respectively, return the minimum window substring of s such that every character in t, including duplicates, is included in the window. If there is no such substring, return the empty string. So the test cases will be generated such that the answer is unique. A substring is a contiguous sequence of characters within the string. So in the first example, we have Adobe Code Bank and t is equal to ABC. So we need to find the shortest substring within S that contains all the values of t. So in this, there are multiple substrings, but the shortest one is bank, which is found at the end here, containing 1b, 1a, and 1c. And that is the output that we need to give. In the second example, we have a as the output because t contains only 1a. The string itself only contains 1a. So that meets the requirement. So it meets all of the values that are in t within the string of s. And finally, in example 3, we have an answer of an empty string. And the reason for that is t length is greater than the length of s. So we will never find two instances of a within a string that only contains 1a. So could you find an algorithm that runs in om plus n time? So let's discuss a potential solution with that time complexity. So this is a pretty difficult question. There's so much to take into consideration here, and especially with the fact that we've got to hit om plus n time complexity. So with this time complexity, we can have a trade-off. So we can increase our space complexity in order to hit this time complexity. And one great way of utilizing more space to improve time complexity is by using something like a map data structure when comparing two values. So we're going to have a frequency map that is going to store all the values of t and the amount of their occurrence. So we're going to have a, which is pointing to 1, b, which also has 1, and c is also going to be equal to 1. Right? And the great thing about frequency maps or map data structures is they have constant lookup. We can say that this map is the m within this time complexity, and this n, we can actually update that to be s. And that's going to be this string right here that we're going to loop through. And because we're only allowed to loop through it once, a great technique that we can use is the two-pointer technique, where we have a left and right pointer. That way, rather than traversing the string multiple times and increasing the time complexity to something quadratic, we can keep it linear and compare values together. So how this solution is going to work, we're going to loop through this string. We're going to check at each point whether the value that we're on is within the frequency map. If it is, we're going to decrement the value associated with that letter. And once the frequency map is all equal to 0, we then know we have found a substring within the string of s. So we can update our minimum window substring. So before we do that, we need a couple more variables to take into consideration. So we need a count, which is going to be equal to the size of this frequency map, which is 3. And we also need to declare our minimum window, which is going to be set initially as an empty string. And the great thing about setting it as an empty string is it takes care of that case where we do not find a substring within the string s, because we're going to be returning this, so we will return an empty string. So let's give this solution a run through. At our right pointer, we have the letter a. Is a within the frequency map? Yes, it is. So what do? We decrement a to 0. Now once a or any of these values point to 0, we can decrement the count because we have found all occurrences of that letter within the substring that we're looking for. So we found all occurrences of a, so we can decrement the count. We only need to find 2 more letters, b and c, in order to find a potential solution. Now we can increment the right pointer. So right pointer moves to d, d is not in the set, we move over to o, o is not in the set, we move to b, b is within the set, so we decrement b, b goes to 0. So we found the required amount of b within our string. So we can decrement count now. So count goes to 1, and we can increment the right pointer. So we go to E is not within the map, so we can move along. We go over to C, C is within the map, so we decrement C, and now C is equal to 0, so we decrement the count, and we move the right pointer along one more. Now here is where we have to add additional logic. Because count is equal to 0, we have found all occurrences of A, B, and C, so we have found 1A, 1B, and 1C. Those are the requirements that are needed for T within this substring. So we have A, B, and C. So we have this as a substring. And I say it's Adobe C rather than Adobe CO because we are going to slice from the left pointer to the right pointer. So s.slice left, right is going to give us Adobe C because the right value here within slice is non-inclusive. Okay, great. So we have found a substring, a potential solution. So we need to update the minimum window to that solution. But we have another issue here. We have an empty string here. And usually what we do in a case like this is we compare the minimum length of the minimum window with the length of this substring we have. But we can't do that here because the minimum window is much shorter than the substring and it will always be the result. So we need to create another variable. So we have the len variable, and this is going to be set initially to infinity. So whatever length substring we have as our initial substring, it will always be less than that. So minimum window will always update to the first substring we find. So we can do that now. We can update our substring to equal Adobe C. And now we have to carry out a sliding window technique in order to increment the left pointer to find all possible substrings within this string. So while count is equal to 0, we check the map. If the map has the value at the left pointer, so it has A, so we increment A to 1. And if this value increases, or if any of these values increase above 0, we can increment the count, basically saying that we need to find one occurrence of A to find another substring now, and we can increment the left pointer. So once we have done that, we can repeat the process with the right pointer, so we can check if O is within the frequency map. It's not, so we can move that along. D is not within the frequency map. E is not within the frequency map. So we get to B. B is within the frequency map. And what do we do when we find a value within the frequency map? We decrement it. So B moves to -1. Now usually we decrement count, but B is not equal to 0. B is equal to -1. So we have two occurrences of B within the substring. So we do not decrement count because the only value we're currently looking for is A. We want to decrement this to 0. So we can just carry on. We can move the right pointer to A. We have finally found A. We can decrement that to 0. And now we can decrement count to 0. We can increment the right pointer. And now that count is equal to 0, we have found another substring. So D all the way through to A here. So we have A, we have B, and we have C. We can check if this is less than the minimum window. It's not. So we carry out the sliding window technique. We check to see if this point here is within the frequency map. It's not. We move it along. O is not within the frequency map. B is within the frequency map. So we increment B. So this goes to 0. However, B is not greater than 0. So we do not increment count because remember, we still have an instance of B over here. So we move the left pointer along to E. That is not within the frequency map. We move it along to C. That is within the frequency map. So we update C to 1. And now C is greater than 0. We can increment count. Then we can increment the left pointer. And now we can repeat the process on the right side. So is N within the frequency map? No, it's not. So we move the right pointer along. Right is at C. C is within the frequency map. So we decrement C. Great. That's now equal to 0. We decrement count. Now count is equal to 0. So we have a current minimum window substring, which is equal to this string right here. Is this less than Adobe C? No, it's not. So we check the left pointer. We see if that's within the frequency map. No, it's not. We move along. We now have a new substring, which is equal to this substring. Is that less than the minimum window? No, it's not. So we increment the left pointer and we check if the left pointer is within the frequency map. No, it's not. But at this point, we have a new window substring. eBank. Is that less than minimum window? Yes, it is. So we can update that to be equal to eBank. Now we check to see whether E is within the frequency map. It's not. So we move the left pointer along. We now have a new substring, which is equal to bank. And that is less than eBank. So we can update that. And we check to see whether B is within the frequency map. It is. So we update B to 1. B is now greater than 0. So we update count to 1. And then we increment the right pointer. And then that is out of bounds. So we exit this loop and we return bank. So time complexity for this algorithm is, as stated in the question, O t plus s, where t is all the values within t string. because we need to create this frequency map, and S is all the letters within the S string. Okay, so let's start writing this out. So let's initialize the map data structure. So map is equal to new map. Let's loop through the values of T and create that frequency map. So that letter T. So if the map doesn't have letter, then we can initialize it with 1. So map.set letter 1. Else we just need to add to the current value within the map. So map.set letter map.get letter plus 1. So that'll populate the frequency map. Then we need to initialize all the variables, so the left and right pointer, len, which is going to be equal to infinity, count, which is going to be equal to map.size. So the map has and the count, which is going to equal to map.size. So map has a size property, which will be equal to 3 within the first example. And then we also need min window to be initialized as an empty string. And then we can start the loop. So while right is less than s.length, we can extract the letter at the right pointer. So our letter is equal to s.right. Make it a bit easier to read. If map has our letter, so if the frequency map has the letter at the right pointer, we can decrement the value of that letter within the frequency map. And then we can do an additional check to see whether that value is now equal to 0. We can decrement count if it is. And then we just need to increment the right pointer there. So while the count is equal to 0, so we have found a substring. If right minus left is less than len, which we will be updating. So the first time we check right minus left, it will be checking against infinity, so it will have to be updated. We'll update the length to equal right minus left. So this is the current length of the substring. And then we need to update minimum window variable to equal s.slice and slice from left up to, but not including the right pointer, because remember we incremented right on line 32. Then we can use the sliding window technique and increment the left pointer here. So let's extract the left pointer to make it easier to read. And let's check to see whether the map has the value at the left pointer. If it does, we can increment the value within the frequency map by 1. And then we can do an additional check to see whether the value at the letter is greater than 0. And if it is, we can increment count. Then we just need to increment the left pointer. And finally, we can return min window. Let's give this a run. Okay, let's submit it. So given two strings s and t, return true if t is an anagram of s and false otherwise. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So in the first example, we have anagram and Nagram, which returns true because if you see all the values within s are within t and there is no remaining values. Rat and car in the second example is false because we have two letters in each which don't add up, right? The only thing that's similar between the two examples here is the A. So we could use some kind of sorting algorithm and sort them and then see if they're the same. That would work just fine. But what we're going to use instead is a hash table, also called a frequency map. And we're going to store the frequency. So we're going to loop through S and we're going to update our frequency map. So this is what the frequency map is going to look like. So we're going to have A, which is going to be pointing to 3, right? Because we've got 1, 2, 3. N, which is pointing to 1. G, which is pointing to 1, R, which is pointing to 1, and m, which is pointing to 1. So we've created our frequency map. Now what we can do is we can loop through t, and we can see if the letter at this position is found within the frequency map. And if it is, then we can subtract it from the frequency map, and then we move along. We can subtract it, we can move along, subtract it, we can move along, subtract it. And then once this is complete, if we pass all the tests that we have in our for loop, checking the frequency map, then we can return true, right? But say we have an A here, we get to the A, this is going to go to -1. So we need some conditional logic, which is going to say if map at letter is less than 1, just return false. Or if it's undefined, return false. So the way this algorithm is set out, time complexity would be on, where we create the hash table. So we have to loop through each value within string in order to create the hash table. So that's going to be of n times. So it's going to loop through the entire string, plus m, where m is looping through the entire t string. And then suppose complexity is O of n, because we're storing all the values of string s within our hash table, which we created. So firstly, before we add any code, we can take care of an edge case, right? So if s.length doesn't equal t.length, then it's not going to be a valid anagram because they're not the same length. Then we need to initialize a map. So our hash table, which is going to be an object, we need to loop through string s, and we need to populate that map. So let's just declare letter as si. So we're grabbing each letter here. If the map at letter doesn't exist, we're going to create it and set it equal to 1. Else, map at the letter gets incremented. So if there's already a value within map at letter, then we just increment it by 1. And this will give us the frequency map we're looking for. Okay, so the second part of this algorithm, we just need to loop through the second string. Create a variable called letter, we'll equal it to t at position I. So the second string at position I, to make this code a bit more readable. Then we need to carry out a few if clauses. So if map at letter is undefined, we can return false, right? Because it's not found within the map. So they aren't valid anagrams. If map letter is less than 1, we can return false because there's more of the same letter in one string than there is in the other. So return false, and then map letter decrement. So if we pass the first two if statements, then we need to decrement from map at that letter's position. And if we pass all that throughout the entire for loop, we can return true because that will essentially be a valid anagram. Let's run this to see if it's worked. Okay, let's submit it. So given an array of strings, group the anagrams together, you can return the answer in any order. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So in example 1, we have an input which is an array of words, and our output is an array of an array containing words. And these words have been ordered based on their anagrams. So if we look at NAT and TAN, they all have the same letters in, just rearranged differently. So let's think of a way that we can solve this problem. Oh, so we have this array of strings, right? Now we need to work out which words go in which anagrams, or which words are grouped together based on their anagrams. Now the easiest way to think of that we could possibly do this is to order them alphabetically, right? So loop through the strings and order them alphabetically. So with this one, it would be AET. With this one, it will be AET. With this one, it will be ANT. AET again, ANT, and ABT. So as you can see, this one, and this one can be grouped together. These two can group together, and then you have this one on its own. So how do we get from this to a returned answer where each one of these are grouped in arrays? We could use a map data structure. And what we do is we'd loop over, say, the sorted array. So we'll create this as an array. We'll loop over this, and we'll map the values within the strings array to the values within the sorted array. So it's going to look like this. AET, we loop over, first value is EAT, that's going in there. You get to the second value. T is now going in here. You get to the third value, we've got ANT. We add tan in there. We move over, we've got 8, which goes in here. We move along, we've got nat, which goes in here. And finally, we've got ABT, which is going to store that. And then all we need to do in order to get our answer is just return the values. Now in terms of time and space complexity, time complexity in this instance, we are looping over this array to begin with, which is going to be n, and then we have to loop over each individual word in order to sort it. And the sorting of each string will be k log k. So n is the length of strings, and k is the maximum length of a string within the strings array. And then space is going to equal O n k, the info that we're storing within the map. So let's write this out. So first step in solving this problem is to create the sorted array. So let's do that now. The way we do this in JavaScript is we can map over strings, pass in string, and then we split the string, so we turn it into an array. We sort the string, and then we join the string, so we turn it back into a string. That will give us an array of strings that are sorted alphabetically. Now we need to create the map data structure. So we can just define this as plain object, and then we need to loop through the sorted array we just created and check if the map contains that value. If it doesn't, then we can add it to the map and map it to the string values. So let's do that. So if map doesn't have sorted at I, so if it doesn't have the sorted value, we can create it. So map sorted at I is equal to strings at I. And remember to put this within an array, because we want to return the values organized within arrays. Else, if sorted is already in map, then we can just push the value into it. So map sorted at I dot push strings at I. And at this point, what we have is we have an object containing key value pairs, and the key is the sorted value and the values are the strings. So in order to get the values out of this object, what we can do is we can return object.values and pass in the map. Let's see if this worked. Okay, great, let's submit it. So given a string s containing just the characters open parenthesis, closing parenthesis, open curly brace, closing curly brace, and open square bracket and close square bracket, determine if the input string is valid. An input string is valid if 1. The open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order. So in the examples, we have an opening and closing bracket. This returns true because it follows a valid input string. So we have an open bracket followed by the same closing bracket. Example 2 is also true because we have open, close, open, close, open, close with respect to each different bracket. And then the last one, we have two different brackets, one open, one closed, and that's going to return false because it's not closed by the same type of bracket. So let's jump into the explanation. So with this question, the most important thing to remember is that it needs to be in the correct order, and that would suggest to use something like a stack data structure, right? So we can loop through this and we can input into the stack any opening brackets, and then we can check the counterpart to see if it's the corresponding closing bracket. So a stack data structure is simply an array, but the most important part of a stack data structure is the processing order. So the processing order is last in, first out. So say we added 2 curly braces and 1 square bracket in that order. The first one that we're going to be removing is the square bracket, right? So we're going to pop off from this stack data structure. Okay, so that's what a stack data structure is. So the way we're going to solve this is we're going to loop through this string. We're going to push in to the stack all the values that are open, and then once we get to a closing bracket, we're going to check to see whether the open bracket is equal to the corresponding closing bracket. So we'll pop off a stack, we'll have that current value, and then we'll check to see whether the next value is the counterpart, so is the bracket's counterpart. So let's run through this first example. So we start looping through the string, we push in an open bracket. The next value that we're on, this one, is a closing bracket. So what do we do here? Well, we need to check whether the previous bracket is the same but its counterpart. If we pop off the stack here, so we've got this open bracket, Now we need to check with the current value, which is this value. If they are not equal to each other, we can return false. But in this case, they are equal to each other. So we just loop through. The stack is now empty. We move to the next one. It's an open bracket. So we add that to the stack. The next value is a closing bracket. So what do? We pop off a stack. So nothing is in stack now. We check to see whether the square bracket does not equal the current value we're on, which is a closing bracket. If that is true, we return false. But in this case, we don't need to. We just move through this. So we go to the next position, which is an open curly brace, add that into the stack. We move along, we check. We have a closing bracket. So we need to check whether the previous one in the stack is its counterpart. So we pop off the stack and we check whether this does not equal its closing counterpart. In which case, we exit this and we can just return true, right? And that will solve this example. However, say we have another example with all open brackets. Based on what we just did, we looped through and we pushed into the stack all the open brackets. So let's do that now. And now we have finished the loop. So if we use the previous example, it will return true. So we need to account for this. And the way we do this is we say if stack.length is equal to 0, return true. So if the stack has been emptied, we know we found all of the counterparts. And if not, it's going to return false anyways. Now there is one other example. If we have all closing brackets, we have a stack data structure. It's going to loop through and it only pushes in opening brackets into the stack. We have none. So when it gets to this position, it's going to look at the previous value for the stack. So it's going to try and pop off the stack, but there is nothing in the stack. So this is going to be undefined. So we need to create another case. And that is if the value we popped off a stack, let's just call it prev value, is equal to undefined. So if there isn't any previous value, return false. So when solving this problem, make sure you go through a number of different examples just to make sure you've covered all edge cases. So time and space complexity. Time complexity is ON because we need to traverse through the entire string. And then space complexity is also ON. So very simple complexity. And that is because we are storing all the values within the stack. So let's initialize the stack data structure. Now we need to loop through the values in the string. We can extract string at I and just put it in a character variable. Then we can say if character is equal to an open bracket or is equal to a curly brace or is equal to an open square bracket, we can push into stack that value. Else we need to get the previous value, which is going to equal stack.pop. So we're going to pop off the stack because remember stack data structure is last in, first out. And then we're just going to create a number of cases. So if prevval is equal to an open curly brace and the character that we're currently on does not equal a closing brace, then the open brackets are not being closed in the correct order. So we can return false. And then we can do this for the other two cases. And the last case we discussed was if we have a test case where all of the values are closing brackets, we're going to have prev value equaling to undefined at this point. So if prevval is equal to undefined, we can also return false. And lastly, there was that base case we need to cover where it's all open brackets, right? So the string is all open brackets. The stack is going to contain those values. So we need to make sure that the stack is emptied at the end. And the way we do that is we just say stack.length is equal to 0 and we return that. Let's give this a go. Okay, so equal operator. Okay, so that's true. Let's submit it. So a phrase is a palindrome if, after converting all uppercase letters into lowercase letters and removing all non-alphanumeric characters, it reads the same forward and backward. Alphanumeric characters include letters and numbers. So given a string S, return true if it is a palindrome or false otherwise. So in this example, we have a man, a plane, a Canal, Panama. This is going to return true because once we get rid of the non-alphanumeric characters, so like the commas, the spaces, the semicolons, it's going to be the same forwards as it is backwards once we create all of this in lowercase. So we have this example here, race a car with 1 comma. It contains alphanumeric characters and also non-alphanumeric characters. So we need a couple of helper functions, right? Clean string, which is going to be a helper function. And what this helper function is going to do is it's going to remove uppercase, so convert to lowercase, and remove non-alphanumeric values. That's all this is going to do. It's going to clean up the string. Then we need to check if the string is a palindrome, so we can create a function for that. And the way we do that is we just compare the left side to the right side. So at the end of this, it's going to give us this as a result. Now we need to check if it's a palindrome. If we start at either side and we work our way in, so we have a 2-pointer technique, and we check if this value here is the same as this value, which is not, so we can return false. But if it was, what we do is we'd increment inwards. So left pointer would move here, right pointer would move there, until there is no space left, and then we can just return true. So time complexity for this really does depend on how you implement both of these helper functions. So we'll discuss this in the code. So to start off with, we need a helper function, and we're going to call it cleanup, and we're going to pass this into a variable called clean string. And what this helper function is going to do is it's going to convert our string into lowercase and remove non-alphanumeric values. So let's write out that function. So cleanup takes in string. So the way we remove all non-alphanumeric values is we store all alphanumeric values within a variable. So let's do that. And what we're going to do is we're going to loop over this string that we've passed in, and we're going to check to see whether the value within string is found within the character above. And if it's not, we remove it. If it is, we add it to a new string variable. Okay, so we're going to loop through the string. We're going to convert it to lowercase first. So this is the important part. So we're going to look in character, and we're going to check if we can find the index of L case. And if that is not equal to -1, we know for a fact that it is an alphanumeric value, so we can just add it to the string. So what this is doing here is it's looking within character, it's looking to find the index of this value. And if it doesn't find it, aka it's equal to -1, then it's a non-alphanumeric value. So if it's not equal to -1, then it's found within here. And then we can return new string. Next, we need to create another helper function, and this is to check whether it's a palindrome. So we're going to pass in the clean string we just created, and we need to create that helper function. So is pal takes in the string. Now with a palindrome, we just want to check to see whether the left is the same as the right. So for example, ABA is a palindrome because firstly we check the left against the right, and then we move inwards. ABA is also a valid palindrome because we check the left, the right, they're both the same. Then we move inwards, we check the left and the right, they're both the same. Now if we had C in there, we check the left and right, they're the same. Then we move inwards, B and C are not the same, so it's not a valid palindrome. So let's utilize the 2-pointer technique. So left is equal to 0, right is equal to string.length -1, and while left is less than right, we can check if string at left does not equal string at right. So if they're not the same, it's not a palindrome, so we just return false. And then we need to increment and decrement both sides respectively. Otherwise we'll enter into an infinite loop. And once we pop out of this loop, if a false has not been returned, we can just return true because we know it's a valid palindrome. Okay, and then finally, we need to return this value up here. And that will return true or false. So let's give this a go. Okay, so it's been accepted, let's submit it. And there you have it. So in terms of time and space complexity with this particular solution, time complexity is O(n + m) because we've got one for loop within the cleanup, which will loop through the entire string that is being passed in. And we also have a 2-pointer technique here using a while loop. So it's going to be O(n + m) for time. And then with regards to space complexity, the only thing we need to consider is this function here for space. We have characters here which is constant because this is the same no matter what string is being passed in. However, we do create a new string here, and this could potentially be, in worst case scenarios, the same length as the string passed in. So space in this case is O of n. So given a string S, return the longest palindromic substring in S. So in example 1, we have BA, BAD, and the output is BAB. So a palindrome reads the same forward as it does backwards, and we need to find the longest palindromic substring within the string S. So here the output is BAB, or it can be ABA. Those two are valid palindromes, and we need to return the substring. Within example 2, we have CBBD, we have BB, which reads the same forwards as backwards, so it is a palindrome, and we just return that answer. So a great way of solving a problem that concerns palindromes is to expand from the center. So we're going to have an isPal helper function, which checks if something is a palindrome. And what I mean by expanding from the center, say we have B as our initial position. We check if that's a palindrome. So B on its own reads the same forwards as it does backwards, so that's a palindrome. Then we expand outwards. So we have a left and right pointer here. We expand outwards. Left goes here, right goes here. We check if this is a palindrome. So A is equal to A. It is a palindrome. So we expand outwards again. Left becomes B, right becomes D. These aren't equal, so this is no longer a palindrome. So we can forget that. So that's how we're going to check for palindromes. But the difficult part of this question is we need to find the longest palindromic substring within this sequence. So we need to check, say, if this is the palindrome, if that's the longest palindrome, this is a palindrome, if that's the longest palindrome, if this is a palindrome. So we're going to check for all possible solutions, right? And update a variable, say longest, which will start off initially as an empty string, update that to the longest palindromic substring that we find within this string. So let's run through the example. So as we said, we're going to be expanding from the center. So if we start off at B, we're going to have a left and right pointer here. We check if this is a palindrome. It is a palindrome. So we expand outwards. So we go left and right. So left goes there, right goes there. Left is out of bounds now. So we'll have to add that into the conditional logic of isPal, and we can move along this sequence. So we're now at A. We have the left and right pointer. A is a palindrome, so we expand outwards. So let's start off at B. We have the left and right pointer here. This is a palindrome, so we expand outwards. So left goes here, right goes here. Left is now out of bounds, so we check against the longest string. So B is currently the longest string, so we can add that in there. Now we move along. We start off at A, left and right pointer. That is a palindrome. Great. So we can expand outwards. Left and right. Is B equal to B? Yes, it is. That's also a palindrome. Great. Let's expand outwards. The left pointer is now out of bounds. So we can check to see whether this palindrome, BAB, is greater than this. So it is. So we update the longest to equal BAB, and then we move along in the substring. So we move to B. That is a palindrome. So we expand outwards. A and A both equal. So that's a palindrome. So we expand outwards. B and D are not equal to each other, so that's not a palindrome. So we look at this value here, ABA, we compare it to the longest length. They're both equal, so there's no need to update this. We move along to A is a palindrome, we expand outwards. B is not equal to D, so that's not a palindrome. A's length is not greater than the longest here, so it's not greater than BAB. So we can move along. So at D is a palindrome, we expand outwards. Right is out of bounds. D is not greater than BAB. So we exit this. So this is the solution to this example. Now let's have a look at the other example. So let's say we have, so let's check the first one. So here's a palindrome, we expand outwards. That is out of bounds. So we can update the longest palindromic substring to equal C. With the solution we used to the previous problem, we check B. B is a palindrome, we expand outwards. C and B, they're not equal, so that's not a palindrome. And that is equal to the length of the longest string, so we don't need to update that. We move over to B. B is a palindrome. We compare B and D. They are not palindromes, so we don't need to update the longest. We go to D. D is a palindrome, so we compare B and a value that's out of bounds, so we don't need to do anything here. So at this moment in time, the longest is currently C. And if you look in the string, that is inherently wrong because we have B and B here. And the reason for this is that our current solution, when we check for the palindrome, we are only checking odd length strings. So say when we check B, we check string of length 1. And then if we expand outwards, we check string of length 3. And then if we expand outwards again, if it was in bounds, we'd be checking a string of length 5. So we also need to run an extra isPal for even length strings. So for example, rather than having the left pointer and the right pointer just on one string, we'll have the left pointer here and the right pointer here. So we can check if this is a palindrome. No, it's not. So what do? We move along. So we move a left and right pointer. Left and right pointer is now situated here.
B. B is a palindrome. So we check if that's the longest. If that's greater than the longest length, it is. So we update the longest to be BB. Then we move along, check if BD is a palindrome. It's not. So then we can exit this. So time complexity for this algorithm is ON squared. We have a quadratic time complexity because we're looping through the string twice, one to compare odd length strings and one to compare even length strings. And space complexity is O of 1. Even though we update the longest and we have space allocated here, this is used in the output, so it is not included within space complexity. Okay, so let's write this out. So we're going to need the longest variable as an empty string. We're going to have a helper function called isPal to check for palindromes. We're going to pass in the string, left and right pointer. We're going to have a while loop. So while left is inbound, so if it's greater than or equal to 0, and right is less than string.length, so right is also inbound. We also need to check whether s at left is equal to s at right. So if those two values are the same, then we know we have a palindrome. So we expand outwards. So left minus minus, right plus plus. Once we exit this while loop, we know that any further strings are not going to be palindromes. So what we can return is the string sliced from left plus 1, because we don't want to include the current left value, and right. And the reason it's not right plus 1 is because the slice method here is non-inclusive. So it doesn't include the current right value. So it goes up to the right value, but doesn't include it. Then we need to loop through the string. Run isPal for odd length strings, and run isPal for even length strings. Store these in variables. So we could have first pal. Actually, what we'll do is we'll call it odd pal, even pal. And now we can work out the longest palindrome between the odd pal and the even pal. So the longest pal is equal to odd pal dot length. So if the odd pal dot length is greater than even pal dot length, then we return odd pal, or we return even pal. Now we can check against the longest variable we set at the top on line 7. So if longest pal dot length is greater than longest dot length, we can update longest to longest pal. Finally, we can return longest, and then let's give this a go. Okay, so that's been accepted. Let's submit it.
So given a string S, return the number of palindromic substrings in it. A string is a palindrome when it reads the same backwards as forwards. A string is a palindrome when it reads the same backwards as forward. A substring is a contiguous sequence of characters within the string. So within the string we have A, B, C. We have 3 palindromes. So we have one that's equal to A, B, and C. In the second example, we have a string of 3 A's, and the output is 6, so we have 6 palindromes. 3 single A's, 2 double A's, and 1 treble A. So let's discuss a potential solution for this. So just to visualize what this question is asking for, we need to loop through the entire string to see whether all the substrings within it are palindromes. So we need to look at this value, we need to look at these values, we need to look at this value, and then we also need to do the same for B. So look at B by itself, then BC, and then do the same for C. So we could have a brute force approach with multiple for loops that compares exactly that. So it compares this one with this one with this one, then it goes across and compares this one with this one, etc. But we have a solution which has a better time complexity, right? And that is if we start at one position and then we expand outwards. So let's say we started at this position, position A. We check to see if it's a palindrome. So we'll have some kind of function called isPal, which will take in a string or positions within the string. So it will take in left and right pointer, and then it will just check whether it's a palindrome or not. So we can clearly see that A is a palindrome because it reads the same forwards as it does backwards. So we'll have a count variable, which will be equal to 1. And then we need to expand outwards. So right now, this string is out of bounds. Okay, so we're expanding this way. So this is less than 0. So we need to add that into the conditional logic. So if it's less than 0, then cancel out of this loop and then move along. So we've covered A, move on to B. At B, this is a palindrome. So we can increment count to 2, expand outwards. So expand outwards. We're now at point A and point C. Are these two, is this compared with this, a palindrome? Well, they're not the same, so we can cancel out of this loop now. And lastly, we reach C. Check if it's a palindrome. It is a palindrome. So we increment count to 3, expand outwards. Now this is out of bounds because the right side is greater than string.length minus 1, which is this value. So we can escape this. So let's run through the second example. Just to solidify this solution, we have A as our first point. So we have the left and right pointer both pointing to the value of A. Is this a palindrome? Yes, it is. So we increment count. Then we move the one pointer to the left and the one to the right. So we're now pointing to an index that is minus 1, so it's out of bounds, and we're also pointing to this value. So this is out of bounds now, so we can move along. So upon reaching the second A, we can check, is that a palindrome? Yes, it is, so we can increment count, and then we can expand our left and right pointer. So left goes here, right goes here. Now we check, is this a palindrome? So is the string at the left pointer equal to the string at the right pointer? Yes, it is. So we increment count again, and then we expand outwards, and now we're out of bounds. So we move along. So at the last A now, is this a palindrome? Yes, it is. So we increment count, we expand outwards. So left pointer, right pointer. The right pointer is out of bounds, so we escape that. Now, the issue we have here is that in the question, the answer for treble A is equal to 6, but we have only got 4, and here is why. So say we started at this pointer. So we have one value within our substring. That's this value. When we expand outwards, we now have 3 values within our substring. If we expanded out again, we'd have 5 values within our substring. So we essentially miss comparing these two and also comparing these two. So we miss all even substrings. So what we need to do, rather than just picking one to begin with, so say we have treble A, rather than just picking one as the starting point, we also need to do another run of this function that we're going to create, but have the pointers pointing to 2 strings. So we include the even length substrings. So this one will look at these two. It will check to see whether they're a palindrome. They are a palindrome. So it'll increase the count to 5. Move outwards. We're out of bounds on the left side. So we move along. We now compare this one and this one. Are these palindrome? They are indeed. So we increment count again, and then we expand outwards. The right side is out of bound. So we can exit this, and then we return 6. Time complexity for this algorithm, well, we have a string here, so we have to loop through n times, so that's going to be n, and then we need to expand on every string, which is also going to be n operations as well, so it's going to be n squared. And we need to do this for both odd and even substrings. So that'll be O n squared plus n squared, which again simplifies to O n squared. And then space complexity is going to be O of 1. Simply because we aren't allocating any extra space here. So let's write this out. So let's declare count and set it at 0. Let's loop through the string. And just to make this a bit easier to read, let's set left equal to I and right also equal to I. So these are the left and right pointers that we're going to be throwing into our helper function. And our helper function is going to be called helper because I'm really imaginative. We pass in left and right for the odd palindromes. So this is odd. And then we also call the helper function again. We pass in left and right plus 1 for the even values. Then we can define the helper function. So let's create that now. Pass in left and right as parameters. And then here we need to create that palindromic condition. So it's going to be a while loop, right? Because we're going to have to loop through this substring. We need to state that left needs to be greater than or equal to 0, so it needs to be inbound. Right is less than or equal to s.length minus 1, so right needs to be inbound on the right side. And s at left needs to be equal to s at right, so it needs to be a palindrome. If that is the case, and all of that is passed, we can increment count. We can decrement left because we're expanding outwards from the center, and we can increment right. And finally, we can return count. So let's just run this and see if it's worked. Okay, let's submit it.
So design an algorithm to encode a list of strings to a string. The encoded string is then sent over the network and is decoded back to the original list of the strings. Machine 1 sender has the function and returns the encoded string, and then machine 2, the receiver, will be returning strings as an array of strings. So string 2 in machine 2 should be the same as strings in machine 1. Implement the encode and decode methods. You're not allowed to solve the problem using any serialized methods, such as eval. Okay, so the examples, pretty much we have some dummy data, and it's going to be outputting the exact same results. Okay, so the input is going to be the exact same as the output here, but it's just encoding and decoding that we need to worry about. So we have strings, which is equal to an array of strings, and we need to somehow encode them into a string that decode can then use to convert back into a list of arrays. So two separate sections of this. There's encode. Now, how do we usually convert an array of strings into strings? Well, we just join them, right? So we could say strings.join, and we could join by, let's say, encode string. So that will encode it. That will convert this array into just one string that is concatenated. So hello will be concatenated with world by encode string. So it'll look something like this. We need to take into consideration that strings could be equal to null. So if strings.length is equal to null, then we just return null, okay? Because we always need to return something in order for it to be decoded. And then within decode, we need to check if the string being passed in is equal to null, which we created up here in encode. So remember, if there's nothing within strings, return null. In here, it takes it in. We check to see if it's null. If it is, we return null. We return an empty array. And in order to convert this right here back into an array of strings, so we want to convert it back into that, we just do strings.split, and we split by encode string. Okay, so let's write this out. So if strings.length is null, then we return null. We have to return something here. Otherwise, we can return strings.join, and we can join by encode strings. As long as you make sure the value here that you're concatenating the strings by is unique, then you'll be fine. Now, this will be passed into the decode function. So we need to check if s is equal to null, because up here we could potentially return a case where it's equal to null. So we need to account for that. We can return back an empty array. Otherwise, split the string at encode string. And that is it. So let's run this, see if it's worked. Okay, let's submit it. So given the head of a singly linked list, reverse the list and return the reversed list. So we have 1 through to 5, and we need to reverse that list. So it's 5 through to 1. So pretty straightforward question. So this is another good introductory question to linked lists. So let's define first what a linked list is. So a linked list is a linear data structure where there is a value and a next pointer or a next reference that points to the next value. So 1 points to 2, 2 points to 3. And the great thing about this is that it can be stored sequentially within space. So it improves on space complexity compared to a bog standard array data structure, because an array is stored as a contiguous block in memory. It means that it's very fast for lookup, but in order to store it in space, it needs that contiguous block of space, whereas a linked list doesn't. Now, before answering this question, it's really good to be able to visualize what it's going to look like. So with this, we're going to have value is equal to 1. We're going to have the next pointer, and this pointer is going to be pointing to 2. So it's going to be pointing to the value of 2, which also has a next pointer. And this is going to be pointing to the value of 3, which has a next pointer that is pointing to null. So with this linked list here, what do we know? We know for a fact that the head is set at 1. We know that the next node is going to be 2. And in order to solve this problem and reverse the linked list, we are going to have to create some kind of previous value. The previous value is going to be here. And this is going to be initially set to null, because what we're going to do is make sure that this is the end of this new linked list we're creating. So we're reversing the list by reversing it so that this is the end. So we need to reverse it. So this pointer right here needs to point to the previous node. So if we do that, we point it here. But then we've broken the linked list and we don't have a reference to the next value now, or the next node. So before we point this to the previous node, we need to create a new reference. So we can say these quotations means reference. So we've created this reference here. so that we can use it in the future to reverse this linked list. Now we can reverse that point. So this next pointer now points to previous, and now we need to update previous, head, and next. And in order to do that, previous moves to head, head moves to next, and then obviously next will go here. And we're able to move head to here because we created that reference node before. And then we can just repeat this process. So we need to create that reference node here. We need to change this pointer so it's pointing to the previous value, and then we need to update previous, head, and next. So previous moves along, head moves along, and next moves along. Previous, head, next. And again, we were able to move head because of this reference node we created. Repeat the process, create a reference, change the pointer, so have it pointing this way. Let's remove that pointer, and then let's update prev, head, and next. So prev moves here, head moves here, and then next is over here. And now head is out of bounds, so head is equal to null, so we can return prev, and this is the linked list reversed. So time complexity for this one is O(n), because we're traversing this linked list once. Space complexity is O1. Okay, so let's start this off by initializing prev to null. So we need to create that previous node. While head is available, we create that reference node that we can eventually set head to. That's going to be equal to head.next. Then we change the pointer of head. So head.next is now equal to prev. So we flip that pointer. Now we need to update prev, head, and the next node will eventually be updated in the next loop. So prev equals head, and head is equal to next node. So when head is equal to null, we're going to hop out of this while loop, and then as we showed in the solution, we need to return prev, and that will be the linked list reversed. Let's give this a run. Let's submit it.
Given head, the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, POS is used to denote the index of the node that tail's next pointer is connected to. Note that POS is not passed as a parameter. Return true if there is a cycle in the linked list, otherwise return false. Firstly, it would be a good idea to discuss what a linked list is. So a linked list is a linear data structure with each element in the linked list being a separate object linked together by a reference field, and that reference field is the next pointer. And the benefit of this is it can be stored sequentially within space, so it reduces the space complexity. Whereas you've got an array, for example, which is stored as a contiguous block in memory. So it means that you can look up any value within that array very fast because it's stored in a contiguous block. So let's just look at this example. So the first example, we've got 3, 2, 0, 4, and then 4's next pointer is pointing back to 2. So there is a cycle here. So we need to determine whether that cycle really exists. So how do we do that? Well, we've got a next pointer, which is pointing, and then 4 is pointing back to 2. The way we could do this is we could use an algorithm known as the tortoise and hare algorithm, or we could just denote it as fast and slow pointer. So let's say we started at the beginning. We have a fast and a slow pointer. Now, if there's a cycle and the fast pointer is jumping 2 at a time and the slow pointer is only jumping 1 at a time, at some point in the future, fast and slow are going to reach the same point. So a nice analogy for this is, say we have a track. We have 2 runners. We have slow runner and we have fast runner. The fast runner is going to run twice as fast as the slow runner. So say the fast runner runs an entire lap. The slow runner is only going to run half a lap. So this is the outcome after the first lap that the fast runner runs. Now, next lap of the fast runner is going to end up like this. So the slow runner and the fast runner have met up again. And that is exactly what we're trying to implement here. So with the fast pointer and the slow pointer, as we said, the fast pointer is going to go twice as fast. So after the first jump, fast pointer is going to be here. Slow pointer is going to be here. After the second jump, fast pointer is going to be here, and slow pointer is going to be here. And after the third jump, fast pointer is going to be here, and slow pointer is going to be here. So they've met up again. So time complexity for this algorithm is going to be O of n. That is in the case of both if there is a cycle and if there isn't a cycle. So if there isn't a cycle, we're just going to be looping through this entire linked list once. If there is a cycle, we're going to be looping through it a number of iterations. So the time complexity is essentially O(n) plus k, which simplifies to O(n), and space is O1 complexity. So first things first, if head is undefined, we just want to return false. Let's cover that edge case. Then we need to declare the fast and the slow variables, and we're going to make sure that they're equal to the head. And then while fast is available, or while fast is true, we only need to take care of fast because the fast pointer is always going to be ahead of the slow, so we don't really need to put slow within the while loop here. If fast.next is undefined, then we return false because we've reached the end of the linked list and there is no cycle because there's nowhere else for the fast pointer to go. Else, if we haven't reached the end, we increment fast and we make sure that it increments by 2 jumps, and we increment slow and make sure that slow increments by 1. And remember, we're using slow here, which we've set as head as a reference to head, and fast here as a reference to head as well. We're not changing head at all. And then if fast is equal to slow at some point in the future, we return true because that states that we have a linked list cycle. And then we can return false if we get nothing back from that. And finally, we can submit this. So let's run this code, see if it's worked. Okay, so it looks like it's worked. So you're given the heads of 2 sorted linked lists, list 1 and list 2. Merge the 2 lists in one sorted list. The list should be made by splicing together the nodes of the first 2 lists. Return the head of the merge linked list. So we can't create a copy of these lists. We have to merge the 2 together. So in the first example, we have list 1 and list 2 as the input arrays, and we have merged them together in ascending order. Okay, so for this question, we are going to be merging the 2 together, and we need to keep the original kind of nodes within this new list that we're creating. So in order to create a new list, we need to initialize a dummy value. So this dummy, it doesn't matter what value it is. It could be any arbitrary value. So we've initialized dummy. We're going to set head to equal dummy. Now this is important because at the end we're going to be returning head. We're going to be using this as a reference. So now we can start the loop. So we need to loop through both of these. So we need to loop through and compare both of these values. So let's start off by comparing 1 and 1. They're both the same, so it doesn't really matter which one we choose. Remember, this is L1, this is L2. Let's just say we choose L1. So we set the next node of dummy to equal L1, which is 1. And then we update L1 to L1.next. So we move that one over here. We've covered this, so we don't need to look at that section anymore. We repeat the process. So 1 is smaller than 2, so we use L2's current value, which is 1. And we set L2 to its next value. So we can remove this from the search criteria. Now we compare 2 and 3. So we update L1 to here. Remember, we're updating dummy to dummy.next down here. We compare 3 and 3. Let's say we take L1 again. So we have 3 here. We've checked this, so we can remove it from the search criteria. Now L1 is pointing to null. So we've reached the end of one of the lists. So there are no more comparisons between the 2. So there is one more operation we need to carry out, and that is we need to add the end of L2, or what's left in L2, to the end of dummy. Okay, so we created H, or we created head as a reference. So all we need to do now is return head.next. So now we can move on to time and space complexity. Time complexity for this algorithm is O(n) plus m, where n is the length of L1 and m is the length of N2, and space complexity is O of 1. So let's start this off by creating that dummy node. So we can initialize it to any arbitrary value. Let's create head, which we're going to use as a reference, and set it to dummy. Now we can create the while loop. While list 1 does not equal null and list 2 does not equal null, we can check if list 1, if its value is less than or equal to list 2. If it is, then we set dummy.next to equal list 1, and then update list 1 to its next value. Else we can do the same
but for list 2. Remember to update dummy to its next value so we can add on to the tail of dummy. Now outside this while loop, one of the lists is going to be equal to null. So all we need to do is append to dummy the rest of the list that is not equal to null. So if list 1 does not equal null, dummy.next is equal to list 1. Else we'll set dummy.next to list 2. And then we can return head.next because we used head as that reference at the start. Let's run it. Okay, let's submit it. So you're given an array of k linked lists called lists. Each linked list is sorted in ascending order. Merge all the linked lists into one sorted linked list and return it. So in the example, we have an array of arrays containing a number of lists, and we just want to have an output that merges all of those lists together in ascending order. Okay, so the idea behind this question is pretty straightforward. The implementation, however, is a bit more tricky. So there are a number of ways you can do this, and they all kind of revolve around the same kind of time complexity. We have a brute force approach where we just create an array from these lists, and then we use a rudimental sorting algorithm and populate a new sorted list, which will give time complexity of n log n. Or we could use a merge sort, which is what we're going to be doing today. So a merge sort is a divide and conquer sorting algorithm. I'll add a link to the merge sort. And what this does, rather than creating an entire list and sorting that individual list, we're going to merge two of these lists. So say we merge these two, which is given to one list. And then with this list, what we're going to do is we're going to merge it with this one, which is going to give us the final list, which we can return as the output. So this with this will give us, and then this compared with this. So there are two parts to this question. Firstly, we need a function which is going to grab these two lists and merge them. And then we're going to have another function which is actually going to carry out the merging. So the time complexity for this one, if you know, merge sort is going to be on log k. So with the operations of the merging, we're dividing by 2 roughly each time, and there's going to be n operations. So there's not much to this explanation, but if we dive into the code, I'll show you how it's implemented and it will become a lot more clearer. So firstly, we need to say if the length of lists is equal to 0, return null, because there's no lists to be merged. And while the list's length is greater than 1, we have two lists that we can merge. So we need to grab both of those. So that list1 equal lists.shift. So we can just grab the first one. And also we need to grab a second one. Now we need to merge these two lists. So we're going to create a separate function for that. We're going to pass in list1 and list2. And then we need to add into the lists the merged value. So we update the list. We've subtracted two lists from the current list. We've merged them. And then we need to update the list with that merged list. And then because it's going to be an array of arrays, we need to return lists at 0. So this is the merge sort. Now we actually need to create the merge list function. So if you want an in-depth discussion on how merge list is implemented, I'll leave a link in the description to the video where I discuss that. But for now, I'm just going to run through it very quickly. So we create a dummy node, which can be initialized to any old value. We create a head, which is used as a reference and it will be set to dummy. Then we start the while loop and compare the two lists. So while list1 and list2 are not equal to null, if list1's value is less than or equal to list2's value, we're going to set the next value of dummy, the next property of dummy, to equal list1. We need to move list1 to its next value. Else, we do the same, but for list2. And then we also need to update dummy to dummy.next, because we need to add the next value from one of these lists to the tail of dummy. And then outside of this while loop, we've reached the endpoint of one of the lists, so one of the lists is equal to null. So what we need to do now is we need to append to dummy the rest of the list that is not equal to null. So if list1 is equal to null, dummy.next is equal to list2. Else dummy.next will be equal to list1. And then finally we can return head.next, so the reference that we created at the start. Let's give that a run. Dummy is not defined. Okay, so there's a spell mistake. Let's run it again. Let's submit it. So given the head of a linked list, remove the env node from the end of the list and return its head. So the understanding of this question is pretty straightforward. We have in the first example n is equal to 2, so it's 2 back from the end, and we need to remove that value in order to get this new list and return that as the output. Okay, so first thing, we need to decide how we are going to delete the node. And rather than thinking about it in a way of actually removing this node, what we need to think about is reassigning the next pointer of the previous value to exclude the for node. And that is how we will delete this. So that's the easy part. So how do we get the previous value? Well, in order to do that as efficiently as possible, we could utilize the two-pointer technique. And with most questions concerning linked lists, we need to create some kind of dummy component that is pointing to head. So let's say we have dummy here, which is pointing to head. Okay, this node here can be initialized to any value. It doesn't really matter. It can be initialized to an arbitrary value. But this is where the left pointer is going to reside initially, and this is where the right pointer is going to be. Now we need to move the right pointer across by n nodes. So if we move the right pointer here, n is going to be equal to 1. We move it along here, n is going to be equal to 0. So we've moved it n times. So that's the initial step. So the gap between the left and right pointer is of n nodes. And now we need to increment both the left and right pointer until the right pointer is residing at null. So left pointer moves here, right pointer moves here, left pointer moves here, right pointer moves here, left pointer moves here, right pointer moves here. So now that the left pointer is at the previous value, all we need to do is reassign left.next to left.next.next to exclude the node that we want to delete. And finally, what we need to return is we need to return dummy.next. Now this is a really important aspect of it. So say in the example, we have just one, and that is pointing to null. So this is the head. We carry out this logic that we just created. So dummy is pointing to head. We have removed it with the left and right pointer. So rather than pointing to head, dummy is pointing to the next node now. If we returned head here, we are going to get 1 as the result. So that's going to error out. So we need to return dummy.next because we've reassigned dummy.next from head to the null value. So rather than getting 1, we are going to get an empty array. So very important, when you create that node, always return dummy.next and not head. So time on this one is going to be of n operation. So n is the length of this linked list. Space is going to be of 1. So let's start off the solution by creating the dummy node, and we will set that to a new list node at 0. Let's set dummy.next to equal head, and then let's set the left pointer to equal dummy and the right pointer to equal head. So we need to move the right pointer across the linked list until it's n nodes apart from the left pointer. So while right and n is greater than 0, we can increment right and we can decrement n. Once we've done that, all we need to do is move both the left and right pointer until the right pointer is at null, so it's at the end of the linked list. So while right will increment left and we'll increment right. So now the left pointer is at the previous value, the right is at null. We need to skip the node we want to delete, so we set left.next equal to left.next.next, and then we return dummy.next. Okay, let's see if that's worked. All right, let's submit it. So you're given the head of a singly linked list. Those can be represented as L0 all the way up to Ln, and we need to reorder the list in the following form. So L0 points to Ln, points to L1, points to Ln minus 1, L2, Ln minus 2. Right, so let's not waste any time and dive straight into the walkthrough. So we have this linked list here, right? L0, L1, Ln minus 2, Ln minus 1, and Ln. And we need to create this result, right? So somehow we need to break this so that L0 points to Ln, Ln points to L1, L1 points to Ln minus 1, and Ln minus 1 points to Ln minus 2. So firstly, I'll give you a high-level overview of how we're going to solve this. We need to split this into two, right? We need to split at the middle. So this is an odd length linked list, so we're going to take 1, 2, and 3 for the left linked list, and then we're going to have 4 and 5 on the right linked list. We're going to break this connection. We're going to reverse these two, so 5 is going to point to 4, and this is going to point to null, and then we're going to have this linked list on the left-hand side, right? So we have two separate linked lists. Then we combine these two, right, to give us this solution. So that's the high-level overview of what we're going to do. So firstly, we need to work out the midpoint within this linked list. And how can we do that? Well, there are a number of different approaches to resolving this, but we're going to use a fast and slow pointer, also known as the tortoise and hare algorithm. So the fast pointer is going to move twice as fast as the slow pointer. So after the first iteration, fast will be here, slow will be here. Then the second iteration, fast will be here, and slow will be here. Now we can say as long as fast.next and fast.next.next are available, then we keep on searching for the midpoint. But as you can see, fast.next is pointing to null, so we have the midpoint, which is slow. So here we can create a reference to this. We'll just call this current, right? Because what we're going to do is we're going to break this. So we need to create a reference so that we can always get to this value within the linked list. So we're going to break this, and this value is now going to point to null. So we've broken the list up into two linked lists. Now we need to reverse this linked list. And if you want an in-depth discussion on how to reverse a linked list, I definitely check out my video on LeetCode question 206, reverse a linked list. But essentially in order to reverse this, we're going to have 4 pointing to 5 pointing to null. We have current value here. We're going to create a previous value, which we're going to set to null. We want to break this point and have it pointing over to this null. But in order to do that, we need to create a temporary variable to 5 so that we can access this once we've broken this. Let's break this. Let's point this to null. Then we update the previous, the current, and the temp points, right? So previous moves to current, current moves to temp. And then we repeat that process. So we want to break this point and move it here, but we need to create the temp. We break the point, and then we update the pointers. So previous moves to current, current moves to temp, and now we're at a point where current is equal to null. So we've reached the end of reversing this linked list. So now we have these two linked lists. All we need to do is combine them in order to get this output. And we're going to be using pointers throughout this in order to do that. So we're going to have a h1 pointer pointing to the head of this linked list and a h2 pointer pointing to the head of this linked list. Now, as you can see in the results, the 1 from h1 is pointing to the value from h2. So we want to break this and have it point to h2. But in order to do that, we need to create a temp variable on 2 so that we have access to this. So let's go ahead, break that and make the connection. So 1 points to 5, so h1 points to h2. Now we update these pointers. h1 becomes h2, h2 becomes temp. h1, h2. And then we repeat the process. So we create a temp variable at h1.next. So this is going to be here because we are going to be breaking the connection. 5 points to 2, right? So we need to break this. 5 then points to 2. Great. Then we update these points. So h1 moves to h2, h2 moves to temp. So the next step is to break this point, right? And we want h1 pointing to h2. So we create the temp here. We break this connection and we make a new connection between h1 and h2. And then we update the points. So h1 moves to h2, h2 moves to temp. Okay, so the final step here, we want to break this point here. So we'll create a temp here, we'll break that point, and then we'll point 4 to 3.
And then we'll update H1, H2, and temp. So H1 moves to H2, and H2 moves to temp. Now, as you can see, H2 is at null, so we can exit this. If we have a look at where these are pointing, well, 1 is pointing to 5, 5 is pointing to 2, 2 is pointing to 4, and 4 is pointing to 3, which is ultimately pointing to null. And as you can see, that is the answer we're looking for. So this solution that we just calculated is running at O(n), and space is going to be O1 for this. So let's start off by finding the mid. We're going to have a slow and fast pointer, so slow is going to equal head, fast is also going to equal head. And then while fast.next and fast.next.next are available, we're going to update those pointers. So slow equals slow.next and fast equals fast.next.next. Once this is run, the slow will be at the middle. So now we can break this linked list. So firstly, we need to create a pointer so that current equal slow.next, and then we can say slow.next is equal to null. Now we need to reverse the second linked list. So let's create prev, which is equal to null, and then whilst current is available, we'll create the temp, which is equal to current.next. Current.next is equal to prev. Prev is equal to current, and current is equal to temp. Then the final step is to combine these lists. So we're going to have a H1, which is pointing to the head, so the first linked list, and then H2 is going to point to prev, right? And up here, we created prev, we ran through reversing the second linked list, so prev is now going to be pointing to the start of the second linked list. And then like we said in the walkthrough, whilst H2 is available, we need to create a temp variable so that we don't lose the next position of H1. H1.next is going to equal H2, H1 equals H2, and H2 equals temp. So first we find the middle, we break the linked list, we reverse the second list, and then we combine the lists together, and this should run. So let's give it a go. Submit it. So given an n by n integer matrix, if an element is 0, set its entire row and column to zeros. You must do this in place. So it's a pretty self-explanatory question. We just need to set the rows to zeros and the columns to zeros where we have a 0. And we must do this in place. So initially you may just think to loop through this entire matrix, and when you find a 0, update its row and columns. So let's try that now. So if we go across, we find no zeros. When we get to this point, we find a 0. So let's say we update its row and update its column. Then we carry on. Oh, we've got a 0 here. Let's update the column. Then we move along. We find this one. We update the row. And that is not going to be the right answer, right? So as you can see, that would error out. So a solution to this, by doing it in place, what we could do is we could store the position of the row and the position of the column of this 0 in an auxiliary data structure. So we could store it in an array, right? So we could call it 0 position, and then we could store it as 1, 1. So every position we find within this matrix that is equal to 0, we store its row and column within this array. Okay, so we haven't mutated it. And then once we've done that, we can loop through 0 positions. So there'll be multiple in here. If there's multiple zeros within the matrix, we can loop through this, and then we can just update the rows and columns that way. That way we won't be mutating the array and then searching for further zeros. We've already found the zeros. So now all we need to do is we need to update the rows and columns. So we're going to loop through the rows. So we're going to loop through here, here, and here. And where row is equal to 1, we're just going to update all values within it. And then we'll do the same for columns, loop through that. And then where columns is equal to 1, we're just going to update all the values there. And that will give us the result we want. So time complexity for this algorithm is OM times N. Because we're going to be looping through at maximum, say 3 times, we're going to be looping through the matrix entirely once to begin with to find all the zeros, or to find the positions of all the zeros. And then we're going to be looping through the rows and the columns afterwards to update the matrix with zeros. And we're going to do that all in place. So space complexity is O n plus m, because we're going to be storing positions of zeros within the zero position array. And in the worst case scenario, all of these values could be zero. So our initial kind of zeros position array would have each position within there. So it's going to be on plus m. So let's code this out. So let's declare zero position as an array. Let's loop through the matrix and find all the zeros. So we're looping through the entire matrix here. If the matrix at ij is equal to 0, then we can push into 0's position. The position of the row and the position of the column. Once we found all the positions, we can then loop through 0 positions. Extract the row and column. And then we can loop through the rows. So I is less than matrix dot length I plus plus. We can update where the column is equal to 1, because here we know for a fact that 0 index here, the row and column is going to be set to 1. So here it's going to be 1, 1. So we're going to be looping through the matrix rows, and where column is equal to 1, we're going to update that to 0. And then we're going to do the same for the columns, so that I equals 0, I is less than matrix at 0 dot length, I plus plus. And then we have matrix row I is equal to 0. So where the row is equal to 1, and then we're looping through the columns, we'll update that to 0. Okay, so that's looking good. Let's run it. Let's submit it. So given an m by n matrix, return all elements of the matrix in spiral order. So we have matrix 1 through 9, and we need to return 1, 2, 3, 6, 9, 8, 7, 4, and 5. It's quite a simple question to understand, but it's pretty tricky in implementing it. So we have this matrix, right? And the first step is to loop through the first row, so row 0, and add to a result array. So let's create that. We know we're going to be needing a result array, and that's going to store in all the values as we traverse through the entire matrix. We're also going to have to set some boundaries, right? Because we don't want to be going out of bounds here. So we don't want to be going too far past here. We don't want to be going too far down here, etc. And we need to also change the direction. So in terms of this, we need to set left, which is equal to 0, right? So we're going to start here at left equals 0. Top is also equal to 0. We're going to have right, and this is going to be equal to this value here. So it's going to be matrix.length minus 1. So 0, 1, 2. And then bottom is going to be this value down here. So bottom is also going to be 2. So we've got a few variables here which we can use to loop through this array here, go down here, here, and back up. We just need to work out how to implement that. And we also need some kind of way of making sure that we've finished this loop. So we don't enter an infinite loop. So we need an exit clause. And this exit clause is going to be when the result contains all the values within the matrix. So we need to get the size of the matrix. So the size of the matrix is going to be equal to the length of the row times the length of the column. So we've got 3 times 3, which is 9. So if result values, so if result.length is equal to 9, we can pop out of this and just return res. So let's work through the solution. So we've got this while loop on the go. So while the result, actually let's call this nums. So while the nums.length is less than the size, carry this out. So we're going to be pushing these values into the nums array. So we can add 1, 2, and 3 in there. Now once we've reached this end, we need to exclude this portion, right? So we need to exclude this from the search criteria because we only want to be searching what's down here now. So we need to increment something. So what we're going to increment here is top. So top goes to 1. So top is now here. So we've excluded this now because we've already added it into the nums array. Now we need to go from top to bottom. So from this value here down to bottom and add those to the nums array. So 6 and 9. Once we've added those, we've checked that it's inbound. We need to remove this section from the search criteria. And the way we do that is we decrement right. So right is now equal to 1. So this is our search criteria now. We don't have this anymore, and we only have this. So now we need to loop backwards. So we loop from right to left, and we add in these values. So 8 and 7. So they've been added. We exclude this area now, and we do that by saying bottom minus 1. So bottom is equal to 1. So that's gone. And then we move upwards. So we go from bottom to top, and we know that top is equal to 1, bottom is equal to 1. So we only add this value in here. So 4 is added in there. We remove that from the search criteria by saying left is equal to 1. So left equals 1. And then we just repeat the process and we add 5 in. So moving from left to right, 5 is added in there. Nums.length is now equal to size. So we can hop out of this while loop and we can just return nums. Time complexity of this algorithm is O m times n, because we visit each element in this matrix exactly once, and then space complexity is O of 1. Now you may be thinking, well, we've created this nums array, but this is included in the result. So this is what we're going to be returning. So we exclude this from space complexity. So let's start by declaring those variables. So left is equal to 0. Top is equal to 0. Right is equal to the matrix at length. And then we work out the size. So size is equal to the rows times the column. So matrix length times matrix 0.length. And then we have the nums array, which we're going to be returning at the end. So remember we said whilst the length of nums is less than the size, so the size of the matrix, carry out this logic. So for let I, so we start off at the left value. So we start off at 0. I is less than or equal to right. So we want to move up and include the last value. So it's going to go 1, 2, 3. We need to make another check whether nums at length is less than size, because at any point within any of these for loops, nums.length could equal size. So we need to make that additional check. And then we push into the nums array matrix, and we're going to push in the top value and I. So when we loop through the top, the only thing we're changing is the column, and that is this value here. We aren't changing this value, so the top is set at 0, so we just keep that static, and then we change the column value. Once we've done that, we need to exclude this section from the search criteria because we've already added it into the nums array. So we increment top. Then we carry out another for loop. So I is equal to top because we're moving from top down. I is less than or equal to bottom. And we need to make that check again. So nums.length is less than size. And we're going to be incrementing downwards. So we're going to be going down the rows. So we're going to be here, going down here, then here. And what we need to push in nums, we know for a fact that the rows are going to be changing because we're going down from row to row to row, and the column is going to stay the same. So what we need to change is the row. So we change that value, and we know that right is going to be equal to 2. So we add right in there. Once we've added that into the nums array, we need to exclude this section from the search criteria. So we decrement right. Moving on to the next for loop. So I is equal to right. Because we're starting at the right side down here, we're going to be moving left. So we need to go backwards. So while I is greater than or equal to left, and make sure we do that check again, I minus minus. And what we need to push into nums. So we're changing the columns in this section. So we can put I in there. And the position we are within the rows is bottom. And then in order to exclude this section down here, we just decrement bottom.
So bottom goes from 2 to 1, and we've removed that from the search criteria. Okay, so the last loop, I is equal to bottom, and we're going to be moving up, so we're going to be moving up this way. I is greater than or equal to top, so we know top is at 1 already. We can do the check, and then we need to decrement I because we're moving backwards. And then what we can push into nums is matrix. We know that we're changing the rows, so we can add I in there, and we need to add a static value in here, and that will be left because left is set at 0 here. And then we need to exclude that from the search criteria, so we just increment left. And then we repeat the process, and once nums.length is no longer less than size, it'll hop out of this while loop, and we can return nums. Let's give this a go. Okay, so I forgot semicolon. Let's give this another go. Okay, so that's been accepted. Let's submit it. You're given an n by n 2D matrix represented in an image. Rotate the image by 90 degrees clockwise. You have to rotate the image in place, which means you have to modify the input 2D matrix directly. Do not allocate another 2D matrix and do the rotation. So in this example, we have just rotated this by 90 degrees. So 741 moves to the top, 123 moves down the side, and 369 moves across the bottom. So this is a pretty tricky question, especially if you don't know how to manipulate matrices. This is a two-step process in the solution. So firstly, we need to transpose this. And by that, I mean we need to switch the diagonals. So this one, to begin with, is going to be flipped with itself. So we've got row 0, column 0. So we're going to flip that with itself. Then we're going to move to column 1. And we want to flip that with row 1. So those two are going to flip. Then if we move to row 2, for example, we're going to flip with column 2. So those two are going to flip. 5 is going to flip with itself. 6 and 8 are going to flip together. And then 9 is going to flip. So we're going to end up with something like this. So this has been completely transposed now. So that's step 1 of this solution. Now step 2, in order to get from here to here, we're going to have to just flip these values. So we're going to reverse the first and last value and then move inwards, okay, to flip this value. And the reason I say move inwards is because if we had an example like this, we'd also have to flip these values on the inside here. So we need to flip on the outside, move inwards, flip on the inside. But because this array up here is so small, we only flip 4 with itself. Okay, so that's the general understanding of this solution. And what that will return is that will return us the answer right here. So let's jump back into the code. We'll start writing it out and then we'll come back into this and discuss how we'd actually work this out. So firstly, let's transpose the matrix. So if we loop through from I at 0, I is less than matrix.length, I++. So we're looping through the rows here. And then for the columns, we'll set that to j. We're going to make sure that j is equal to I, j is less than matrix.length, j++. Now the reason we set j equal to I is because at this point where we have I is equal to 0, I is equal to 1, 2, we want to make sure that the column, or j, is also the same. So as we went through in the example, if I is equal to 0, we want to make sure that j is equal to 0. And if I is equal to 1 down here, we want to make sure j is equal to 1 because we're going to be flipping those values. So now we can just flip those values. So temp is equal to matrix at ij. Matrix at ij is equal to matrix at ji. And then matrix at ji is equal to temp. So that's going to transpose the matrix. So that's the first step done. Next, we need to reverse elements and move inwards. So with this example, in order to reverse the first value and the last value, it's going to be matrix at ij, which is this value. And we need to get the last value. So that's going to be matrix at I, because we're at I equal to 0. And it's going to be matrix.length because it's going to be the length of this row. So matrix.length, and it's going to be -1 because the index is 1 less because we start at 0. So that will solve this problem. So that'll flip those two.
So what happens when we move inwards? Well, firstly, let's change these up. So 1 is going to be flipped with 7. So 7 and 1 are changed. Now we're in the middle. So we've got 4. So matrix ij is equal to 4, and that's going to be flipped with this matrix I matrix.length minus 1, which is currently at 1. So this isn't going to work here. So we need to decrement something else. Well, we need to decrement this by j, right? So j is equal to 1. We need to decrement by 1 in order to get that middle value. It's the same with down here. We first flip these two values. So matrix ij is equal to 5. And we want to flip it with the last value, which is 11. And j at that moment in time is equal to 0 on the first iteration, right? So those two are flipped. Then we move inwards. So we move to j is equal to 1. Now we need to flip. So matrix ij, we're flipping 1 with matrix I matrix.length minus 1 minus j. So j is equal to 1. Matrix.length minus 1 is 5. We minus 1. So we flip it with the 9. Okay? And we repeat that process. So let's write this part out. So let j equals 0. J is less than matrix dot length divide by 2, j plus plus. The reason we have matrix dot length divide by 2 is, if you think about it, if we switch these values up, so we switch 2 and 10, and then we switch 4 and 8. So we've only gone to j where j is equal to 1, right? So half the length, and we flip those values. So we flip those values, and we've only gone up to this point. If we move past this point, we're going to flip them back. So we're going to flip 4 and 8 again, and we're going to flip 10 and 2 again. So we're going to end up with what we started off at. So we don't want to do that. And we only want to go up to half the length of the matrix. Then we create the flip logic. So let temp equal matrix ij. Matrix ij is equal to matrix I matrix dot length minus 1 minus j. So once that's been added in, we can return the matrix. Let's give that a run. Okay, so that's been accepted. Let's submit it. So given an n by n grid of characters board and a string word, return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once. So in example 1, we have this board. We are looking for the word ABCCED. As you can see, this can be found within the board, so we need to return true. In the second example, we have C as the word, which is in the board. And lastly, in example 3, we have the word ABCB, which is not in the board, so we return false. So with this question, we are going to be utilizing a DFS recursive solution, because we need to check all possible solutions within this board to find if it potentially holds the word. So how would we do that? Well, we'd start off at the first position, we'd loop through this entire board, and we'd check to see whether we have this letter at the position we're on. If we do, then we can start a search. So we can start the DFS recursive call and check the next letter in word, and also traverse through this board. So we need to check all positions. So we need to go right, down, left, and up. And this would be a good idea to suggest that we need to have some kind of inbound function, or just an if statement that says if columns is less than 0, or rows is less than 0, or rows is greater than board.length, or columns is greater than board 0.length, then it's out of bounds, right? So this will be too far over this way. Rows less than 0 will be up here, column less than 0 will be over here, and row is greater than board.length will be too far down this way. So we've checked all directions to see if it's inbound. So moving from A, we can't go here because it's out of bound. We can't go here because it's out of bound. We can move either to S or B. If we move to S, S does not equal the next letter within the word that we're looking for. So we can't go down that path. We have B here. So we can start the DFS function on this, and then we repeat the process. So we check all of potential solutions, check whether they're inbound. So here we have an issue, right? Because we're going to be going back to the previous value, which we've already checked. So this has been checked. We don't need to go back to it. So in this case, we could use something like a set to store all the letters we visited, or we could simply change this to a value like a hash. Okay, so we exclude it from the board now by adding this hash. So there's no point in going back that way. So we can't go this way. We don't go this way because the next value in the word is not equal to F. So we go to C, which is the next value. B has now been seen. Okay, so we can update B with hash. We do the same with C. We check all directions. We move to the next position, which is this position. We check all positions. We move to E, repeat the process, and we move to D. Now at D, so we've checked. Now at D, so we've reached the end of word. So the position we're on, say the index, which we could keep track of, is equal to word.length minus 1. And if that is the case, we can return true. So we'll return true up the stack all the way up until we get back to the original position. So true will be returned from here, 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 and lastly here. So this will hop out of the DFS recursive call stack. We'll have true as our answer, and then we can just return that Boolean. So time complexity is O. We have to traverse the board. So we're using a recursive call stack, so that's going to be of n operations. The difficult part is in the first iteration, we can go in 4 different directions, right? But moving along, we can only choose 3 other possible directions, right? So we've got these 3. We can't go back to the previous one because we've already looked at that. So we have 3 potential solutions. So that would be 3 to the power of L, where L is the length of this word. So it is going to be of exponential time complexity. So to begin with, we can start off by creating the loop through the board and check to see whether we have the initial letter that's in word. So that r equals 0, r is less than board.length r++. So we're looping through the rows here, and then we're going to loop through the columns as well. So c is less than board0.length. And if board at rc is equal to word 0, then run this DFS function, which we're going to create, and pass in the row, the column, and 0 for the index. Now, if this returns true, then we can return true from this. Else, we need to return false. Okay, so now we can create the DFS function. So DFS takes in row, column, and index. If word.length is equal to I, we can return true. Because we've reached the end of the word and we found all of the letters within the board, we need to carry out the inbound check. So if row is greater than or equal to or.length, or row is less than 0, or column is less than 0, or column is greater than or equal to board 0.length. And finally, we need to check if the board at RC does not equal word at I. So when we start recursing through, we're going to check all 4 positions, or after the initial, we're going to check all 3 positions. And if the letter at the current position in the board does not equal the letter in word, then we can return false. So before we carry out the recursion, we need to set border RC as visited. And the way we'll do this is by setting border RC to a hash. And now we can carry out the recursion. So if DFS r+1 c I+1, so we need to increment row here and also index. Or, so we need to traverse all 4 directions. So r-1, c+1, c-1. And if one of these positions returns true, then we can return true. Finally, within this DFS function, we need to reset the border RC to equal word at I. And that's it for this code. Let's give it a run. Submit it. So given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from root node down to the furthest leaf node. So here we have a binary tree. Maximum depth is 3, where we have 3, 20, 15, or 3, 20, and 7. We need to work that out. So there are a number of different solutions to this question. We'll go through two of the most common ones. The first one is a recursive solution. So with any recursive solutions, we have base case and a recurrence relation. Great. So in a base case, just think of the most simple tree you can think of. So let's just say we have a tree that's just null. What are we going to be returning if we have a tree that's null? Well, we're looking for the maximum depth. So, well, if root is equal to null, return 0 because we're going to be returning some kind of number, some kind of integer. So we need to return 0 here. So that's the base case solved. With the recurrence relation, we're going to be returning a maximum depth. So we need to work out the maximum depth between the left subtree and the right subtree. So we can do that by simply doing math.max or a max method and passing in the left subtree and the right subtree. So that'll be this tree with this tree. But we also need to take into account the root, because at the moment, nothing is going to be returned here. So we need to specify the root as 1. So it'll be 1 plus max left and max right. So at this point alone, we have 1, but we now need to check its left subtree and its right subtree. So we create the recursive call on this subtree and on this subtree. So this becomes 1, and then it checks its subtrees. So nothing is going to be returned here because it's going to start a new section here. Root is equal to null, root is equal to null. So it's going to return 0 back. So 0 is going to be returned back here. And we have a 1 here, so it's going to return 1 up here. But we don't add this to the 1 here yet because we need to compare it to the right subtree. And at this point, the right subtree is 1. Then we compare it to these subtrees. So this is going to be 1 again, and this is also going to create check null and null. That's going to return zeros. It's going to go back up to here and return a 1 here. So it's going to be 1 plus 1. It's also going to check the right subtree. So this is going to be pointing to null and null. So we have null and null. Those are going to return 0. This is going to return 1 here. So it's going to choose the maximum between here and here, which is going to be 1 because they're both the same. So we have 2 here. This is going to return 2 to here. And then 1 and 2 are going to be compared and it's going to be added to the 1. So it's going to be 1 plus 2. So the final answer is going to be equal to 3. So this is the first solution. And time complexity here is O of n because we need to go through each node within this tree, and space complexity is also going to be O of n because within recursion we are using a stack data structure to store these values in temporarily, and they're going to store each and every value. So with this solution it's very quick to write out. So we write the base case out. So if root is equal to null, return 0, else we can return math.max max depth root.left max depth root.right. So we're comparing the left subtree and the right subtree, and we need to remember to add 1 because we are including the root here. Let's run that, see if that works. Let's submit it. Great, so that's worked. Okay, so let's go on to the second solution. So the second solution involves breadth search. So this is more of an iterative solution, which traverses this tree level by level. So it looks at this level first, then this level, then this level. And along the way, it increments depth. So we're going to have 3 things that we need for breadth search. We're going to have a queue. Remember, recursion is a stack. Breadth search is a queue. We're going to initialize it with the root. So we're going to pass 3 in there. We also need a current value, and we also need depth, which is going to be 0 to begin with. So with breadth search, we create a loop, and we loop through the first level. In this case, we've only got 1, so we only need to do that. So what happens is we shift off queue, we pass value into current, so queue has now been emptied. We check 3's children, so we look at the left subtree and the right subtree, and we see if there are any values in here. Yes, there are. There's 9 and 20, so we can add that to the queue. Right, now this part of the loop is complete. So 3 can be removed from current and depth can be incremented. So this is now done, and that is level 1. Now we can restart the loop with the new values in Q. So we can shift off of Q, we can pass 9 into current, we can check 9's children, see if it's got a left or right child. It doesn't in this case, so we can just remove that, and we need to now shift off of Q again. So 20 is in current now. We check 20's left and right child. It has 15 and 7, so we can add those to Q. We can remove 20 from current, and we can increment depth again. Now that is the second level done, so that's level 2. On the last level now, we can shift off of Q, so we add 15 into current. We check its children. There are none, so we can remove that. We check 7, we shift off of 7, add it into current, check its children. There are none, so we can remove that. And now we can increment depth by 1 again. And that is the final level. And we just need to return depth now because we exit the loop we created at the start. With time and space complexity, time again is O of n because we need to go through each node within this tree, and space is O of n. But in this case, we are using a queue to store the values rather than a stack. We still need to store each value within it. So space is O of n too. Okay, so firstly with breadth of search, what I forgot to mention in the explanation, if root is equal to null, then we return 0 because we need that sanity check. We have the depth, we need to initialize as 0. We have the queue, which we initialize with root passed in. Then we create the loop based on q.length. So as long as something is in queue, carry this out. So we create a reference to q, and then we loop through the level. So I is less than len I plus plus. Here is where we check to see whether there is any values in the left and right subtree, and we push them into q. So let current equal q.shift. If current.left is true, q.push current.left. So we want to push the value within q, and the same with right. So if current.right is true, we push into q the value of current.right. And once this loop exits, we have finished that level. We can increment depth. And once q is emptied, we'll exit this while loop, and then we can just return depth. Let's check to see if this has worked. Submit it. So given the root of two binary trees, p and q, write a function to check if they are the same or not. Two binary trees are considered the same if they are structurally identical and the nodes have the same values. So with this question, it's going to be a recursive solution. So what we need to look at is we need to create some base cases. So with any recursive solution, we have a base case and we have the recurrence relation. So what the base case is going to do is it's going to pop us out of this recursive call stack, otherwise we'll enter in an infinite loop. Okay, and the recurrence relation is what's going to get us closer and closer to the base case after each kind of recursive call. So we need to define some base cases and we need to define the recurrence relation, right? We're checking to see whether these trees are the same. We need to check whether these nodes are the same, and then we need to split it in two afterwards and check whether these are the same and also whether these are the same. And then we'd split these in two, so it's more of a divide and conquer approach, okay? Let's consider these base cases. So in the most basic tree you can think of, we have p is equal to null and q is equal to null. These are the two trees, both equal to null. So if they're both equal to null, we can simply define this and say return true. However, what if one is not equal to null and the other one is? So say 1 is equal to null or q is equal to null. In this case, we can return false. So that's another base case sorted. Now let's work out what would happen if the values were the same. We can return true, right? And if they're not equal to each other, we can return false. So these are the three base cases we've got. So we've got this one where p is equal to null and q is equal to null, we can return true. If p is equal to null or q is equal to null, we can return false. And if p.val is equal to q.val, we can return true. And then with the recurrence relation, what we need to do is we need to check both the left trees and also both of the right trees. So we need to do 2 recursive calls. And then what we need to do is we need to create that recurrence relation. And in order to do that, we need to do 2 separate recursions. One that checks the left subtree of both the trees, and then one that checks the right subtree of both the trees. And with these base cases in place, it will carry out the check within both trees. With respect to time complexity, we're going, in the worst case scenario, say all the values are equal to each other, like in this case, we have to iterate through each individual node of both P and Q. So it's going to be OP plus Q. And then space is just O1 because we aren't allocating any extra space. Okay, so let's write out this solution. So we need the base cases written out. So in this case, it's going to be P is equal to null and Q is equal to null. We can return true. If P equals null or Q is equal to null, then we can return false. Then we check the values of both P and Q. So if P.val is equal to Q.val, then we can carry out the recurrence relation. So we can carry out these recursive calls both down the left subtree and the right subtree. So we need to return this because we want to return a value whether it's true or false. So is same tree P.left, Q.left, is same tree P.right, Q.right. And this will create that recursive leap of faith. Else what we're going to do is return false, because if P.val does not equal Q.val, then return false. Let's give this a try. Submit it. So given the root of a binary tree, invert the tree and return its root. So in the first example, we have 4 as the root, we have 2 as the left child, 7 as the right child. Those have been inverted, and also the subtree of 7, 6 and 9 has been inverted, and the subtree of 2, 1 and 3 has also been inverted. So let's discuss a way of solving this problem. So we have our binary tree here, and we want to flip these values. Now, before we get into any kind of recursive calls in order to reverse every single node within the tree, let's first take a small subsection of this tree and work out how to solve that. With this subsection here, how would we flip these values? How would we flip root left and root right? Well, with JavaScript, you can just define root left and root right like so, put it in an array, and then just switch the values. And that in itself will give us the result of 4, 7, and 2. So we have inverted that subsection of this binary tree. So now what do we need to do? Well, we need to recurse down and invert these subtrees now. So let's take the right, for example. How would we recursively go down the right side and invert its children? We'd call the recursive function on root.right. And if that's the case, we'd call the recursive function on root.left as well to invert where the root is equal to the left. So if we recursively called the right, we'd get 7, 9, and 6. We recursively call the left, we'd get 3 and 1. Because at each recursive call you're adding onto the stack, you're changing up the root value to either the left or right child, and then you're repeating this process. Now there's one last thing with recursion that you need. You need a base case that will allow you to hop out of the recursive call. And in this question, say we have the root as undefined. So here in example 3, there is nothing within the root, so we can just return an empty array, and that is our base case. So if root is undefined, just return an empty array. So let's code this out. Let's invert just the left and right child to begin with, like we did in the example. So it'd be root.right, root.left. Then let's add the recursive call to invert root.right and to invert root.left. Let's make sure we spell it right. And then let's add a base case. So if root is available, and finally we can just return root. Let's give this a go. Okay, let's submit it. So a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum of a path is the sum of the nodes' values in the path. Given the root of a binary tree, return the maximum path sum of any non-empty path. So in example 1, we have this binary tree. The output is 6 because the maximum path sum is 1 plus 2 plus 3. In example 2, we have this binary tree. The output is 42, where we have the maximum path sum equaling this subtree right here, 15 plus 20 plus 7. Okay, so there's a lot to consider with this question. We're going to be using DFS, so we need to keep track of the maximum path. So we'll just call it max for now. And what we're going to do is constantly update this. So we're initially going to set our maximum to 0. So let's run through this binary tree and see what we need to return. So we're going to do a depth first search approach, and we're going to traverse the left and the right before visiting the root. So let's do that. So let's go down to the left. We reach this null value down here. Okay, so 9 is pointing to null. When we reach a null value, we can return 0. We need to return an integer in this case because our actual output is going to be an integer. So we have a base case. And that is if the node we're on is equal to null, just return 0. So we're going to return 0 here. We're going to return 0 here because we've gone down the left side, the right side, and then we visit the root. Okay, so it's going to be a post-order traversal. We reach this 9. The current max at this point is going to be the left side plus the root value plus the right side. So this is the current max. So 0 plus 9 plus 0. Is that greater than our max of 0? Yes, it is. So we can update that. Now, what we need to pass up from this side is going to be the maximum between the left value and the right value plus the root value. Now, the reason we do this is because we cannot take both of these subtrees, so this left side and this right side, we cannot include both of those in this path, right? This path here is a valid path, and this path right here is a valid path, but including both of them is not valid. So we need to return up the root value plus the maximum between left or right. So in this case, it's just 0, so we're going to return up 9. Now we need to go down the left side or the right side here, but go down the left. So we reach this null value. Again, we're going to return up 0. Go down the right, return up 0. Now here's the sticking point. We have a negative value here. So our current value at this minute, or our current max, is 0 plus minus 2 plus 0. So that's minus 2, right? So is that greater than this max here? No, so we can keep the maximum at 9. Now, what do we return up from here? Because if we return up minus 2, whatever we add that to is going to be decreasing the overall max, which is something we don't want. So in this case, we need to return up 0. So now we're at 20. Current max is, well, let's go down the right side. This is going to be connected to a null. That's going to return up 0. The current max is 0 plus 20 plus 0, which is going to be 20. So we can update the max. And then we return up 20. We go down the right side. We return up 0. Here we have a current max of 20 plus 15 plus 0. So that's 35. So we can update the maximum. So we have 35 as our maximum at this moment in time. Now what we return up from here is the root value plus the maximum between left and right. So that's going to be 20 plus 15, which is 35. Then we traverse the right tree and then the left. So we reach null here. Turn up 0. Return up 0. Current max is 0 plus 7 plus 0. So that's not greater than 35. So we return up 7 plus the maximum. So that's going to be 7. Now we have a current max of 35 plus 20 plus 7, which is equal to 55 plus 7, which is equal to 62. So that's greater than 35, so we can update the max. Now we return up the root value plus the maximum between left and right, so that's going to be 35 plus 20, so we return up 55. Now at this level, we have the root value of 10 plus 9 plus 55. which is equal to 74. So we can update the max again. And because we've reached the root, we have nowhere else to look. So we return this value here. So the complexity analysis for this question, time is going to be ON, where N is the number of nodes, since we visit each node no more than twice. And then space is going to be O of H, where H is the height of the tree. So let's code this out. So we need the max variable, which will initially set to negative infinity. I said in the explanation it should be 0, but actually it should be negative infinity just to account for any values less than 0. Okay, so let's create the function. We'll call it DFS. I'm going to pass in root. When we call it, we'll pass in root. And we also need to return max at the end of this. So as we said in the explanation, if root is undefined, we can return 0. So if we reach a null value, we just return up an integer. Then we need to do the post-order traversal, so left, right, then root. So let's get the left, which is equal to DFS root.left. Let's do the same for right, but on the right side, so DFS root.right. And then we can get the current max. So current max is going to be equal to left plus root.val plus right. So this is where we're getting the total of the subtree. Now the issue is, at this moment in time, we haven't accounted for negative values. And the way we do that is by using math.max and comparing the left side with 0 and returning whichever value is greatest. And we can do the same for the right. 0 DFS root.right. This way we're always going to be returning a positive value, so we're never going to be decreasing the overall maximum path sum. Then we can update the max, so I'll equal maximum between current max and max. And finally what we need to return up the tree is root.val plus the maximum between left and right. Okay, let's give that a go. Given the root of a binary tree, return the level order traversal of its nodes values from the left to right, level by level. So in the example here, we have a binary tree, so our output needs to include the nodes values level by level. So we've got 3 here, which is the first level. We've got 9 and 20 here, which is the second level. We've got 15 and 7, which is the third level. And as you can see, the output is an array containing 3 different levels, first, second, and third level. So let's discuss how we'd solve this. So level order traversal, we'll be using a breadth first search approach. So breadth first search utilizes a queue data structure. Now a queue data structure just restricts the processing order of an array to first in, first out basis. So we're going to initialize this queue with the root. So we're going to pass in 3. We're going to have current. This is just going to resemble the current node that we're on, that we're checking to see if it has children. And then we are going to also need a level array, which is going to store the levels. And up here will be the result array. So let's walk through this example. So we've got root within the queue. We need to check its children, left and right. So we shift from queue. So 3 goes into current. We check its children. So there's 9 and 20. 3 has been seen, so we can add that into level. And because we've finished this level and there's no other node at this level, we can push 3 into results and then we move on. So everything is reset apart from the queue, which contains 9 and 20. We shift from the queue, so 9 goes into current. We look at current. Does it have a left child? Does it have a right child? No. 9 has now been seen, so we can add it into levels, and then we move over and check the next value within the queue. So 9 has been seen. 20, shift from, add it into current, check if it has children. We have 15 and 7. These can be added into the queue. 20 has now been seen, so we can add it into the level. Now there are no more nodes at this level, so we can add this array within to results and then reset level and current. So now we shift from queue, 15, add that into current, check 15 if it has children. It doesn't. So 15 has been seen to, and it can be added into level. Now we move along in queue. We check 7.
7 can be shifted, can be added into current. Check to see whether 7 has children. It doesn't, so we can add this into level. Now there are no more nodes at this level, so we can push that level into results. Finally, because everything has been seen to in queue, so queue at this moment in time will be empty, there'll be nothing in current, and level will also be empty because we pushed it into results. Now that queue is empty, we can pop out of that while loop, and then we can just return results. Time and space complexity. Time complexity is ON because we need to visit each individual node, and space complexity is O of N as well because we need to allocate space for the queue. So firstly, we need to carry out a sanity check. So if root is equal to null, then we can return an array. Let res equal an empty array. Let q equal an empty array, and we're going to pass in root. So let's create that while loop. So as long as there is something in queue, carry this out. We need to initialize level and level size. We'll call this q.length. And then we need to create the next loop. So while level size is true, carry this out. So we need to grab the current value, which is going to be shifted from queue. We need to check whether current has a left and right child and then push that into queue. So if current.left is available, queue.push current.left, and do the same with right. Now that current has been seen, we can add that into our level array, and we need to add in the value, and then we need to decrement level size so we can escape this while loop. Res.push level array. So once we exit this while loop, we have finished the level, so we need to push into res the array that we have created, and then lastly we can return res. Let's run this code. Okay, let's submit it. We're given a tree and we're given a subtree, and we need to work out whether this subtree can be found within this tree. Now this question is very similar to LeetCode 100, same tree, which I've made a video for. Now if you want to go check that out before trying this question, then go ahead and do so. So the trick here is each position within this tree, we need to check for this subtree. So we're going to have two recursive functions. One is going to check whether this is the same subtree. So we'll check, say at the root here, we'll check 3, 4, and 5 to see whether this is the same. And one is going to recursively go through each of these nodes. So let's drill down into it, right? So how can we check to see whether this subtree, for example, is the same as this? And this is where we'd be using the solution to LeetCode 100, same tree. Firstly, we need to check the roots, right? If they are different, so if val1 doesn't equal val2, then this will return false, like in this case. Or if one of them is equal to null. So say we were comparing 4 and 1 with 4, 1, and 2. Well, the right child of 4 is null, and this is equal to 2. So if one of them is equal to null, then we can return false. And lastly, in the most simple case, if both of them are equal to null, then we can return true. So if both val1, val2, then we can return true. So these are all the base cases that we need, and these base cases will be checked within each recursive call. So firstly, they'll be checked at the root level. We can clearly see that value 1 doesn't equal value 2, so we return false from this. Then we move down the left side and the right side. We carry out the isSame function from this starting point. So 4 is equal to 4. Great. We recurse down the left side and the right side. And we can see that the left side and the right side are both equal to each other. Then obviously it goes down to nulls. The values are both equal to nulls, so we can return true from this. So this subtree right here is going to return true. We also need to check the right subtree. So the right of 5, we can clearly see that the first node doesn't equal the node in the subtree we're comparing to. So from this, we return false. Now this is a really important point. When we return the values, we need to return whether the left subtree or the right subtree returns true. So we return true or
false. So as long as one of these subtrees returns true, we're going to return true from this. And time complexity for this one is going to be O of m times n, because for every node within this tree, we're going to check whether it matches this subtree. So it will be m times n, where m is the number of nodes within this subtree, and n is the number of nodes within this tree. And then space is going to be m plus n. So let's code this out. So for each node in the tree, we have to run an isSame function to see whether at this node within the tree, if it's equal to the subtree. So if we take root 1 and root 2, if root 1 and root 2 are both equal to null, we know that we found a match, so we can return true. If root 1 is equal to null, or root 2 is equal to null, or root 1 val doesn't equal root 2 val, then that isn't a match, so we can return false. And then we need to recurse down the left subtree and the right subtree. So we're going to return isSame, passing in root 1.left, root 2.left, and isSame passing in root 1.right and root 2.right. So both of these need to return true in order for the subtree to be the exact same. Then we need another function to go through each node within the main tree and recursively call from each node to check whether this subtree is the same. So if we call this DFS, we pass in node. When we call it, we're going to return it. So DFS, pass in the root, so the main tree. If the node is equal to null, we can return false. Then we need to call the isSame, passing in the node and the subroot. And if this returns true, then we have found a match. So we can return true from this DFS function. And what we said in the solution run through is we need to return whether the left subtree or the right subtree returns true. So if one of these subtrees returns true, then we know that this tree has a subtree that is equal to the subroot. And that's it. Submit it. So given two integer arrays, preorder and inorder, where preorder is the preorder traversal of a binary tree and inorder is the inorder traversal of the tree, construct and return the binary tree. So we have preorder, we have inorder, and we need to construct this tree using just those arrays. So let's dive into the walkthrough. Okay, so this is a really fun question. We need to construct this binary tree here using the preorder traversal, which is root left right, and the inorder traversal, which is left root right. So what do? Well, we have the root here, which we know is 3. Where can you see within preorder or inorder, how can we get the root of this? Well, we know preorder is root left right. So the value at this index, the first index within the preorder list, is going to be equal to the root. Great, so we can start constructing it. Now we need to know the left and right subtrees. Well, if we look in preorder, we can't exactly find out what's in the left subtree and what's in the right subtree using this preorder list. However, if we look in the inorder, we've just gotten the root from pre, right? So if we work out the index of the root from preorder, then as you can see, everything to the left of 3 is in the left subtree, and everything to the right of 3 is in the right subtree. So by using that information, we can use recursion in order to build out this tree. The only other thing that we need in order to build this tree out is the length from the inorder list at position 0 all the way up to the root value. Once we have that, we can construct the recursive calls for the left tree and the right tree and build it out. Now, the best way to show you this is to jump into the code. So that's exactly what we're going to do. So we're going to have a function called recurse. Right, and inside this, we are going to need 4 parameters. We're going to need the start of the preorder, so we call it pstart. We're going to need pend, which is going to be the end of the preorder. And we're also going to need the same for inorder. And when we call this, we need to return it. So it's going to be recurse, passing in 0 for pstart, preorder.length -1 for the end of the preorder. 0 for inStart, and inorder.length -1 for the end of the inorder array. So all very straightforward to begin with. Now if inside the recursive call, we need a base case, which is going to hop us out of this. So at any point, if the starting value of preorder or the starting value of inorder is greater than pend or is greater than inend, we can return null, right? Because we've reached the end of either the left subtree or the right subtree. So if pstart is greater than pend or inStart is greater than inend, we can return null. So that's our base case. Now we need to build out the tree. So like we said in the walkthrough, we can get the root value, right? And this is going to be preorder, passing in pstart. So initially we've got the preorder at index of 0, which is pstart. This will give us the root value of 3. Now we need to work out the position of that within the inorder array. So let's call it in index. This will be inorder index of root val. And remember, like we said in the walkthrough, we need to determine the number of nodes to the left of the root value within the inorder array. So n left is going to be in index minus inStart. Now we can create the root. So root is going to equal a new tree node, and we're going to pass in the root value. Then we can build out the left and right subtree. So it's going to be a recurse. Root.right is also going to be a recursive call. And at the end, we are going to be returning the root. So this is the tricky part, right? In the left subtree, we have 9. And within preorder, we know that 9 is at position 1 within the preorder array. So we are going to pass in to this recurse for pstart plus 1. For the end of the preorder, we are going to pass in pstart plus n left, right? Because we can use the numbers to the left of the root value within inorder to work out where the end of preorder is going to be with relation to the left subtree. So it's going to be pstart plus n left. Then within the left subtree for inorder, the starting position is still going to be inStart, right? Because inorder is 9 to begin with, and it's going to be inend -1 for inend. And that's because we are subtracting a value, we're subtracting the root from this. And then for the right subtree, we're going from 3 to 20. So in preorder, how do we get to 20? Well, if we do prestart plus 1, we get 9. And then if we add n left, we get 20. So we do pstart plus 1 plus n left. For the end, well, we're going up to the end of preorder. So it's just going to be pend. Then for the parameters that we're going to be passing in regards to the inorder array, it's going to be the index, right? So this value here, the index of this, plus n left. So we're going to move here. So in index plus 1. And likewise for the inorder array, we're going to be going up to the end of that array. So it's going to be in end. And that looks good. When this runs, it's going to return this root, and we're going to return it here. So let's give this a run. Submit it. So given the root of a binary tree, determine if it is a valid binary search tree. A valid binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's keys. The right subtree of a node contains only nodes with keys greater than the node's keys. Both the left and right subtrees must also be binary search trees. So let's jump into the explanation. So there are a few ways we could solve this. So we know for a fact that binary search tree, the left value needs to be less than the root. So it cannot be equal to, it cannot be greater than, and the right value needs to be greater than the root. It cannot be equal to or less than. So there are a couple of ways we can work this out, and both include recursion. One is to do an inorder traversal, which will give us 1, 2, 3. So inorder traversal is left, root, right. So left, root, right. And then we could create some kind of isSorted function to see whether these are in order, and that would return true. Now the other way, the way that we're going to be doing it is by using recursion. So we need to do some kind of divide and conquer approach. With this tree here, with any recursive solution, we need base case or base cases and we need a recurrence relation. This is any recursive solution boilerplate. So we need a base case and we need recurrence relation. So let's think about this tree, for example. Let's just imagine we have the most basic tree and the tree itself is just null. What is that going to return? That is going to return true, because based on definition, a binary search tree that doesn't have anything in it is said to be true. So we can create a base case to say that. So root is equal to null, then just return true. Okay, so that's one base case solved. So we need to create another base case based around binary search trees. And we know for a fact that 1 needs to be less than 2 and 3 needs to be greater than 2. So we can create a base case from that. So we can say if root is less than or equal to the left, or root is greater than or equal to the right, return false, because in that case this is not a valid binary search tree. Now that we've carried out the base cases, what we can do is we can create this recurrence relation, and as you can see, we need to compare the left subtree and the right subtree, because remember in the question it said that the left subtree and the right subtree both also have to be valid binary search trees. So we need to recurse down, and we need to go down the left and we need to go down the right. Now there's one thing that we haven't done yet, and that is work out what we compare the root to initially, because at this point in time with the left value we can compare that to the root, and with the right value we can also compare that with the root. But what do we compare the root with? If we look at the question and we go into the constraints, we can see the smallest value is minus 2 to the power of 31 and the greatest value is 2 to the power of 31. So those are some pretty large values. So we can say that the left side that this is comparing to would be minus 2 to the power of 31, and the right side would be 2 to the power of 31. Okay, but an easier way to do that, or a more simple way, would be to just say compare it to negative infinity and compare it to positive infinity, and then we can create the recursive calls. Now time and space complexity of this solution. Time complexity would be O(n), because we need to go through each individual node, and space complexity is also going to be O of n, since we keep up to the entire tree within the call stack. So let's create this recursive function. So let's call the function recurse. And what we're going to pass into the recursive function is the root, because we're going to be updating this. And we also need to pass in negative infinity and positive infinity. And we'll call these min and max. So min and max. So we need the base cases. First one is to check if root is equal to null. If it is, we can return true, because null is defined as a valid binary search tree by definition. The second base case is to check whether root.val is greater than or equal to max, or root.val is less than or equal to min. We can return false. So those are the two base cases. Now we need the recurrence relation. So here we just recurse down the left side and the right side. So the root in this case, because we're going down the left side, is going to be root.left, because we're moving from this position, 5, down to 1. The new root is going to be root.left. In this case, the minimum is going to stay as min, and the maximum we know now is going to be 5, so it's going to be root.value. Okay, so we've gone down to 1, so the root is now root.left. We don't exactly know the minimum at this point, but we do know the maximum, because 5 needs to be greater than 1, so we can pass in root.val. And if we do the same for the right side, so if we recurse, pass in root.right as the root, and then with the minimum, we know that 5, well, this isn't the best example to look at. At this example, we know that 3 needs to be greater than 2, right? So 2 is going to be the minimum. So it's going to be root.val as the minimum, and we need to just pass in max. And then we need to return this, and we also need to return this. And that should be enough to solve this problem. Let's check to see if it's worked. Okay, so it's been accepted. Let's submit it. So given the root of a binary search tree and an integer k, return the kth smallest value of all the values of the nodes in the tree. In the first example, we have a BST right here, binary search tree. We have a kth value equal to 1 and the output is 1. In the second example, we have another BST, the output, or k is equal to 3, and the output is also 3. So let's dive into these examples and try and work out what this question's looking for. So here we're looking for the Kth smallest value, and the smallest value is 1. Now remember, the smallest value 1 indexed, so that just means that 1 is the starting point, okay? So if it says the first smallest value, that means index of 0 within the BST. So within this binary search tree, well, the really important part to consider is that this is a binary search tree, and what is unique about a binary search tree, that is that each element or each node within the tree is in order. So the left value is always less than the root, and the right value is always greater than the root. So we can use this to our advantage, and we can use an in-order traversal method of this BST. And what that's going to give us is it's going to go down from the root, it's going to go down left, it's going to go down left again. This is pointing to null, so it's going to add this into the order, then it's going to go right, then it's going to go to the root, and then it's going to go right. So we now have the BST within an array, and it's completely ordered. So that's the first step of the solution, right? Just convert it into an array using in-order traversal. And then what can we do with this? Well, we can just do a loop and loop through this and find where the index is equal to k minus 1, because the first value right here is the smallest value, and we're going to have to get k minus 1 because this is at index 0. And that's the second part of the solution, so that will just return the answer that we want. Let's have a look at the second example. So k here is equal to 3, so we need to find the third smallest node within this binary search tree. And if we do the in-order traversal again, what we have is the left side, so we go down all the way to the left, 1, we do the root of that, which is 2, we look right, there's nothing there, so we go up and we go to the root of that one, which is 3, we go right, which is 4, then we go to the root of that one, which is 5, and then we go right, which is 6. So the in-order traversal has given us this. Now what we need to do is we need to loop through this array, and we need to find k minus 1 index. And we want to find k minus 1, so we want to find 2. So we loop through this array and we find 2. And that is the answer that we are going to be returning. Okay, so let's write this out. Let's declare a variable called r, which is going to contain the in-order traversal of this binary search tree. Let's create that function. So within the in-order function that we're going to be creating, we pass in the root, and we pass in r because we want to be updating r, and we want to be traversing the tree, so we have to pass in root. So let's write this in order function. So we pass in root and r. Root is undefined, then we return and carry on the traversal to other nodes. So in order root.left r. So the first step is to traverse down the left side, because remember, in order traversal is left, root, right. We push in r root.val, and then we do in order traversal of the right side. And this will recursively fill out this array here. Now we just need to create another function. Let's call it find kth. Pass in the array that we just created and pass in k, and then let's create this function. So as we said, we need to loop through the entire array. And we need to specify if I is equal to k minus 1. Remember, it's the first indexed value, so we need to specify if I is equal to k minus 1. And then if it is, then we can return the value at r. And then lastly, we just need to return this function here. Let's give this a go. Okay, it's been accepted. Let's submit it. So given a binary search tree, BST for short, find the lowest common ancestor of 2 given nodes in the binary search tree. According to the definition of lowest common ancestor on Wikipedia, the lowest common ancestor is defined between 2 nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So we have P as set at 2, Q is set at 8. We need to find the lowest common ancestor of that. So in this binary search tree, where is 2, where is 8? 2 is here, 8 is here, and this is the lowest common ancestor because it has both 2 and 8 as its children. Now, if we wanted to find the lowest common ancestor of 3 and 5, it would be 4, right? Because 4 takes in both 3 and 5 as its immediate children. So let's dive into the solution to this. Okay, so our solution is going to be using some sort of recursive algorithm, and a thing to take into consideration here is that this is a binary search tree. So the binary search tree is ordered, so everything to the left of this root is less than the root, and everything to the right of it is greater than the root. And we can use that to our advantage to create this solution. Okay, let's say we have p is equal to 3, q is equal to 5. So let's begin this. So let's have a look at the binary search tree at the root. So the root is 6. Now, what do you notice about p and q? Well, they're both less than 6. And because this is a binary search tree, we know that all values that are less than 6 are held within the left-hand side of the tree from the root. So we can use this to create a recursive function. So if the value, so p.val and q.val, are both less than the value at root, then recurse down the left-hand side. So that's exactly what we're going to do. So we're going to recurse down the left-hand side. We're going to update the root. So the root is now going to be 2. So we're now at this point. Is p.val less than 2? No. Is q.val less than 2? No. They're both greater than 2. And what did we say about a binary search tree? If the values that are greater than the root are always found in the right side of the subtree. So we can recurse down the right side. So if p.val and q.val are greater than root.val, then recurse down the right hand side, and then we end up at 4. So 4 is the new root. So we check, is p.val less than the root.val, which is 4? Yes, it is. Is q.val less than the root.val? No, it's not. q.val is greater than the root.val. So we have one value which is less than root at val, and one value which is greater than root of val. So if we have this condition, then all we need to do is return this value here, because we have found the lowest common ancestor of both 3 and 5. Okay, let's just run through another example to solidify the solution. Let's say p is equal to 11 and q is equal to 13. So we start at the root, we look at the root, we check if p is less than root value. No, it's not. Is q less than the root value? No, it's not. So based on the binary search tree, all the values greater than the root are held within the right subtree of the root. So we're going to traverse down that side. So at 8, is p and q less than 8? No, it's not. So again, we traverse down the right side. We're at 9 now. Is p.val and q.val less than 9? No, they're not. They're both greater than, so we traverse down the right hand side. We get to 12. Is p.val less than 12? Yes, it is. Is q.val less than 12? No, it's not. q.val is greater than 12. So based on that, we can just return this value. So in terms of time complexity for this algorithm is O of n, linear time complexity, where in worst cases, we visit each node within the tree. So say we had this, for example, just this tree of 6, 2, and 8, and we have p is equal to 2, and q is equal to 8, we are going to visit each node within this tree. Space is O of n, where n is the height of the tree, so the space utilized by the recursive call stack, and in worst case scenario, we could have a skewed tree, so we could have just this tree on this side here, and each level we would add into the recursive call stack. Okay, so let's write this out. So if p.val is less than root.val, and q.val is less than root.val, we know that p and q are both going to be found within the left side of the tree. So we need to recurse down the left side, passing in p and q. So if p.val is greater than root.val and q.val is also greater than root.val, we know that it's going to be found within the right side of the tree, so we can recurse down the right side of the tree. Again, passing in p and q. Else, all we need to do is at this stage, we'll have one which is on the left-hand side and one which is on the right-hand side. So neither of the two cases above will carry out. We can just return root because we have found the lowest common ancestor. Let's run this code. Okay, let's submit it. So a trie or prefix tree is a tree data structure used to efficiently store and retrieve keys in a dataset of strings. There are various applications of this data structure, such as autocomplete and spell checker. So implement the trie class. Trie initializes the trie object. Insert inserts the string word into the trie. Boolean search returns true if the string word is in trie and false otherwise. Boolean starts with returns true if there is a previously inserted string word that has the prefix, and false otherwise. So here we're inserting apple. We're checking to see whether the trie contains apple. It returns true. We check to see whether it contains app. It does not contain app as a word because within this trie we have set apple as the word. So we're going to have a flag which states that apple is the word. So once we get to app, that will be a prefix of apple, but it will not be the word. So we check here if starts with is equal to app, in which case this is going to return true because app is a prefix of apple. And then if we insert app into the trie and then search app, we will get true. So we need to implement this using classes. So let's quickly walk through what a trie is. So a trie, also called a prefix tree, is a tree data structure, and you basically store strings in it. So strings and letters. So the root is always an empty string. So we've got two strings here. We've got cars and carpets. So let's work how this would fill out. So we have C. We check if that is in the tree. It's not. So we simply create it. We do the same with A, R, and S. Now that we've reached the end of this first word, we can add an isWord flag, set it to true, to show that this right here, cars, is a whole word ending at S. And all the ancestors above it are prefixes of the word. So we have carpets now. So let's add that into this trie data structure. So we look to see whether C is within the data structure. It is. Look to see whether A is in. Yes. R is also within it. Now we have PET. So P is not within this trie currently. So we need to add it. So we branch off of R. We add P. We move over to E. It's not in the tree, so we add it. And then lastly, we have T, which we add in. And again, we add isWord to signal that this path carpet is equal to a word. So the two main sections that may provide some difficulty is the search and starts with. So we need to search within the trie to see whether we have a particular word. Now, if we looked for, say, car, this is going to return false. Even though we have car here, that is not a word within the trie because R right here does not have isWord set to true. It's a prefix of both carpet and cars. However, if we had cars, we'd go down to S, we'd see that isWord is equal to true. So that search is successful. So if we look at starts with cars, this is going to return false because this is actually a word, it's not a prefix. And likewise, if we look at car, this is going to return true because this is a prefix. So when writing this out, the first thing we need to do is we need to initialize the trie object. So let's set this.root equal to an empty object. Then in order to insert a word into the trie, we're going to get a reference. We're going to say node is equal to this.root. Then we loop through the characters of word. So let's see of word. So we check if the value of C within node is equal to null. If it is, we set it as an empty object. And once we exit that loop, we know we're at the end, so we can set isWord flag to equal true, so that we've created a word. Now within search and starts with, we're going to have to traverse through both word and prefix. So we could make this a lot easier and create a helper. And we will call this traverse. So in order to traverse, it's very similar to insert. We just need to get the node, which is set to root, loop through the word, traverse through. If node is equal to null, We can just return null. Else we can return node. When searching, firstly we need to traverse the word. So let's extract the node. So node is equal to this.traverse, which we just created, pass in the word. So here we're searching if the word is within the trie. So we need to make sure that node does not equal null, so the last value does not equal null, and also that the last value has is word flag set to true. So return node does not equal null and is word is equal to true. And then we starts with, so here we're looking for the prefix. So again, let's grab the node. Now we can traverse down to the prefix because remember, any descendant within the trie always has common ancestors. So here, as long as the value we're on does not equal null, then we have a prefix. So we can just return node does not equal null. And then we can give this a go. Let's run it. So we need to design a data structure that supports adding new words and finding if a string matches any previously added string. So we need to create word dictionary to initialize the object, add word with word as a parameter, which adds the word to the data structure, and then search, passing in word, which returns true if any string in the data structure matches the word or false otherwise. And if the value in the word is equal to a period, this is a wildcard, so it can be matched to any letter. So what data structure do we know where we can search through characters within a word in order to find whether the word exists? Well, we have trie data structures, right? And a trie data structure has, say, a root, and this branches off to the individual characters. So say we had a period, we had A, we had D. At the end of the word, there is usually a flag such as end is equal to true to state that, look, this value right here, this character is the end of this word. So if we search afterwards and we're looking for BAD, this will reach the D and it will return true because we've reached the end of that string. So in order to add a word to a trie data structure, I'll add a link to LeetCode 208 implementing a trie, also known as a prefix tree, where I discuss in detail how to construct a tree. Here we'll just look at the high level overview, right? So say we want to add to a trie, right? So our trie is initially an object, right? What we do is we look in this trie if we have this first character. If we don't, we set it to an empty object, and then we move over to A, and we repeat the process. So is A within this trie? No, so we add it. We reach D. Is D within the trie? No, so we add it. And now this is at the end of the word, so we can have an is end flag, which is equal to true within here. This is what a trie data structure looks like, and this is how we're going to construct it. Now, the tricky part of this question is where we're going to search through this trie data structure in order to work out whether we have a word that matches. So as stated in the question, if we have a period, this is considered as a wildcard, so this can be matched with any letter. So firstly, we are going to be using recursion for this, and with any type of recursive call, we need a base case. So something that's going to say, look, we found our solution, or we haven't found the solution, so we're going to return this. And for this question, we have a word, say we have bad again. The length of this is going to be equal to 3, right? So in our recursive call, what we can do is we can pass down an index, right? So this can be index 1, 2, 3. As you can see, we've reached index of 3, so we've reached the length of bad. If these two are equal, so if word.length is equal to the index and is end flag is set to true, this is really important because otherwise it could just be a prefix, then we found a result. So we can return true. So that is the base case we're going to work with. The other issue we have is this wildcard here. So like we said, if there is a period, this can be matched with any letter. So what do we do at this point? Well, the best step is to iterate through the keys at this level, right? And if any of these keys return true, so if we reach the end and there is an isEnd flag set to true, then this can ultimately return true. Otherwise, say we're looking for dad. We're simply going to check within the trie at each character. As long as they're not equal to null, we're going to check and carry on recursing, passing in the index, the trie at that character, and the word we're looking for. Sorry, that should be 2. And if we reach the end, where the index is equal to the length of the word and isEnd flag is equal to true, we can return true. What happens if we have Dado. Right, so in the case of Dado, we're going to go down this subsection of try. We're going to reach D. We're going to traverse further, and the value we're looking for is going to be equal to null. Right, and the current way we've constructed this so far, this hasn't been checked. So before we recurse down, we need to make sure that the character within the try doesn't equal null. If it does, then we just return false. So I believe we've covered everything for the solution. Let's jump into the code editor and start coding it out. So let's initialize the try, right? And this is going to be class-based. So we need to initialize it with this so that we can have access to it within add word and search. So that's the first part done. In order to add a word, it's the same as implementing try, LeetCode 208. We're going to have a reference to the try. So we're going to say this.try. And then we loop through the characters of the word. Like we said, if node at character is equal to null, so if it's not already in the try, we create it. So node at character is going to be set to an empty object. And then we move into it. And once we exit this, we are at the end of that value within the try. So we can add an isEnd flag here and set that to true. That's all we need to do to add word. Now for search, we are going to be using recursion. So we can have a container here. So we can say this dot, we'll call it DFS. We're going to pass in the word. We're going to pass in the try, and we're going to pass in an index of 0. And we need to return this. So let's copy this. Let's paste it up here. Let's add DFS here. Let's update the parameters to word, try, and index. Let's first add the base case. So if word.length is equal to the index, we have found an endpoint. So we also need to check whether we have the isEnd flag here. So try.isEnd. If there is an isEnd flag, we can return true or false. And we need to return this. Then we need to get the character. So the character is going to be word at index. So that gets us the character. Now, like we said, the period is going to be a wildcard. So if the character is equal to a period, we have a wildcard. So we need to loop through the keys within the try. Okay, so let's do that. So that key in try, if we find a solution when recursing to each of these keys within this try, if we find a solution that is true, we need to return true from this. So we're going to pass in word, we're going to pass in try at key as the next value within the try, and we also need to update the index to index +1. And if that returns true, then we need to return true. Else, if the character is not a wildcard, we first need to check whether the character is within the try. So like Dado, the O was not within the try, so we just return false. So here we're going to check, so if the character in try doesn't equal null, then we can carry out the search. So we're going to carry out the DFS. Remember, we're using class here, so we always need to add this before, and we need to pass in word, try at character, and index +1. And we need to return this. If we have reached this point, we can just return false. And that will recursively call throughout the entire try and compare it with the word, either return true or false, and it will be returned here. So let's give this a run. It's been accepted. Let's submit it. So given an m by m board of characters and a list of string words, return all words on the board. So each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally and vertically neighboring. The same letter cell may not be used more than once in a word. So let's have a look at what our first example looks like. So we have an m by m board with a number of different characters within it, and we need to find if any of these words right here exist within the board. We have oath, which starts at the first position and ends right here, and we have eat, which is backwards over here. So there are two words within the word array that can be found within the board, so we return those as the output. In terms of implementing it, I would say it's very similar to number of islands, but there is an extra level of complexity to this because we have characters as opposed to zeros and ones. So in order to make this as optimized as possible, what we could use is a try data structure to store all of our words in the dictionary. So firstly, what we need to do is create our try data structure with these words. A try data structure looks like this, so there is nothing within the initial position, and then we create the try. So we've traversed down oath, and we've put that within the trie. And at the bottom position, what we usually have within a trie is a flag of some sort to say that this is a word. But instead, what we're going to have is word equal to this entire word. So it's essentially going to be equal to oath. So we've checked over oath. Now we can go to P. So P-E-A. So now we can just add eat and rain to the trie. And this will make more sense in a minute when we start DFSing through this 2D array as to why we've done this. So again, word at this point at A is going to equal P. Word here is going to equal EAT. And word in this section is going to equal rain. Okay, so we've created our trie data structure. Now we can start carrying out the DFS on this tree. So let's start the first position. We have an O. So firstly, we need to check if O has the word attached to it. In this case, it doesn't. So we can start looping through. So we can check to see whether it's in the first position of our trie. So is it equal to P, E, R, or O? Well, we have the O right here. So at this point, we can DFS to the next position, right? So up, right, down, and left. So there are 4 possible positions, but we have to check if it's in bound. So this and this are invalid because it's not in bound, right? So across this way is j is less than 0. Up this way, I is less than 0. We also have to check whether it's too far down this way. So I is greater than board.length minus 1. We also have to check where it's too far over this way, where it's board j is greater than board at I.length minus 1, right? So we need to check whether it is valid to begin with. So that's the first step, to check whether the positions are valid. Also, we need to check, so say we went to E. E is not within the next position of this trie. So this descendant of O is not equal to this value. So we cannot go down this way. So the only position we can go is to this A, because it's equal to the A within the trie. So we can DFS at this position. So we can go up, right, down, and left. So we can't go up because that's out of bounds. We can't go right because the next value within the trie is T, and this is equal to A. So we can't go that way. Can we go back? Well, we've already visited O, so we can't go this way. So we need to make an adjustment for this. And the way we do that is we could use either a visited flag, so we could have visited and pass in all the positions that we have visited. So we could pass in 0, 0. But this increases your space complexity. So what we're going to do is we're actually going to just set this value before we finish this section. We're going to set this to an arbitrary piece of data. So we're going to set it to a hash. So it's no longer equal to an O. So we never go back to that position. Then we can go to T. We can DFS at that position. So we can't go back because we set this A to a hash. We go to T. We try to go to E. We can't go to E because the next position in the trie is a H. We go to A. We can't go to A because it's a H. So the only position we can go to is this value right here. Now this value has word attached to it. Okay, so it has a dot word attached to it. And if that is the case, then we push this value. So we're going to add this value to our result. So we're going to have a result array, and we're just going to push in oath. Now we want to stop this from being duplicated again. So what we can do at this point in time is we can set this to null now, because we have found it. So if there's 2 positions where there is oath within the board, we're not going to get that now because we have set this word to null. Great, so at this point, what we need to do now is we need to backtrack. Because we found this value, we need to go back up because all these values are currently a hash, right? We need to reset this board, right? So we need to reset this to a H, we need to reset this to a T, this to an A, and this to an O. So we can go ahead and do that. So now that we've done that, we can traverse through the board. So we can check at position A. Is that within the first position of the trie? No, it's not. So we can move to the next position. Again, A is the same. So we move to N. N is not found within this first level of the trie. So again, we move along. E is found within it. But if you see, if we traverse or DFS through E, the next position is A, and we don't have this. So we can move on to T. T is not within the first position. A is not within the first position. We go to E. E is within the first position. So we have this E. So we check, is word attached to it? No, it's not. Word is not attached to it. Word is attached to the T down here. So we can carry out DFS on this. We can't go this way because it's out of bound. We can't go to N up here. We can't go to R down here. We can only go to A because the second position within this try now is A. And before we move over to A, remember we need to convert this to a hash so that we don't go back to it. We go to A, we DFS at A. We can't go this way because we've converted E to a hash. We can't go to A up here. We can't go to K down here. We can only go to T because the next value in that try is a T. So we check at T, does this have a word property? Yes, it does. So we can push in that value here into our result array. And then again, we need to clean this up. So we need to convert the hash back to an A, the hash back to an E, so that we can carry on traversing through the board. So I, H, K, and R. If we look at the top level, the only one that we can find is R, and all its next positions, if we DFS in all directions, do not equal A. So we can move on. I, F, L, and V are not within this first level either. So we can end this and just return our output, the result here. So that's the basis for solving this problem. Time complexity in this case. So say we had a board that looks something like this, and we were at this position, and the words we have to look for are AA and treble A. How many steps can we take from this initial position? Well, firstly, we need to loop through every value within this board. So time complexity is going to be OM, where M is the number of characters within the board. And if we're at position A within the middle here, what is the maximum number of positions that we can go to that are inbound and valid? It's 4, so it's going to be 4 times what is the maximum number of positions. Say we had extra A's added on down here. What is the maximum number of positions that this A can go to? Well, it's going to be 3 in this case, that are inbound and valid. So it's going to be 3, and it's going to be to the power of L minus 1. L in this case is the length of the words within the try. So that is the time complexity. So space complexity is going to be ON, where N is the amount of characters within the try. So firstly, we need to create a function called buildTry, which is pretty self-explanatory because we need to obviously create our try. So to start off the try, we're going to have root, which is going to be equal to an empty object. We're going to loop through the words. We're going to get the current node. We're going to pass it as a reference to root. Then we're going to loop through the characters of the word. Okay, so if current node at the character is equal to null, then we can just say current node at character is equal to an empty object. So we're just creating an empty object at that current node at position char. Otherwise, we can traverse through. And then once we reach the end and we've built this try out, we need to add the word property. And the word property is going to be equal to the word. So the word that we've looped through within these words, just so that we can return this within our results. And finally, we need to return root. So within the main body of the actual function, we need to initialize result, which is going to be an empty array. We need to create, or we need to build out the try. So let's call it root, and we can say build try, and we can pass in words. Then we need to loop through the board to initialize the DFS. So looping through the rows. Looping through the columns. And then within the DFS, we're going to pass in the root. So the try that we've just created, I, J, going to pass in board. And we're also going to pass in result and pass in board. Now we need to create the DFS function. So DFS, we can call the root node. I and J can stay the same, as well as result and board. So the first thing we do within our DFS function is check whether the position or whether the node has the word property attached to it. If it is, we know we found a word within the board. So we can push node.word, the property which we created down here, which is equal to the word that we looped through. We can push that into the result array. And then we need to set the word property to null. And the reason, as stated in the solution, was because we cannot have duplicates. So say we found H here, that's going to have the word property attached to it. If there was another oath within this board, the H on that would also have the word property attached to it because it's the exact same word within the trie. So we need to set that to null so that we don't have duplications within our final result. Then we need to check whether the value is in bounds. So if I is less than 0, I is, or j is less than 0, that's out of bounds. If I is, or if I is greater than board dot length minus 1, or j is greater than board at 0 dot length minus 1, we can return. So these are all out of bound. If node board I j is null, we can return. And what this is saying is if the position in the board is not found within the trie, just return, because that isn't a potential path. Now we need to stop an infinite loop from occurring. So we create a reference to board ij, and we'll explain what this is for in a second. We set board at ij to equal the hash, and this is to stop an infinite loop so we don't go back to the previous value, which we've already looked at. We need to carry out the DFS in all 4 directions now. So we node at C, so node at board ij, result, and board. Now we can copy this 3 more times. And we just need to change the direction. So I plus 1, I minus 1, j plus 1, j minus 1. Okay, so once we've DFS'd through all of the positions and we've checked the board and they've all returned a value, we need to reset board at ij. So that's where C comes into play. So board at ij is currently a hash, and we need to convert it back to the value to carry on traversing through each value within this board. So we just set that back to C. And then finally, we need to return result. That's looking good. Let's give this a run. Okay, let's submit it. So given a reference of a node in a connected undirected graph, return a deep copy of the graph. Each node in the graph contains a value and a list of its neighbors. So with the test case format, for simplicity, each node's value is the same as the node's index. For example, the first node with value equal to 1, the second node with value equal to 2, and so on. The graph is represented in the test case using an adjacency list. So an adjacency list is a collection of unordered lists used to represent a finite graph. So each list describes the set of neighbors of a node in the graph. The given node will always be the first node with value equal to 1. You must return the copy of the given node as a reference to the cloned graph. So as you can see in example 1, we cannot exactly return the original graph. We also cannot return a copy of the original graph if the nodes are not in the correct position. We need to return a copy or a reference of the original graph where the nodes are all in the correct positions and they are pointing to the correct neighbors. Okay, so there are 2 ways we can do this. We can either use BFS or DFS. In this solution, we are going to be utilizing DFS because it's a slightly more intuitive solution. Within this, we need to create references. So we need to create copies of each one of these nodes, and we need to make the connection between these nodes as well. Because remember, this is an undirected graph, so that means that this pointer right here is connecting both ways, which makes this problem a bit trickier. Like any DFS recursive solution, we have base cases that we need to create. So we have base cases and we have a recurrence relation. So a base case, firstly, if we had the smallest graph possible, so we had a graph which was just equal to null. So if node is equal to null, what are we going to return from this? Well, we are just going to return node, right? So we're going to return node, which is the value of null. Now, within this, as I mentioned, there is an undirected link between all of the nodes within this graph. And we're going to have some kind of visited object that is going to store the nodes mapping to their copies. And the reason for this is to stop an infinite loop from occurring. So say we did a recursive call from 1 to 2. 2 is obviously going to check its neighbors as well, so it's going to go back to 1. 1 is going to check its neighbors, it's going to go back to 2. So we need to make sure we have a visited object to stop that from occurring. So let's put our visited object here. Okay, and this is going to be a mapping between the node and its copy. So let's start out this DFS recursive call. So say we start at 1. We want to check if the node is equal to null, which it is not. We're going to have a copy, which is going to be a reference, and we're going to have neighbors, which is going to be the neighbors that are going to populate within here. So before we carry out a recursive solution to go to 2, we need to add this within the visited set, right? We need to add this within visited. So we need to create that mapping. So 1 is going to be mapped to a copy. Now this asterisk means copy in this case. So we can add this within the copy. Now we can go to the next neighbors, okay? So we can go to 2 and we can go to 4. So let's say we went to 2, right? So we're currently at node 2. Let's add the references. So copy and neighbor. We check if the node is equal to null. It is not. We need to check whether the node and the copy is within visited. So this will be another base case. So if visited at node.val, because remember these are objects here and node has a value property, does not equal null, then we have already visited that node. So we can just return that value immediately. So that's the second base case sorted. So at this node, we've checked if it's equal to null. We've checked if it's in visited. It's not. So what do? We add it to visited. And we create that copy. So 2 copy goes up here. Then in order to populate these neighbors, we need to recurse to its neighbors. So we go to 3 and we go to 1. Let's say we went to 1. We check to see if 1 is within visited. It is. So what do we return? We return that value. So we return 1 here. So it's going to be the copy. So that part of the recursive call has been done for 2. Now we go to 3. So we're at 3. We check if this is equal to null. No, it's not. We check if this is within the visited object. It's not. So we add it within the visited object. Then we can add its reference. So 3. And its neighbors. So in order to get its neighbors, it needs to carry out the DFS function. So we go to 2 and we go to 4. So say we started off with 2. We check if 2 is in visited. It is. So from here, we can just return a copy of 2. So this error right here has been resolved. We can remove it. We go to 4. We're at 4 now. We check if it's equal to null. It's not. We check if it's in visited. It's not. So we can add it to visited. So we create the copy. Have a look at the neighbors. So in order to get the neighbors from this one, we go up to 1 and we go back to 3. If we go to 1, we check if it's equal to null. It's not. We check if it's in visited. It is within visited. So we can return a copy of 1. So 1 copy goes in here. This error has been resolved. Then we go back to 3. Now 3 is within visited. So we return the copy of 3. So 3 goes into neighbors. Now we have a node that is completed. So it has a copy, it has both of its neighbors as copies. So what do we do in this situation? So basically, what are we returning up the call stack? So what are we going to pass back to 3? Well, we need to pass back the node, right? So we're going to pass back 4. So 4 is going to go in here. We're at 3. 3 has been complete. So we can actually tick these off. So what do we need to return to 2? Well, we need to return 3. And then once we get back to 2, we can add 3 into neighbors. We can remove this arrow. The node 2 has now been complete. We need to go back to 1, but what do we need to pass back? Well, we need to pass back 2. So 2 goes along here. 2 goes into neighbors here. We remove this arrow. As you can see, we only have 1 neighbor within our copy. So we need to carry out the recursive call going to 4 here. So we go to 4. We check if it's in visited. It is within visited. So we return the copy of 4. So that is that. And then we can just remove this. And finally, we are left with a complete copy of the graph. And that is the basic understanding of how to solve this problem. Time complexity for this problem is O n plus E, where n is equal to the nodes and E is equal to the edges. And then space is equal to O of V, where V is the values within visited. So let's start this off by creating the visited object. Let's create the DFS function. We're going to pass in node as a parameter. We need to return DFS passing in node. So remember, the first thing to do is add the base cases. So if node is equal to null, we can return node. Then we need to check within the visited object whether we have the current node and its copy. So if visited at node.val does not equal null, then we can just return that. Otherwise, at this point, we need to create a new node. So we need to create a copy. So root is going to be equal to new node, passing in node.val. Then we need to set invisited at node.val to root. So we need to set to the copy we just created. And lastly, we need to create the recurrence relation. And the way we do that is we loop through the node's neighbors. So let neighbor of node.neighbors, got to make sure I spelled this right because it's the American spelling. Now here's the tricky part. We've just created this new copy, right? We've just created this copy. We've passed in node value. So at this moment in time, neighbors is going to be empty. So it's going to be an empty array. So what we need to do is we need to allocate some values to that. So neighbors, we need to push in. And what we're going to push in is the DFS function passing in neighbor. So we are passing in, or pushing into neighbors of our copy, the result of this recursive call passed in neighbors. And what this will do is it will create the connection between each node. And then finally, we need to return root. So what do we need to pass back up the recursive call stack? Well, we need to pass root in order for the neighbors of the copies to be populated. Let's give this a run. Submit it. So there are a total number of courses you have to take, labeled from 0 to num courses -1. You're given an array of prerequisites, where prerequisites I, A, B indicates that you must take course B before course A. So if we have zeros and ones, we need to take 1 before we can take 0. Return true if you can finish all the courses, otherwise return false. So in this first example, we have number of courses equaling to 2. And in order to take course 1, we need to take course 0 first. Is that possible? Yes, it is. There aren't any cycles here. However, in example 2, we have 2 courses. And in order to take course 1, we first need to take course 0. And in order to take course 0, we first need to take course 1. So there's a cycle here, right? So this is going to return false. So how can we implement this? Let's take this example, right? We have 0 pointing to 1, 0 pointing to 2, and 1 pointing to 2. Okay, there are no cycles here. Whereas with example 2, where we had 1, 0, 0, 1, if we have a look at this, 1 points to 0 and 0 points to 1. So in order to complete 1, we go to 0. In order to complete 0, we go to 1, and we repeat the process. So it's going to enter an infinite loop. So we have a cycle here. So we can return false from this. But how would we go about checking to see whether there are cycles in this? Well, we're going to use DFS to solve this problem. And with graph problems, we're going to create an adjacency list. And this will look something like this. So we have the current course we need to take, right? And this is going to map to the courses that need to be taken before this one. 1 is going to point to 2, because in order to take 1, we need to take 2. And 2 doesn't have any outgoing edges, so 2 can be an empty array. We're also going to need a visited set, and this is just going to store the nodes that we've visited within this graph. So let's start. We're going to loop through the keys within the adjacency list. So if we start at 0, we can check whether it's in visited set. If it is within visited set, then we have a cycle, right? So if it's not, we just add it into the visited set and then we recurse, right? So we go to its neighbors. So let's say we go to 1 first. We're at 1, we check visited set. It's not in there, so we add 1. And then we go to 1's neighbors, so 2, right? We look at 2. 2 is not within visited, so we add it. And we can see that 2 doesn't have any outgoing edges. So this immediately, because there are no outgoing edges, can return back up the call stack true. But before we return true, we first need to remove 2 from the visited set. And the reason for this is if we go back to 0 and we check for 2's neighbors, if we left it within the visited set, this would return a cycle, right? But here, as you can see, there aren't any cycles because these outgoing edges are directed, right? So we return true from this. At 1, we can see that we've checked all of 1's neighbors, or the courses that it needs to complete before being completed. So we can remove this because we've now seen it. And we can also update 1 in our adjacency list. So we can remove the course it requires to complete, right? Because we know it can carry this out. It can be completed. Once we've done that, we can return true from here. Now 0 has to go to 2 because 2 needs to be completed in order for 0 to be completed. So we visit 2. We look in the visited set here. As you can see, we've deleted it from the previous time we visited 2 because, as you can see, these are outgoing edges. right? So there is no cycle here. So we can add this into the visited set. Then we go to 2. We look in the adjacency list. This is an empty array. So we know this can be completed, right? There are no outgoing edges. There's no chance of there being a cycle. So we can remove this from the visited as soon as we've seen it, and we can return true. Finally, all neighbors of 0 have been visited. So we can empty this out, and we can finally return true. So firstly, we'll create the adjacency list, right? So it's going to be an object. Then we're going to need a visited set. So we can create that here. Now we need to populate the adjacency list. So we're only going to be mapping B to A in this case, right? Because for course A to be complete, it's dependent on course B being completed first, right? So we're only going to map B to A. So if we loop through A and B of prerequisites, if we don't have a value already in the adjacency list at A, then we can create that, and we'll create it being an array containing B. Otherwise, we're just going to push in at position A within the adjacency list. So we're going to need a DFS function, right? We'll pass in current. And in order for this to work, we need to loop through the keys of the adjacency list and run DFS for those keys. So let key in adjacency list. So if DFS at key returns false, then we are going to return false, right? Otherwise, we're going to return true. And what this DFS function is doing is it's checking for cycles. So firstly, we need to check visited, whether it has current. If it does, then we have a cycle. So we return false. We also need to check whether the value in the adjacency list is just an empty array. If it is, great. This course can be completed. So we return true. So if adjacency list at current is equal to an empty array, we can return true. Then we can add to visited the value of current, and we can check the neighbors. So if there is a neighbor to check, then we can loop through the neighbor and carry out the DFS on this. So if DFS neighbor doesn't return true, then we're going to return false. And once current has been visited, we need to delete the current from visited set. And seeing as we visited all neighbors within the adjacency list at current, we can set it to an empty array. Finally, if we reach this point, we can return true. Let's give that a run. Submit it. So you have an M by M rectangular island that borders both the Pacific Ocean and Atlantic Ocean. The Pacific Ocean touches the left and top edges, and the Atlantic Ocean touches the right and bottom edges. So the island is partitioned into a group of square cells. You're given an M by M integer matrix height, where height RC represents the height above sea level. The island receives a lot of rain, and the rainwater can flow to neighboring cells directly north, south, east and west, so up, down, right and left. If the neighboring cell's height is less than or equal to current cell's height, return a 2D list of grid coordinates result, where result RC denotes that rainwater can flow from cell RC to both the Pacific and Atlantic Ocean. Okay, great. So we have a 2D board right here. And the left side is bordering the Pacific, the top side is bordering the Pacific, the right side is bordering Atlantic, and the bottom side is bordering Atlantic. So we need to work out which of these cells can reach both the Pacific and Atlantic based on the constraints that water can only flow from higher values to lower values, or higher values to values that are equal to those values. And we can only move up, right, down and left. So this is a standard graph problem. We'll probably be utilizing BFS or DFS in this solution. So as you can see in this example, all of these values in yellow can reach both the Pacific and Atlantic Ocean. Okay, so firstly, let's quickly discuss how this water flows. So say we take 5 here. Water can flow in 4 directions. It can flow up, down, left and right, and it can flow from higher values to lesser values, or values that are equal to each other. So we need to make sure that we reach the Pacific and Atlantic from this position. If we can't, then it's not a valid point within this grid. So let's have a look. So 5 can flow to 4, 4 can flow to 2, 2 is touching Pacific. 5 can flow to 3, 3 can flow to 1, 1 is bordering the Atlantic. So this is true. So how do we go about solving this? Well, as I mentioned, we can use BFS or DFS. It makes more intuitive sense to utilize BFS in this solution because it's essentially the shortest path. So we can forget about DFS. Now within this BFS, we are going to have to do 2 breadth first search. So we're going to have to do one for the Pacific and one for the Atlantic, because we need to find whether a value can reach the Pacific and the Atlantic, and then we need to do some additional logic to state whether a value in the board can reach both the Pacific and the Atlantic. But as with any BFS, we have a queue. So we're going to have a Pacific queue, and we're also going to have an Atlantic queue. And what we're going to push into this is going to be the position of each value within the board, and what we're going to push into, say, this Pacific queue is all the values within this board that are neighboring the Pacific. Okay, so all of these values and all of these values are going to be going into the Pacific. So their positions in this grid will populate the Pacific queue. So let's write a few out. So we've got 0, 0, 0, 1, and 1, 0. I'm not going to populate the entire queue, otherwise this would take all day. So that's Pacific. We'd also do the same with Atlantic. So all the positions in the board that are touching the Atlantic, so all of these values and all of these values, all of their positions are going to be added into Atlantic. So we've got 5, 5 here, 5, 4, and 4, 5. So we're just going to do the same for Atlantic. With BFS, as you probably know, we're just going to take from the top of the queue and we're going to look at this value. We're going to check all of its neighbors and carry out breadth search on them. Now, as you can see, the left side and the above arrow are out of bounds, so we need to take that into consideration. And we need to create some kind of isValid function to check whether it's in bound. So if we're outside of the board in any of the directions, so if I is less than 0, j is less than 0, I is greater than heights dot length minus 1, j is greater than height 0 dot length minus 1. All of these are out of bounds, so we just forget about those and we continue through the BFS on the other values. So can we go to 3 and can we go to 2? Well, as stated in the question, water flows from higher values to lower values, but that's getting to the Pacific and the Atlantic. So in this case, we are looking for greater values, right? Because 2 can then flow to 1, 3 can then flow to 1. So we check to see whether this value is greater than this value. If it is, then we can go down and BFS that value. And the same with 2 here. So we can go here and we can go here. So we push those values into the queue. So 0, 0, 1, and 1, 0. So here we have an issue, right? We've already got these within the queue. So if we push them into the queue, so 0, 1, 1, 0, we're going to have to visit those again. So we need to keep track of where we visited. So we're going to have to populate another array. So we're going to be creating a 2D array of the same size as this board, and we're going to initialize it with false in every position. So as soon as we take the value off the queue to visit it, we add or we update this visited array to true. So the position is set to true. So this has now been seen. So if we pop off the same value again, we can look into this visited array and see that it's already been seen, so we can continue. So we can check 2. 2 can be visited. We look at its different directions. 2 can go to 2, and it can go here because they're equal values. It can't go here. So we push these positions into queue and BFS on those. So I'm not going to go through the entire board on this. I'm just going to update this array as to what the values are supposed to be, and then we can move on to the Atlantic. It's pretty much the same process, so I'll speed up this flow. Okay, so we have shifted off of queue all the positions. We've set our visited array to true on all those positions that we've checked, and we've made sure that all of these positions can reach the Pacific Ocean. So they can reach these positions here. So these are all the values within the board that can reach those positions, okay? Now it's very much the same process for the Atlantic. So we shift off queue, we look at this position, we go to all of its neighbors, and we carry out BFS on all of those as long as those values are greater than or equal to the current value we're on. And we do that for all of the positions, and if they are a valid position, then we push that into queue, and then we shift off, push into queue, shift off. You get the idea. So what we're going to have at the end is a visited array for the Atlantic as well, and all of these values which have been changed to true can reach the Atlantic Ocean. So as you can see, we have two arrays, two visited arrays, one for Pacific Ocean, one for Atlantic Ocean. Now we have some additional logic to carry out in order to work out which positions in the board can reach both the Pacific and Atlantic. And because these boards are both the same size, we can carry out a nested for loop, passing in the board's width and height as parameters, and we can check whether the position we're on, say this position for example, is true for both this array and this array. If it is, then we can create a results array and we can add into the results array that position. So that'd be 5, 0. And we do this throughout the entire board. And what we're going to get is all the positions in the board that are both true for reaching the Pacific and Atlantic Ocean. So that's the main idea of how you'd calculate the solution, right? How you'd build out this algorithm. So time complexity for this one is going to be O of m times n, where m is the number of rows and n is the number of columns. And then space is also going to be O of m times n, where n is again the number of rows and n is the number of columns. Okay, so firstly, let's extract out the rows length and the columns length. We're going to need two queues, so we're going to have Pacific queue, which is going to be equal to an array, and Atlantic queue, which is also going to be equal to an array. Now we're going to loop through the entire board and push into the Pacific queue if the current value is touching the Pacific, and push into the Atlantic queue if the current value is touching the Atlantic. So if I is equal to 0 or j is equal to 0, then we're bordering the Pacific, so we can push into the Pacific queue that position. If I is equal to m minus 1 or j is equal to n minus 1, we're bordering the Atlantic, so we can push into the position. So now we need to carry out the bulk of the algorithm, which is the BFS. So we're going to create a function for this because we need to reuse it. We're going to pass in q. We need to state whether the value we're on is valid, or we need to make that check. So we're going to pass in x and y, so the coordinates. So if x is greater than or equal to 0, and y is greater than or equal to 0, and x is less than m, and y is less than n, therefore the position we're on is valid. We're going to have directions or deltas in order to move to the next position, so const directions, and this is going to be equal to all the directions we can take and then we need to create our visited array, which is going to be a 2D array where all values are initialized to false. And now we can start the breadth of search. So while q.length is available, we can extract out x and y. So we'll just do q.shift. We'll set that position in visited to true. And then we need to loop through the directions, right? So let dir of directions. So the directions array we created above is going to make sure that we go up, down, left, and right in our next positions. So firstly, we need to extract the next x, which is going to be current x plus directions at 0. So the 0th position, we need to extract out next y, which is going to be y plus do it at position 1. And then we need to check if that position is valid. So next X, next Y. And we also need to check if it's already within visited. So if it's either invalid or it's being visited, we can just continue. And before we push the next positions into the queue for checking for BFS, we need to check whether the height at the next position is greater than or equal to the height at the current position. So if heights at next X, next Y is greater than or equal to heights at X, Y, then we can push into queue. Next X, next Y. And then we need to return visited. So visited is going to be the array that we created. It's going to have all the true values for all the values that are bordering the Pacific, and it's also going to be another array for all the values that are bordering the Atlantic. So let's extract those. So Pacific is equal to BFS. And we're going to pass in the Pacific queue. Atlantic is going to be BFS Atlantic queue. And then finally, we need to populate a results array that match up the true values for both the Pacific and Atlantic. So let X equal 0. X is less than M. So if Pacific at XY and Atlantic at XY are both true, then we have found a match. We have found a position that can reach both the Pacific and Atlantic, so we can push that into our results array. And then we can just return result. Let's give that a go. Submit it. Given an M by N 2D binary grid, which represents a map of 1's land and 0's water, return the number of islands. So an island is surrounded by water and is formed by connecting adjacent land horizontally or vertically. You may assume all 4 edges of the grid are all surrounded by water. So we have 2 examples here. The first grid has an output of 1, so there's 1 island in here, and the island is formed by these connecting 1's. And remember, the outside of this will all be surrounded by water, so it will be surrounded by 0's. And in the second example, we have a grid with an output of 3, and that's formed from these 4 1's connecting together adjacently to create 1 island, this one on its own, which counts as an island, and these 2 connecting adjacently to form the 3rd island. So let's jump into the explanation. So we have 2 examples here. Let's start off with grid 1. So in this grid, we know that we want to be returning a number or a count, right? So we can have a count variable, which we can initially set to 0. And what we need to do is we need to loop through this grid, and we need to find a position that is equal to the string of 1. Okay, so say we started here at the first position, we have a 1. So we have an island, but we need to check its adjacent values to see whether the island or whether this piece of land is connected to other pieces of land to form a larger island. So the way that we could do this is to use DFS, recursive solution that checks all possible solutions. And with DFS, we have base cases. So in order to check all potential values, we need to go in 4 different directions, right? So we need to go up, right, down, left. But we first need to decide when to hop out of this DFS recursive call. And the first case that we can think of is if the neighboring element or the neighboring value is equal to a 0, because that signifies water, right? So if grid at I, j, so let's assume I is the row and j is the column. If grid at ij is equal to 0 as a string, then we can return out of this recursive function. Now the second base case we need to think of is if it's inbound. And what I mean by inbound is making sure that the value we're on is within this orange box, so it doesn't go out of bound. So if I is less than 0, we're going to be outside here. So I is less than 0, that's out of bound. If I is greater than this grid here, if it's greater than grid.length minus 1, then that's also out of bounds. So if I is greater than grid.length minus 1, that's also out of bound because the grid length here is 5. The index of that is 4. So if it's greater than 4, so the index of 4 would be here. If it's greater than 4, then it's out of bound on this side. And then we do the same for columns, right? So we do the same for j. So if j is less than 0, it's out of bounds up here. And if j is greater than grid at I dot length minus 1, then that's also out of bounds, and that'll be out of bounds down here. So we need to specify I so that we go down. So those are the base cases resolved. Now we can carry out the recursion, right? So we can move right, down, left, and up from this initial position. Now let's take care of these two positions. So this one is going out of bounds because I is less than 0, so that's not going to work. Going up, j is less than 0, so that's not going to work, so that's out of bound. So we know that we can go to this value and this value. So say we carried out our recursion on this value. So we go up, that's out of bounds. We go right, that works absolutely fine, so we can go there. We go down, that goes to there, that's absolutely fine. But we also go backwards. So we go back to this previous one. Now we can't allow that to happen because that's going to create an infinite loop. So what do we do in this case? Well, we could store all positions that we've looked at within a set. So we could store I and j within here. But the only issue with that is that it takes extra space. So what we could do instead is we could manipulate this grid in place. So before we move from the first position, we set this to 0. Now when we move to this position, if we go backwards, it's going to hit one of our base cases where grid at ij is equal to 0, and then it's going to hop out of that. So it's only going to check the positions that are equal to 1. And then we can carry this out. We can go to all the different positions, check everywhere. And once we hit zeros, we're going to realize we've reached all the positions where there are neighboring ones, and we're going to hop out. But we need to specify that we've hit a number of islands. So we need to specify here to return 1. And then outside of this DFS, we can increment count, because count is going to be incremented by this 1. Okay, so count is going to go to 1. And then it's going to return the answer, because it's going to check all the other possible solutions, because all of these ones are going to be reset to 0. And then it's going to check all the other positions, and they're all set to 0. And once we reach the end, pop out, return the count. And it's pretty much the same for the second example. Okay, so we start off at the first value. We go right, down. We can't go left because that's out of bounds. We can't go up because that's out of bounds. And then this is set to 0. This one can't go up because it's out of bounds. Can't go left because we've reset that to 0. Can't go right because that's at 0. But it does find a neighboring one down here. So we can do the DFS on this, and this one is going to check values as well. So here we're going to go left, right, down. There are no extra values, so this one gets set to 0. This one is going to check right, that's already set at 0, down, that's set to 0, that's out of bounds. So now we can increment our count by 1. So count is now equal to 1. While we carry on traversing the grid, we find the next position where there is 1. Here is the position. So we carry out the DFS function from here, and we recurse in all 4 directions. They're all pointing to 0, so we can hop out of this and increment count. Then we move along until we reach another 1 and do the exact same here. So we check all directions. Out of bound, 0, 0, pointing to 1, check this one. But before we do that, we set that to 0. Goes this way, can't go this way, can't go right, cannot go down, cannot go left anymore because we set the previous one to 0. So we increment count again. So that's the basic understanding of this question and how we formulate an answer. Now let's talk about time and space complexity. So with time complexity, it's O(m) by n, where m is the number of rows and n is the number of columns. And then space complexity is the exact same. In the worst case scenario, we are storing up to m by n within our stack for the DFS recursive solution. So let's start off by initializing count to 0. we need to find all the positions in the grid that are equal to 1. So let's loop through the grid. I is equal to 0, I is less than grid.length, so this is going right. J is equal to 0, j is less than grid I.length, so that's going down. So it loops through the entire grid. Now we need to check if grid at position ij is equal to the string of 1. If it is, we are going to carry out some recursive function to check all other possible positions. So DFS, we're going to pass in the grid because we need to update the grid in place. We're going to pass in I, which is going to be the rows, and j, which is going to be the columns. So let's create that function. So function DFS. So we need to pass in the grid, row, and column. So in this, first thing we do is set the base cases. So if row is less than 0, or row is greater than grid.length minus 1. So if too far to the left, too far to the right is out of bounds. Column is less than 0, or column is greater than grid.length. Sorry, grid at row.length, because we're going down, minus 1. So if too far up or too far down, that's out of bounds. And finally, grid at row column is equal to 0. So if it's water, we don't want to check that because it's not a neighboring island. If any of these are true, then we just return out of this recursive call. Next, we need to set grid at row column to equal 0. So we need to stop any further DFS calls from going back to previous positions. The way we do that is we set the current value of grid to 0. And then finally, we need to recurse in all 4 directions, up, down, left, and right. So we need to call DFS 4 times. Passing in grid, row plus 1 will go down, row minus 1 will go up, col plus 1 will go to the right, col minus 1 will go to the left. And finally, once we found all neighboring islands, we need to return 1 so that this function actually returns something. And up here, this is going to return 1. So we need to increment count by that value. So we can say count is equal to count plus DFS. And then finally, we can return count. See if this has worked. Okay, it's been accepted. Let's submit it.
So given an unsorted array of integer nums, return the length of the longest consecutive element sequence. You must write an algorithm that runs in ON time. So this question is asking for the longest consecutive sequence. So in example 1, we have the nums array 10, 4, 200, 1, 3, and 2, and the output is 4. So the longest consecutive sequence is 4 because we have 1 here, followed by 2, 3, and 4. And then in example 2, we have this nums array here, and the output is 9 because we can go from 0 to 8, which equals 9. Now if you see here, we've got 2 zeros in this array, so we need to account for that. So we need to create an algorithm that has linear time complexity, and we also need to make sure that we remove duplicates from this. So we can utilize a set data structure, which has O1 lookup, so it's optimized for looking up values. So the set will equal, which has removed the last value. So remember, a set only has unique values, so we've removed any duplications, so that will not be accounted for in our final output. So that's the first issue solved. Now we need to look at this and work out how to find a consecutive sequence with only linear time complexity. And the best way to do that is to just break the problem down. So we have 1, 2, 3, 4, we have 100, and we have 200. So we have 3 different sequences. This one has a total of 4 values, this one has a total of 1, and this one has a total of 1. Now how can we work out how to start a sequence when looping through this set? Well, one thing that all 3 of these sequences have in common is that they don't have a value to the left of it. So we can use that in our solution. So if set doesn't have nums at I, we can carry out a loop that would check to see whether the set has nums plus 1. Okay, so looping through this, we have 100. Is 99 within the set? No, it's not. So we can start a count. So we have 100. Do we have anything following it? No. So the total is 1. We move over to 4. Is 3 within the set? Yes, it is. So we carry on. We move to 200. Is 199 in the set? No. So this is a start of a new sequence. So 200, is there a value following this? So is 201 within the set? No. So we can say that the current streak for that, or the final streak for that one, is 1. Now we move on to 1. Is 0 within this set? No. So this becomes the start of a new sequence. Is 2 within the set? Yes it is. So we can add 2 onto that. Is 3 within the set? Yes it is. We can add that there. Is 4 within the set? Yes it is. Is 5 within the set? No. So we can say that the total of that sequence is 4, and then we just return this value. So before we look at the time complexity on this one, it'd be good to jump in and write out the solution to this and then discuss that.
Okay, so let's code this out. Let's create the set. Let's initialize it with nums. Let's initialize a streak. And then let's loop through that set. So let num of set, and we need to check if the set has num minus 1, so the previous number. If it does, then we can continue because that's not the start of a new sequence. Otherwise, let's create current streak and set it to 1 because we have found the start of a sequence. Then let's create a while loop. So while set has num plus 1, so while set has the next number, we increment current streak. And we also increment the number. Then once we exit this while loop, we can update streak to equal math.max compared with current streak. And then we can return streak. Okay, so let's start off this loop. So we check at 0 if the previous value is in the set. It isn't. So we start the while loop. There's no other value, so we move along. 2 doesn't have the previous value, so we start the while loop. 4 is the same, we start the while loop. And 6 is the same, we start the while loop. Now if you think about it, if the time complexity was O(n) squared, we'd loop through each value in the set for every while loop. But in this example, we have only looped through one of the values with each while loop. So that is O of n plus n, which equates to O of n. Let's take one more example. So we have the set. We check to see if 99 is in the set. It's not, so we start the while loop. 101 is not there, so we move along. 4 is 3 within the set, yes it is, so we move along. 200 is 199 in the set, no it's not, so that starts the while loop. 201 is not in the set, so we move along to 1. Is 0 in the set? No, so we can start another while loop. Is 2 in the set? Yes it is. 3 is in the set, and 4 is in the set. So in this case we started the while loop 3 times. But as you can see, with each iteration, this one only checked one value. This one only checked one value. This one checked 4 values. And that equates to the set, right? Because we have 1 plus 1 plus 4, which is 6. And the set contains 6 values. So again, it's going to be O(n) plus m, which equates to O(n). So let's check to see if that's worked. Okay, so it's been accepted. Let's submit it. Now, if you haven't seen this and get it in an interview, my condolences, this is tougher than getting a job within the current tech market. But we're going to go through it anyways. So let's start off with the problem statement. So we're given a sorted dictionary of an alien language having n words and k starting alphabets of standard dictionary. Find the order of characters in the alien language. So many orders may be possible for a particular test case. Thus, you may return any valid order and the output will be 1 if the order of the string returned by the function is correct. Otherwise, it'll be 0. So in our first example, we have this dictionary and we know the words in this sequence are ordered. We need to return the order of characters for this dictionary. So let's try and suss this out. So here we have our alien dictionary. We know that this dictionary, the words in it are ordered sequentially. So this word comes before this, comes before this, comes before this, comes before this within this dictionary. But we do not know the ordering of the characters and we need to suss that out. So let's take it back to the basics. Let's say we have these words. And just for argument's sake, this is using the normal alphabet, A to Z. But let's assume we don't know that. How would we go about solving this? Well, we know that these are ordered based on the words. So to get the ordering of the characters, what we're going to do is compare 2 of the words' characters. And we're going to iterate through both of them and compare until we find a differentiating character. So initially we compare A and A. These 2 are the same, so they cancel out. Then we move over to B and C. These are differentiating characters. So we can assume that B comes before C here. And that would make sense because this is A to Z. Then we assess the next 2 words. So we look at each character within those words. The A's cancel out. We hit C and D. These are different, so we can assume that C comes before D. Makes sense because this falls in A to Z. Then we compare the last two words. So the A's cancel out, the D's cancel out. The last one's D and E. D is different to E. So we can assume that D is before E. So within this, B comes before C comes before D, and D comes before E, which all fits within our alphabet. We know that these words are sorted, but we don't know the corresponding order of the characters. So let's follow the exact same process that we just used to calculate it. So we look at the first two words. We look for characters that are different. So B and A are different. So for this, we can assume B comes before A within this alien dictionary because we know that these words are ordered, so we just need to compare the characters. Then we move to the next two words. The A's cancel out, B's cancel out, C's cancel out, D and A are different. So D also comes before A. Then we look at the next two. Immediately we can see A and C are different, so A comes before C. And the last two words, C and A both cancel out, and we can see that B comes before D. So when running through this and calculating the orders of characters, we can see that consecutive words gives us a piece of information about the ordering of these characters and their dependencies. So in order to get to A, you first need to go to B. In order to get to D, you first need to go to B. And in order to get to C, well, you first need to go to B to A to C, or B to D to A to C. Right, so there is a well-defined order with these characters, indicating that there shouldn't be any type of cycle, and that should be a hint as to what type of data structure we're going to use. Based on the looks of this and the fact that there aren't any cycles, we should consider each character to be a node, and each edge between these nodes to represent the dependencies we've just calculated from this dictionary up here. So this becomes an ordering problem within a directed acyclic graph, a DAG. And this should lead you to using topological sort. So let's see how we can implement that. So we have our dictionary. Now we're going to be creating a graph from this, and in order to create a graph, we usually have an adjacency list that we need to populate based on the characters here and their dependencies. So for example, we know that B comes before A within this sequence, so B is going to be mapped to A as one of the dependencies. Now we can also see down here that B comes before D as well, so we can include D in here. So at the end of it, our adjacency list is going to look like this. So we loop over each word and each character within the words and map it to its individual dependencies. So B must come before A and D, A must come before C, and D must come before A. C, however, doesn't have any dependencies. Once we've created the adjacency list, then we can look at implementing topological sort. And we're going to be using depth of search for this. So what do we need in order to carry out topological sort? Well, we need a couple things. Firstly, we need to keep track of the state. So essentially what this means is for every node or for every character within this adjacency list, we need to monitor its state, whether we've seen it or not seen it, or we are currently seeing it. And this will allow us to determine whether there's a cycle in the list, because if there is a cycle, well, that doesn't fit our criteria for this question. So we need to return something like an empty string. We also need to populate a result array, and we can carry this out within the DFS recursive call. So let's walk through the process. Like we said, we're going to have 3 states. So all the characters initially are going to be unvisited. We also need to populate the result array. So let's add that down here. So let's start this process. So initially we have B. Let's first move B into visiting. Now in order to visit B fully and process it as visited, we need to first check its dependencies. And this is a DFS recursive call. So let's start off with A. We move A into visiting because B has the dependency of A. Now we're in A. A has the dependency C. So we're going to make the recursive call into C. So that's been moved into visiting. Now as you can see, C doesn't have any dependencies. So we can mark this as visited and add C into our result. So we go back up the call stack. So back to A, we check if A has any other dependencies. No, it doesn't. So we can also mark this as visited and include that within result array. Repeat the process. A doesn't have any other characters to look at. So we go back up the call stack. We go to B, check if this has any other dependencies. Well, we've seen A, we now move on to D because D is unvisited. So let's move D over to visiting. So we go into D within the adjacency list. We can see that A is a dependency of D. So we look at A. A state is visited. It's fully complete. So at this stage, we don't even need to look at this. So this will be one of the base cases within our DFS recursive call. If the state is visited, we know that it's been fully processed. So we can exit from this immediately. D has no other dependencies, so we can mark that as visited and add D within our result array. Finally, we go back up to B. We've checked all the dependencies, and we can move B over to visited and add that within our result array. And this is exactly what we expect from topological sort. But as you can see, the results are slightly different from the solution in the problem statement, right? So we're expecting BDAC. So all we need to do now is just reverse the result. And this is going to give us the correct answer of BDAC. So time complexity for this, well, we have two main areas, right? We have the construction of the graph, and we also have topological sort. So in order to construct the graph, well, we have, say, an average length of words, which is L. So we have O, L. We also have n number of words. So it's going to be O, L times n. And in regards to topological sort, in the worst case, we're going to have to visit each character and traverse each edge in the graph, which is going to be K plus E. And then in regards to space, it's also going to be OK plus E. Now let's hop into the code editor and flesh this one out. Okay, so like we said in the walkthrough, the first thing we need to do is initialize the adjacency list. So let's go ahead and do that. So it's going to be a plain object. Let's loop through each word within our dictionary. And then for each character of the word, let's say if we don't have that character within our adjacency list, then let's add it in and assign a set to it. So at this point, we're going to have something that looks like this, right? So for each character within our dictionary, we've assigned a set to it. Simple enough. Now we need to build the graph, and we'll build it based on our given dictionary. So we need to loop through the dictionary. We're going to go up to dictionary.length -1. So by going up to dictionary.length -1, we only include the comparison of these two words as the last comparison, right? We don't go as far as comparing CAD to undefined. Then we need to grab both words. So that word 1 is going to be equal to dictionary at I, and word 2 is going to be dictionary at I plus 1. Simple enough, we've grabbed both the words. Now we need to ensure that we only compare the characters of the smallest word with the longest word. So we need to get the minimum length, and that's going to be math.min. It's going to be word1.length and word2.length. Now we can compare the characters of adjacent words and look for differentials, and then add their dependencies within our adjacency list. So let's go ahead and do that. So j is equal to 0, j is less than min length. So if word 1 at j, so the character in word 1 is different to the character in word 2, well then let's update our adjacency list. And let's say adjacency at the character in word 1, and we're simply going to add the character in word 2 to that. So this is now a dependency of this. And then we can break early from this. So once this is done, we'll have the adjacency list from earlier that looks like this. And now we need to perform topological sort on this adjacency list. So let's first declare our DFS function. We're passing in the character because that's what we're going to be looking at. And we need a few things first before we do this. We said we're going to be looking at the state here. So we need to keep track of that. So let's create an object called state. We also need to populate a result array. And just to keep this code clean, let's create a constant called visit state. And let's create a couple states. So visiting, which is going to be 1, visited, which is going to be 2. In our solution, we don't actually need unvisited because this should be state. If this state object doesn't have the character within it, it just means it's unvisited. Okay, so now let's fill out this DFS function. Initially, we need to check for a cycle. And the way we do that is by checking the state of that character. If it's in visiting, then we have found a loop. We have found a cycle. So if state at the current character we're on contains the visiting state, so the value of 1, then we can return true, right, to indicate that there is a cycle. We also need an early escape if we've already visited the character. So let's go ahead and add that in. So if this is equal to the state of visited, we can return false, indicating that there's no cycle, and exiting early from this. Otherwise, we're going to update the state of the character that we're currently on to visiting. And then just like we did in the example, we're going to be carrying out that recursive call. So we're going to be checking every other dependency. So the neighbor of the current node we're currently on. Let neighbor character of the current node we're on. And if DFS at that neighbor returns true, well, then we know that there is a cycle present here. So we return true from this to propagate that up to where we call the DFS function. If we don't hit that true, then we know that this is a valid option, and we can update the state of the current character to equal visited. Mark it as visited, then we can push into result that character. And just to ensure that we return a boolean from this, we can return false, indicating that we haven't found a cycle. Okay, so that's the DFS function sorted. All we need to do now is loop through the characters within the adjacency list, and if it's unvisited, so state at character is not present, and then we perform the DFS recursive call on that character, and this returns true, well, we have that cycle we were talking about. So we need to return an empty string here. So at the end of this loop, we should have something that looks like this for the first example. So the state for every single character is set to visited, so 2, and then our result array is the correct answer backwards. So all that's left to do, you can create your own reverse function, but I'm just going to use the inbuilt reverse method for simplicity. And then like we said within the problem statement, this needs to return a string. So let's join this array in order to form a string. Right, so let's recap over this very quickly. Initially, we created the adjacency list. We assigned a set to each of those characters. Then we built the graph using the dictionary, right? So we associated dependencies to every single node or every single character within this. Then we carried out topological sort with the use of DFS. Finally, reversing and joining the result in order to form the string. So let's submit this. So we have this graph from nodes 0 to n-1, and we have edges between each node, A and B, and this is an undirected edge. So all we need to do is return true if the edges provided within this tree create a valid tree, otherwise we return false. So this is a bog standard graph traversal question, and we are checking for a cycle. So you can see in example 1, we have this tree. It's going to return true because there aren't any cycles. We have this example, example 2, there is a cycle here that we can see, so this is going to return false. So let's work out how we solve this. So with any graph question, we usually have to populate an adjacency list, and this is going to contain the current node and all of the adjacent nodes that it's connected to. So this is going to be 1, 2, 3 for 0. 1 is going to be connected to 0 and 4. Remember, it's undirected, so it goes both ways. 2 is connected to 0. And 3 is also connected to 0. Now we need to check for a cycle within this. So it would make sense to have a visited set to keep track of all the nodes we have visited. And let's run through the traversal, right? So if we start at the root node, okay, we're at 0. This adds 0 into visited. Okay, so we visited it. Now we look at its neighbors. So let's first look at 1. So we recursively call 1. We add 1 into visited. Now we look at the neighbors of 1. We've got 0. So we go back to 0. We check in visited whether there is a 0. 0 is present. We have a problem, right? Because we know that this is a valid tree. However, if we're just checking to see whether the current node that we're on is within visited, this is going to return us the wrong answer. So how do we cover this? How do we stop this from occurring? Well, before we go down to 1, we need to pass something. And what we're going to pass down is the parent, and the parent is going to be equal to 0. So now when we check the neighbors, so if we check 0, if the visited set contains the neighbor that we want to look at, as long as the neighbor is equal to the parent, there is no cycle. So then we look at 4, right? So 1 goes to 4, 1 passes down in the recursive call to 4, the parent, which is going to be 1. At 4, we add 4 into visited. 4, which I forgot to add into the adjacency list, is connected to 1. If 1 is found within the visited set, but the neighbor is equal to the parent, then there isn't a cycle. So if there's not a cycle, we've checked 4, we can pass back up the recursive call false, right? Because there isn't a cycle. At 1, we've checked all the neighbors, there isn't a cycle, so we pass up false. Then at 0, we can recurse down to 2, passing down the parent of 0. 2 is added to the visited set. We look at 2's neighbors. 0 is within visited, but the neighbor of 0 is equal to the parent, so there is no cycle. So we can return false from this. Then we look at 0's last neighbor, 3. We pass down the parent of 0, so we add 3 into visited. We check 3's neighbors, so 0 is within visited, but the neighbor of 0 is equal to the parent of 0. So just like before, there isn't a cycle here, so we can return up false. So we've checked all the values, and from this we can return false. And if this returns false, then we know that we have a valid tree. There is just one other check which we haven't taken into account. Say we have this tree, but we also have this as well. So we have a disjointed set, right? There are 2 separate trees. Now, how are we going to check for this? Well, after we've made the check to see whether this is the valid tree, what we need to do is look at the length of the visited set, right? If the length of the visited set is equal to the number of nodes within this tree, then we have a valid tree. If it's not, well then there is a disjointed set, so we return false. So let's discuss the time complexity. For this one, it's going to be O n plus e, where n is the number of nodes that we traverse through within this tree, and e is the number of edges between those nodes. And space is also going to be O n plus e. So let's start this off by creating the adjacency list. When creating the adjacency list, we're going to loop through all the values up to n, and we're going to set adjacency list at I equal to an empty array because we want to include the 0th element in this. Then we can create the connection. So if we loop through a and b of edges, we can set adjacency list at a by pushing in the value of b, and we can do the same for b. so that's the adjacency list created. Now we need to check for a cycle. So if check cycle, so this is going to be the function that we're going to create, passing in the current index, so the current index is always going to start at 0, and the parent, so at 0, the parent is going to be -1. If there is a cycle, we can return false. Right, so let's create this function. So function check cycle. We're going to pass in the current, and we're also going to pass in the parent. We need to create a visited set, so that visited equal new set. Now we can add to the visited set the value of current. Then we can grab the neighbors, so neighbors is going to be the values in the adjacency list at key of current. If there are neighbors, then we're going to loop through those neighbors. We're going to check if visited has a neighbor. So we're going to check for a cycle, but there is that edge case if visited has the neighbor, but the neighbor is equal to the parent, right? So if neighbor doesn't equal parent, right, then there is a cycle, so we return true. Else, if neighbor is found within visited, but the neighbor is equal to the parent, there isn't a cycle, so we just recurse through this. So we check the cycle, pass in neighbor and current as the new parent. If this returns true, then there is a cycle, so we return true from this. Otherwise, if this process completes, we return false, so there is no cycle. Now we need to check if there is a disjointed set, if there are two graphs. And to do that, we loop through from 0 to n. We're going to check if visited has I. So if visited has the index, then we're going to check if visited doesn't have the index. If it doesn't, then we know that there is more than one graph here, so we return false. If that checks out, we can return true because there is a valid graph. Let's give this a run. Submit it. So in this question, you're given a graph of n nodes. You are given an integer n and an array edges, where edges equals a, b, indicates that there is an edge between a and b in the graph. Return the number of connected components in the graph. So this question is pretty intuitive, right? We need to work out the number of connected components within the graph, right? And within this solution, or within this example here, we have two connected components. We have 0, 1, 2, and 3, and 4, right? So this right here is one connected component, but then we have another connected component here because there is a disjoint between the two. Okay, so there is 2 here, and we just need to return that output. So we need to return the count of the number of components here, which is 2. So let's discuss how we would solve this problem. With this graph, we are going to be using depth first search, and it's a simple case of keeping a count variable, which initially will be set to 0. And the most difficult part is deciding how we're going to run this DFS. So we need to run it on a particular section of information, which we don't have at this point in time. So we have edges up here, which at this moment is pretty useless. So what we can do is convert this into an adjacency list, right? And what this is going to do is it's for every node within this graph, it's going to point to its neighbors. So each node is going to be the key, and the neighbors are going to be the edges, or the neighbors are going to be the values, right? So in this adjacency list, we're going to have something that looks like this. We're going to have 0, which points to 1. We're going to have 1, which points to 0 and 2, 2, which points to 1, 3, which points to 4, and 4, which points to 3. Great, so we have made this adjacency list. Now what we can do is with DFS is we can loop through the keys of this adjacency list. So what's going to happen is we're going to loop through the keys. So we're going to start off at 0. We're going to look at its neighbors, which is 1. With 1, we're going to look at its neighbors, which at this moment in time is 2 and 0. And as you can see right here, we have an issue. We're going back to 0. So we need something like a visited set, which is going to store each node we visit so that we don't go back and create some kind of infinite loop. So at 0, at the first point, we are going to check whether this node is within visited. If it is, we're just going to return because we have already visited this one. But in this case, it's not, so we can add it into the visited set and then we can check the neighbors. So we can repeat this process, right? So we can go to 1. So we're at 1 now. We check the neighbors, or actually first, we check if it's within visited. It's not, so we can add it to the visited set. We check its neighbors. It goes back to 0. 0 is within visited, so that can be cancelled. We can just return that. And then we go down to 2, right? So we check 2. 2 is not in visited, so we add it. Now we go back to 1 because 1 is a neighbor, 1 is in visited, so that gets cancelled. And now we have finished the DFS on 2. So we can return 1 as a count, right? So we can return 1 up here. This will return 1 to 0. And the DFS on this is going to be equal to 1. So we just append that to count. So we increment count to 1. Then as we said, we're looping through these keys. So we go over to 1, we check 1. 1 is within visited, so we can just return out of that. 2, again, is within visited, so we can hop out of that. 3, we start the DFS on 3. So we check if that's in visited. It's not, so we can add it. Check its neighbors, so go to 4. 4 is not in visited, so add it. Check the neighbors, so we go back to 3. 3 is in visited, so that gets cancelled. And then we're at the end of the DFS function at 4, 4. So we can return 1 to 3, and then that can return 1. So the DFS function of this connected component right here is going to be 1 as well. So we can append that to count. And then we have to loop through 4. So we go to 4, we realize that's in the visited set, so we hop out of that. Don't return anything, don't increment count. Then we have visited each key within the adjacency list, and we can just return count. Pretty straightforward question. Time complexity for this one is going to be OE plus V, because we have to traverse through each edge exactly once, and again we have to visit each vertice exactly once. And space is also going to be OE plus V, because building the adjacency list is going to take E operations, and also with DFS you use the recursive call stack, which is going to be V. So let's initialize count to 0. Let's initialize the kind of adjacency list, which we'll call graph, and we'll initialize each value within that graph to an empty array before populating it. So I is equal to 0, I is less than n, I plus plus, and then graph at I is equal to an empty array. Then we just need to loop through UV of edges. So graph at U, push the neighbor of V, graph at V, push the neighbor of U. And remember, this is an undirected graph, so we have to push in both neighbors in both directions. So U has to push in V, V has to push in U. Then we create the visited set, so visited equals new set. And as we said in the explanation, we have to loop through the keys of the adjacency list. So key in graph, which will get us the keys, and we increment to count DFS of key. DFS of key. So let's create the DFS function. So DFS is going to take in node. We're going to check if visited has node. If it does, we can just return 0, right? Because that's already a visited set, we've already visited it, so we don't have to look through this again, so we can just return 0. So otherwise, we need to add the node to visited. So visited dot add, and we're going to add node. Then we need to loop through the neighbors of graph of the adjacency list at position node, and then DFS the neighbors. Once that's occurred, we can return 1. Now there is a little gotcha in this question, and that is that if we loop through the keys of the adjacency list of graph, these are going to be in string, so we need to convert it to an integer. So key is going to be equal to pass int key, because otherwise visited is not going to recognize node, which is going to be a string. Okay, so we need to convert it to an integer in order so that we can increment count and the DFS runs correctly. And then finally, we can just return count. Okay, let's give that a run. Let's submit it. So you're given an array of k linked lists called lists. Each linked list is sorted in ascending order. Merge all the linked lists into one sorted linked list and return it. So in the example, we have an array of arrays containing a number of lists, and we just want to have an output that merges all of those lists together in ascending order. Okay, so the idea behind this question is pretty straightforward. The implementation, however, is a bit more tricky. So there are a number of ways you can do this, and they all kind of revolve around the same kind of time complexity. We have a brute force approach where we just create an array from these lists, and then we use a rudimental sorting algorithm and populate a new sorted list, which will give time complexity of n log n. Or we could use a merge sort, which is what we're going to be doing today. So a merge sort is a divide and conquer sorting algorithm. I'll add a link to the merge sort. And what this does, rather than creating an entire list and sorting that individual list, we're going to merge two of these lists. So say we merge these two, which is given to one list. And then with this list, what we're going to do is we're going to merge it with this one, which is going to give us the final list, which we can return as the output. So this with this will give us, and then this compared with this. So there are two parts to this question. Firstly, we need a function which is going to grab these two lists and merge them. And then we're going to have another function which is actually going to carry out the merging. So the time complexity for this one, if you know, merge sort is going to be on log k. So with the operations of the merging, we're dividing by 2 roughly each time, and there's going to be n operations. So there's not much to this explanation, but if we dive into the code, I'll show you how it's implemented and it will become a lot more clearer. So firstly, we need to say if the length of lists is equal to 0, return null, because there's no lists to be merged. And while the list's length is greater than 1, we have 2 lists that we can merge. So we need to grab both of those. So that list1 equal lists.shift. So we can just grab the first one. And also we need to grab a second one. Now we need to merge these two lists. So we're going to create a separate function for that. We're going to pass in list1 and list2. And then we need to add into the lists the merged value. So we update the list. We've subtracted 2 lists from the current list. We've merged them. And then we need to update the list with that merged list. And then because it's going to be an array of arrays, we need to return lists at 0. So this is the merge sort. Now we actually need to create the merge list function. So if you want an in-depth discussion on how merge list is implemented, I'll leave a link in the description to the video where I discuss that. But for now, I'm just going to run through it very quickly. So we create a dummy node, which can be initialized to any old value. We create a head, which is used as a reference and it will be set to dummy. Then we start the while loop and compare the two lists. So while list1 and list2 are not equal to null, if list1's value is less than or equal to list2's value, we're going to set the next value of dummy, the next property of dummy, to equal list1. We need to move list1 to its next value. Else, we do the same, but for list2. And then we also need to update dummy to dummy.next, because we need to add the next value from one of these lists to the tail of dummy. And then outside of this while loop, we've reached the endpoint of one of the lists, so one of the lists is equal to null. So what we need to do now is we need to append to dummy the rest of the list that is not equal to null. So if list1 is equal to null, dummy.next is equal to list2. Else, dummy.next will be equal to list1. And then finally, we can return head.next, so the reference that we created at the start. Let's give that a run. Dummy is not defined. Okay, so there's a spell mistake. Let's run it again. Let's submit it. So you're given an integer array nums and an integer k. Return the k most frequent elements. You may return the answer in any order. So in example 1, we have a nums array and we have k, which is set to 2. So we need to return the k most frequent elements within the nums array. And as you can see, the output is 1, 2, and that's clearly because 1 has a frequency of 3 and 2 has a frequency of 2. Now, if k was equal to 3, then 3 would be added into the output because that would be k most frequent elements. Now, if we look at the follow-up, time complexity must be better than O n log n, where n is the array's size. So let's work out a solution for this. So the naive approach would be to create a frequency map. And by frequency map, I just mean an object which is going to contain each number and its frequency. So the amount of times it's occurred. So 1 is going to be to 3, 2 will be to 2, 3 will be to 1, and 6 will also be to 1. Then we could essentially loop through this object k times and push into result the largest value. So the first loop, we'd push in this value right here. We'd push in the key into results. We'd delete this from the object. Then we'd look and find the second largest value, which would be this one. So we push in the key for that. And once k is equal to 0, we can exit that and just return the result array. Either that, or we could simply sort it and then return the 2 highest values. And this will have a time complexity of k log n. So how can we do this more efficiently? So if we want to have O n time complexity and space complexity, we can utilize what's called bucket sort. Now this is just a simple sorting algorithm where we bucket the frequency as the kind of key of the bucket, and then within each key we can add into the bucket or an array, we can push in these values right here. So the numbers that occur X amount of times. So let me show you what I mean by that. So we have the count index as the keys. How many of these values occur 0 times? Well, that's going to be empty. How many occur 1 time? So you've got 3 and 6, so we can add that to the bucket of key 1. So 3 and 6. 2 occurs 2 times, and 1 occurs 3 times. Then it's just a simple case of looping through this bucket backwards and add into results the nums k times. So we add 1 into results, k is decremented to 1, and then we add 2 into results, k is decremented. Then we can just return this value. There is, however, a slight edge case here. Say, for example, we had 5 1s. So rather than 1 being here, we'd have 4 and 5. 1 would be in here. In order to get the top 2 most frequent elements, we'd have to loop through this backwards, but we'd also have to check whether there is a value within the bucket at particular indexes. We can add 1 into results straight away from 5, but then when we get to 4, this is going to be empty. So we need to make that additional check to see whether there is actually something within the bucket array. And that's basically it, running at O n time complexity and space complexity. So let's initialize the map, which is going to be an object, the bucket and result, which are both going to be arrays. We'll create the frequency map. So we're going to loop through nums. If map doesn't have nums at I, then map nums at I can be equal to 1. Else we're just going to increment that position in map. So map nums at I plus plus. Now in order to populate the bucket, we're going to have to loop through the map. So let num and frequency of object.entries pass in map. So if the bucket at frequency cannot be found, then we can set the bucket at frequency. And what I'm going to do is store it as a set where we add the number to that set. So we need to initialize the set before adding a number to it. Else bucket frequency is going to be equal to bucket frequency, and then we're just going to add that number to it. Then we need to loop through the bucket backwards. So I is equal to the last value in the bucket. So bucket.length minus 1, I is greater than or equal to 0. I minus minus. If we find a bucket at position I, we push into results a copy of bucket at I. The reason we create a copy is because we do not want to update the bucket array. If result.length is equal to k, then we can break, right? So we found 2 of the most frequent elements. We've pushed it into results. We can break from this now and just return result. Let's run it. So the median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value. And the median is the mean of the two middle values. So we have two examples here. We have 2, 3, and 4. The median is going to be 3, right? So it's going to be the middle value because this array is odd length. With even lengths, we just add up the two values or the two middle values and then divide by 2, right? So we need to build out a class called median finder. And then we're going to add methods to this, one called addNum, which is going to add a number into this class, one called addNum, which is going to add the number into this median finder object, and lastly, we have findMedian method, which is going to find the median within this median finder object. So let's start off with an array, right? That's what we're going to initialize this class to. We need to add numbers in here. Say we have 1 and 3 already in this array. What is the most intuitive way of finding the position to insert an integer into an array with log n time complexity? Well, it's going to be using binary search, right? So we're going to use binary search to find the position in order to add a value. Say the value is 2. We're going to have a left pointer, we're going to have a right pointer, and we're going to have a middle value. And if this middle value that we calculate from adding these two together and dividing by 2, if that is equal to the value, then we can slot it in there. Otherwise, if it's less than this number, then we're going to increase the left pointer, right? So the left pointer would move to mid plus 1. Otherwise, if the middle value is greater than this number, well, we know that it's not going to be in the right side. So we are going to move the right pointer to mid minus 1. And then in order to insert this value within the array, we're going to have to splice it in. Now, this is the only drawback to this solution, is that we are going to be using slice to insert the value. So it's not just going to be log n time complexity, it will probably be k log n, right? Because we are going to be splicing. Next is finding the median. And there are two ways that were stated in the question. There's an approach where the length of the array is even, and there is an approach where the length of the array is odd. Now, if it's even, we need to find the two middle values within the array. So we can calculate the middle value by simply doing array.length divide by 2. So this grabs us the middle value. So say we have an array of 1, 2, 3, and 4. So this is going to grab us this value here, 3. We also need 2 here. So we're going to have that value as well. And we can just grab it by saying this value minus 1. And then we can just add these two together and divide by 2. So it's going to be 5 divided by 2, which is going to give us 2.5. And then with odd length arrays, it's even more simple. We're just going to calculate the middle value. So in this example up here, the middle value is going to be 2. So we're going to do r.length divide by 2. And we'll have to floor this as well, right? So it'll be math.floor r.length divided by 2. This is going to give us the index of 1, and that is going to be pointed to 2, right? So then we can just return that value within the array. So this will be running in O1 time complexity. Okay, so let's dive into the code. So for the median finder, we're going to initialize the array. So have it equal to an array. Then within the addNum method, we're going to initialize left and right because we are using binary search. So it's going to be this.r.length minus 1. And then while left is less than or equal to right, we're going to get the middle. So the middle is going to be math.floor, right plus left, divide by 2. Great, so we have the mid. Now we need to work out whether we need to shift the left pointer or the right pointer. So if this r at mid, so the middle value, if that is less than num, we know that it's not going to be in the left side, right? So we can shift the left pointer to mid plus 1. Else, if the value within the middle of the array is greater than num, we know that it's not going to be in the right side of the array. So we can shift that to mid minus 1. And then we have to splice it. So we're going to splice this, which does slightly increase the time complexity. Right, so this .r.splice, the first parameter we pass in is the index. Right, so we're going to be passing in a value at this index. The second parameter passed in is how many items we need to remove. We're not going to be removing any, we're just inserting here. So this can stay as 0. And then the third param is going to be what we are inserting. So that's the addNum method sorted. Then for find median, it's pretty straightforward. We just need to work out whether the array length is odd or even. We can use the %sign to. If this is equal to 0, then we have an even array. So then we can work out the mid, right? So let mid equal this dot r.length divided by 2. Then we need to add this.r mid with this.r mid minus 1, right? Because as it says in the question statement, if the list is even, the median is the mean of the two middle values. So we have the two middle values here. We're going to divide that by 2 to get the median, and we're going to return this. Else, we have an odd length array. So we just need to work out the mid, which is going to be math.floor. This.r.length divided by 2. And then we just return this.array at that middle value. Okay, so let's go ahead and give this a run. It's been accepted, let's submit it. So you're given an array of non-overlapping intervals where interval I is equal to start I, end I. Represent the start and the end of the ith interval, and intervals is sorted in ascending order by start I. You're also given an interval, new interval, which is equal to start and end, that represents the start and end of another interval. So insert new interval into intervals such that intervals is still sorted in ascending order by start, and intervals still does not have any overlapping intervals. Return intervals after the insertion. Okay, so in this question, we just need to find if there is an overlap between the new interval and the intervals, and we need to insert it into the correct order, removing that interval. So we need to merge potential intervals that are overlapping. So here we have 1, 3, and 6, 9, and the new interval is 2, 5, and the output is 1, 5, 6, 9. The reason for that is 1, 3, and 2, 5 are overlapping, so we take the smallest from both of them, which is 1, as the first value, and we take the largest, 5, as the second value. So it's 1, 5, 6, 9. And in example 2, we have this intervals array here, and the new interval is 4 and 8, and this is going to overlap with 3 and 5, because 4 is greater than 3, but less than 5. It's going to overlap with 6 and 7, because 6 and 7 can be found within 4 and 8. It's also going to overlap with 8 and 10. So like all the other interval questions, we need to start by drawing out the intervals to give us a visual representation. Okay, so this is what we currently have. We have 1 to 3, we have 6 to 9, and we also have the new interval as 2 to 5. And we need to insert this and remove all overlaps. As you can see, there is clearly an overlap here, right? So this is where the merge will need to be. But before we even do this, firstly, we already know that the array is sorted, so there's no need to sort this. Secondly, let's carry out, say, an edge case. Say we have an interval that is, say, -1 to 1. Do we need to merge this with anything? No, because there is no overlap with the new interval that is here. So we can just insert this into our result array. So let's say we have the result array down here. If, for example, the last value, so we have start and end. So if end at this interval is less than start at the new interval that we're going to be inserting, then we can just insert this interval. So that'll be a potential edge case, right? Now we can focus on merging these two. So there is an overlap here. We have current with start and end. We have new interval, which we'll call new I, start and end. And if current start is less than new interval end, because remember, we've already covered that base case where the end value of the current interval is less than start, we'll just push that into res. So we don't need to look at the end value now. We just are concerned with the start value of current. So we check the start value of current against the end value of the new interval. If it's less than, then we need to update this new interval to equal the minimum between the current start and the new interval start, and that will be the left value, so that will be 1. And then we also need to compare the end values of the two, and that will be the second value. So that's going to be 5. Now, before we push this into res, we need to compare, or we need to look at the second interval here. So this is going to be the new current. We're going to have start and end. We're going to check if interval at start is less than new interval at end. It's not. So based on that condition, we can push this into results. So 1 and 5. Okay, because there is no overlap here, we don't have to worry about that. Then all we need to do, if that is the case, is just loop through the rest of the current array. So loop through the rest of this array and add whatever is left into res. So that's just going to be 6 and 9. Okay, let's look at the second example. So let's draw this out. With this, let's populate the result array. So we said that if intervals at end, so the current interval we're on, is less than the new interval at start, then we can just add it into the result array. So we can add 1 and 2 directly into the result array. So we don't have to worry about that. So that has now been seen. We move on to 3 and 5. End is not less than start. So we check the start to see if it's less than end. In this case, it is. So start is at 3. The end of the new interval is at 8. The start is less than the end. So we can create a merge from this. So we take this value from the start because it's the smallest between the two, and we take this value from the end because it's the largest of the two. So let's just expand this out now. So this is what the current new interval looks like. We're going to update the new interval over here as well. So it's going to be 3 to 8. We've now seen this one, so we can remove that. Okay, so we move on to the next one. Is the start of this value less than the end of this value? Yes, it is. And we have an overlap because the end here is greater than the start over here. So again, we're going to update the start and end based on this information. So the start is going to be the smallest of the two, so it's going to stay as this value, so as 3, and the end is going to be the largest of the two. So it's going to stay as 8 as well. So we've seen this interval now, so we can remove it. Okay, now we're on this interval, so we have start and end. Is end greater than the start of the new interval? Yes, it is. So we check the start. Is start less than the end? No, it's not. But this right here at the same value at 8 is still classed as an overlap. So what we'll do is we'll call this current. So if current at start is less than, is what we've been going with up until now, or equal to new interval at end, then we update new interval. So we need to make sure that we're checking for the less than or equal to in this case. We have an overlap, so we're going to update the start value and we're also going to update the end value. So the start value is going to be the smallest of these two, which is already 3, and the end value is going to be the largest of these two, which is going to be 10. So we can expand this now, expand that outwards. We have now seen this, and now we move on to the last interval. So we'll call this current, start, and end. Is current end less than the start of the new interval? No, it's not. So we check, is current at start less than or equal to new interval at end? No, it's not. All we do now is push new interval into results, 3 and 10, and then we push current into results, which is 12 and 16. And that is the final output that we're looking for. Time complexity for this algorithm is going to be O of n because we have one while loop which we're traversing through a number of times, and then space is going to be O1. Even though we're using this result array to populate our output, it's considered the output, so we class it as O1. So let's write this out. So res is equal to an empty array. We're going to utilize while loops throughout this, so we're going to have an index which we start off at 0. We're going to initialize start as 0 and end as 1 to make this more readable. And then while I is less than intervals dot length, so it's inbound, and intervals at I end is less than new interval at start, we're going to push into res intervals at I and then increment I. Because there is no overlap between the current interval and the new interval, we just push this interval within res. Then we'll have another while loop. So while I is less than intervals dot length and intervals at I start, so the start value is less than or equal to new interval at end, then in this case we have an overlap, so we need to merge the two. So we're going to merge new interval. So we're going to say the new interval at start is going to be equal to math.min new interval at start and intervals I start. So we're comparing the two start values and we're grabbing the smallest. And then we also need to update the end value, which is going to be the maximum between the two. and then we just need to increment I again. So once we've looped through all the intervals where the starting value of the intervals is less than or equal to the end value of the new intervals, once we've exited all of those, we can just push into results, new interval. And then there may be some intervals still left within the intervals array that we haven't considered or we haven't checked yet. So we need another while loop just to push in the rest of these intervals into results. And then we can return res. Okay, let's run this. Okay, so there's a spell mistake. Let's give it another try. Submit it. So given an array of intervals where interval I equals start to end, merge all overlapping intervals and return an array of the non-overlapping intervals that cover all the intervals in the input. So with example 1, we have 1, 3, 2, 6, 8, 10, 15, and 18. And our output is 1, 6, 8, 10, 15, and 18. So we've merged 1, 3, and 2, 6. And the reason for this is because there is an overlap between the two arrays. So 3 here is greater than 2, which is in the next array. So we have to merge and take the smallest from the first and the largest from the second. And then in example 2, we have 1, 4, and 4, 5, and the output is 1, 5. So if the value in the first array, if its second value is equal to the first value in the second array, essentially there is an overlap. So the best way to understand this problem and to formulate a solution is to definitely draw this out so you can get a visual representation of the intervals and what's going on. So let's draw this out. So we have 1 through 3 as one interval. We have 2 to 6 as another interval. We have 8 to 10, and finally 10 to 12. So these are our intervals, right? We have, as you can see, an overlap between this point, and also this point and this point, because remember, if the two values are equal, then that is classed as an overlap. So those are the two areas that we'll be needing to do some conditional logic in order to create a merge between the two different intervals. So we're going to need a results array, which we're going to populate and pass in the answers. And we are initially going to set the result array with the initial array. And as you can see, the initial array that we're going to be looping through is already sorted. But in the case of this question, there may be an issue where they're not sorted, in which case our first step would be to sort this array to make sure that it's in order so that we can see where the intervals are exactly. So we've created this result array. We've passed in 1, 3, so the first array within it, and this is going to be called previous. Okay, so we're going to call this previous now because we've already checked it. We have a start and an end within that interval, and we have a start and an end within the next interval. So we're going to call this second interval current. So as we said, we have an overlap here. And the reason for this overlap is that this value right here is less than this value here. So we can say if current, actually, what I'll do is I'll call this prev, I'll call this current. So if current at start, so if this value right here is less than previous at end, and remember, in this case right here, we have an overlap and those values are equal, so we have to say is less than or equal to previous at end. Then what we need to do is we need to update this interval in order to accommodate this interval. And the way we'll do that is we'll reassign previous end to equal the max between previous end and current end. So the previous end will now be 6. So this will be our new previous value. Previous down here, which is in the results, will update. So I go to 1, 6. And I say it's the maximum between previous and current value, just in case. So say, for example, the previous initially was this. It was 1 through 7. In this case, we have an overlap, but the previous end value, so this is previous at the minute, the previous end value is already greater than current end. So we take the maximum between the two. So now we move on. We update current to be here, and we check this interval right here. Is there an overlap between current and previous? No, there's not. There is no overlap. So in this case, all we need to do is add current into results. Current is 8, 10. But here's the catch. We need to update previous to the current value, so that the next time we check current and previous, it's going to be regarding the next two. So previous moves here, and current moves here. Now we check for an overlap. This is considered an overlap. So we take the maximum, we update the previous end. So this is going to be 10. We update that to the maximum between the previous end and the current end, which is going to be this value right here. So it's going to be 12. So this is what the previous now looks like. And this will update to 12. And then we move along, current goes out of bound, and we return res. So with regards to the complexity analysis, time is going to be O over n, where n is the length of the input, and space is going to be O1, constant space. Because even though we are populating this result array at the bottom here, this is added to our output. So it's not classed as occupying space within this solution. So we're going to start this off by creating constants called start, which is going to be equal to 0, and end, which is going to be equal to 1. So this is just starting off by creating the indexes for 0 and 1 within the interval arrays. Then we need to order the intervals, so we need to sort them in ascending order. So intervals.sort, taking A and B. And remember, we are sorting an array of an arrays, so we need to say A at start minus B at start. Then we need to create a previous variable, which is going to be equal to intervals at 0, so it's going to be equal to the first array within the intervals array. Then we need to create the result array, which is going to be equal to an array containing previous. Then we need to loop through the intervals, so let current of intervals, and we need to compare current at start with previous at end, like we did in our solution walkthrough. So if current at start is less than or equal to previous at end, we need to update previous at end. So previous at end is going to be equal to the maximum, so math.max, between previous at end and current end. Else, if there is no overlap, we can just push current into result, and then we need to update previous to be current, because in the next iteration current is going to move one forward, so we need to update previous to match that, and then we can just return res. Okay, let's give that a run. Let's submit it. So you're given an array of intervals where interval I is equal to start I, end I, return the minimum number of intervals you need to remove to make the rest of the intervals non-overlapping. So the question is self-explanatory, it's pretty intuitive. So we just need to return the minimum number of intervals we need to remove in order to create an array where there are no intervals that are overlapping. In the first example, we need to remove 1, 3 because there is an overlap between 1, 2 and 1, 3. As soon as we do that, we have no more overlap. So as you can see, 1, 2 ends on 2, 2, 3 starts on 2. So that is not considered an overlap. And then 2, 3 and 3, 4 are not overlapping either. In example 2, we just have an array consisting of 1, 2. So we need to remove 2 of those in order to create an array where there are no overlapping intervals. So how would we go about solving this? Well, the first step is to always sort the input array. And we are going to be sorting this by the second values within this array. So we're going to have a sorted values that look something like this. So these have now been sorted, and we can map them out onto our diagram. Now say we start at position 1 within this, so we're going to start at position 1, so this value, we'll call this current, so we'll have the current value, we'll have a start and end point of previous as well, so we'll call this one previous, and in order to see whether there is an overlap here, we compare the last value of prev, so the end of prev, with the start of current. If there is an overlap, then we need to keep some kind of track of how many times we find an overlap, so we're going to have a count variable, which is going to be set at 0, and every time we find an overlap, we're just going to increment that. So at this point, as we stated in the question, this is not considered an overlap. So when it's not considered an overlap, we reallocate prev to current and current to the next value within the array. Okay, so this is going to have start and end. Is current start less than prev end? It is indeed, so we can increment count here and we can move along. So we update current to here, prev stays here, and then we look at prev end with current start and we check to see whether there is an overlap there, in which case there isn't, so we move along, and as you can see there's nowhere else to look, so we just return count. So the reason why we take and sort via the second value within this array is because say we had an input array like this. If we map this out and we ordered them via initial values, so say we go up in 10, so say we ordered this by initial values, we're going to have 100, 111, 212, and 1122. So this is going to be our sorted array. Okay, so if we map these out, if we followed the same solution as we did above, we're going to compare, say we start off at index 1, we're going to compare current with previous. So current start is going to be compared with previous end. So is current start less than previous end? Yes, it is. So we increment count. So count is going to go to 1, right? And then we move this along. So we move current up here, we compare it to start. Current start is less than prev end again, so we increment count to 2. And then again, we are going to increment count because there is an overlap there as well. And we have an output 3. But the actual answer to this is 2. There are only 2 overlaps. And I'll show you why. So with this initial input, say we ordered it by the second values. So we're going to have 1 and 11. We're going to have 2 and 12, 11 and 22, and 1 and 100. This is going to be our sorted array that we're going to loop through. So as you can see, it's in reverse. So if we run through this quickly, so we're going to have current here, prev here, compare prev end with current start. There is an overlap here, so we can increment count. We're going to update this. So current's going to move up here. Is there an overlap between current and previous here? So current start and previous end. There isn't here. So we don't increment count in this case. We just update previous to current and we update current. And then there is one more overlap in this case. So this is incremented to 2. So that is the final answer. So we always need to make sure that we sort this via the end values. So time and space analysis. Time is going to be on log n because that is what is required with sorting. And space in this case is going to be O of 1. So initially we need to sort intervals via their second value. So taking A and B, and it's going to be A1 minus B1. So that's sorted the intervals via the second value. Then we need to create a count variable, which is going to increment every time we find an overlap. And we need a previous, which is set to 0. So we're going to loop through this array starting at 1. I is less than intervals.length, I++. So let current equal intervals at I to make this more readable. So if current at 0, so current at start, is less than intervals prev at end, so it's less than previous at end, we can increment count. Else what we need to do is we need to update previous to I. Okay. And then it's just a simple case of returning count. So let's give that a go. Submit it. So given an array of meeting time intervals, where intervals I is equal to start I, end I, determine if a person could attend all meetings. So here in the first example, we have an output of false, and the reason for that is our first interval start is 0, end is equal to 30, and then the next array is 5 to 10, and the final array is 15 to 20. So these two intervals are in between 0 and 30. So there is an overlap there. So this is going to return false. In the second example, we have 7 and 10 and 2 and 4. These are not overlapping, so the answer is going to return true. So this is a good introductory question to intervals. With this question, the first step to solving it is to sort the input array, and we're going to sort it based on the first values within the array. So like the second example, we have 7 and 10, 2 and 4. We need to sort this just to make sure that it's easier for us to navigate through this problem. So with any interval question, I like to draw out the grid. So we're going to go up in 5s here, so 5, 10, 15, 20, 25, 30, and we're going to plot each of these arrays within this grid. So 0 to 30, 5 to 10, and 15 to 20. As you can see, we have an overlap here, and we have an overlap here. So the key points in question involves the current, end. So let's just call this array, right? Let's call this array current. We have start and end. So start is equal to 0, end is equal to 30, and then we have current plus 1. We have start and end. So how can we tell if there is an overlap between current and current plus 1? Well, we take this end value of current and we compare it to the start value of current plus 1. If the end value of current is greater than the start value of current plus 1, we have an overlap, in which case we can just return false. For our second example, the first thing to do is to sort this array. So we're going to plot this out. So it's going to be, and here we can clearly see that there is no overlap because this value here, so current end, is less than current plus 1 start. So the person could attend both meetings in this example. So firstly, let's sort intervals based on their first value. So it's going to be A at 0 minus B at 0. Let's create a start variable, which we're going to set to 0, and an end variable, which we're going to set to 1. So these are going to be the indexes within the arrays. We need to loop through intervals. So I is equal to 0, I is less than intervals.length minus 1. So we're doing minus 1 because we're comparing two values. And this way, by minusing 1 from the interval.length, it means that we won't go out of bounds. If intervals I at end, so if the current interval end value is greater than intervals I plus 1, so current plus 1, start, we can return false, else return true. So whenever we reach a point where current value at end is greater than the current plus 1 value at start, we can return false. If that never occurs within this for loop, we return true because we have found that there are no overlaps within this array of arrays. So let's give this a run. Submit it. So given an array of meeting time intervals where interval I is equal to start I, end I, return the minimum number of conference rooms required. What the question is asking for here is how many overlaps are there at any point in time within the intervals. In the first example here, we have 0, 30, 5, 10, and 15, 20. Now, at any point in time, we have two meeting rooms, right? Because at any point in time, there is one overlap. So we have to have two conference rooms, okay? So 5 to 10 and 15 to 20 are found within 0 to 30. However, 5 to 10 is not interlinking or doesn't have an overlap with 15 to 20. So at most, there can be only two conference rooms. With the second example, 7, 10, 2, 4, there is only one conference room because there is no overlap within this meeting room. So as soon as we loop through this array, this conference room is open. So we have one conference room here. So let's have a rooms variable, which is going to store how many rooms are available at any point in time. So we have one. As soon as we reach this level, This one is still going to be open, and we have started a new one. So at this point, we are going to have 2 rooms open, and then once we reach the end here, so once we reach this point, this conference room is going to close. So rooms essentially is going to go back to 1. Once we get to this point, another room is going to open up. So this is going to go back to 2, because remember here we closed it, so it's going to be 1. And then here it's going to equal 1 again. So as you can see, the maximum amount of rooms that we need at any point in time is 2. And that is the output that we need to return. The difficulty in this question is kind of working out a way to check the initial values to see whether they're before the last values within these intervals. So we need to extract out the start values from this array, and we also need to extract out the end values and put them into separate arrays. So if we have start, which is equal to 0, 5, and 15, this also needs to be sorted. And we have end, which is equal to, well, we'll call it starts and ends, 10, 20, and 30. Now within this, we can easily compare the starts and the ends. So at any point, if start is less than end, we can increment rooms by 1. Okay, so we're going to have rooms and end. So initially rooms is going to be set at 0. We compare the start, which is 0 to 10. Is it less than 10? Yes, it is. So we can increment rooms to 1. We move to the next value in start, which is 5. That is also less than 10. So we can increment that pointer again to 2. Then we move along. Starts is equal to 15. 15 is greater than 10. So rather than incrementing rooms in this one, what we're going to do is we're going to update end, which is the index within ends. So this is going to be incremented by 1. So we're going to increase that to 1. So we move ends along, and then we'd carry on this until we exit one of these, and then we can just return the value of rooms. And there is just one small edge case that you need to take into consideration. And say we have 20 to 25 here. Okay, so we have an extra value onto these arrays. When we reach this point, this right here is considered one room closing whilst another one's opening. So this is not an overlap. So unlike merge intervals, where we have an endpoint which is equal to a start point, that is equal to an overlap. In this question, this does not equal an overlap. So we can just carry on as normal. So if we do this again, so we start at starts, this is less than 10, we increment room, we increment start. Start is 5, that's less than end, which is 10, so we increment room again. We move over to 15. 15 is now greater than 10, so we increment end, which is the index to end, to 1. So we can increment ends. We also need to increment starts here, and we can see 20 is equal to 20. That is not an overlap, so in this case, we are just going to increment end, not change start, and then we exit start. So we're now out of bounds, so we can just return 2. Time complexity for this one is going to be n log n, because initially with this array, we need to loop through or map the values, and then we need to sort them via their first or second values. So it's going to be n log n, and space complexity in this one is going to be O n plus m, where n is the length of starts and m is the length of ends array. Okay, so let's just cover an edge case. So if intervals is equal to null or intervals.length is less than 1, we can return 0. Because there are no intervals within the array, there are no times for meetings, so essentially no rooms are needed. So firstly, we need to sort the intervals into all the start values and end values. So we can have const starts. So we're going to map over the values. We're going to take in intervals or interval. And we're going to grab the first values within that, and then we're going to sort them in ascending order. And then we're going to do that for ends. And we're just going to take in and map over the second values within those arrays. So we're going to grab the ends. Let's create the 2 pointers. So rooms is equal to 0, end is equal to 0. We're going to loop over so that I equals 0, I is less than intervals.length, I plus plus. Now if starts at I is less than ends at end, we need to increment rooms, else we add to end. So every time a new room is opened or every time a starting value is found that is less than the current ends, we increment rooms. Else we're going to update the ends. So we're going to move to the next end value within the list. And finally, we can return rooms. I'll submit it. So you're climbing a staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? So the question's asking for distinct ways, the maximum amount of ways you can climb the stairs using either 1 or 2 steps. So that suggests it's going to be dynamic programming. So it's a pretty straightforward question. N is equal to 2, so there are 2 ways to climb to step 2, 1 step plus 1 step or 2 steps. So let's have a look at an example. So with dynamic programming, you can use one of 2 methods. You can use a top-down approach, which is going to be recursion and memorization, or there's bottom-up. And what we're going to look at today is bottom-up because it's the simplest to understand with this question. So we have 5 stairs here. 1, 2, 3, 4, 5. We start off at this position and we want to get to this position. And we want to know the distinct ways we can climb this staircase to reach this value here. With DP bottom-up solution, what we can do is create some base cases to start off this chain of events, because what dynamic programming ultimately does is it calculates the solution to get to 1, it calculates the solution to get to 2, so how many ways are there to get to 2, to 3, to 4, and then it uses previous values from previous solutions in order to computate the new solution. And then it'll do that until we get to the top. Let's create these base cases. It's pretty straightforward. So how many ways are there to get to 1? DP of 1 is going to be 1 way, right? We can take 1 step. DP of 2, so how many ways are there to get to step 2? Well, you can take 1 step, and then another step, that's 1 way. Or you can take 2 steps, and that's another way. So DP of 2 is equal to 2. Now we have some base cases, right? But let's carry on this. Let's see how many steps it takes to get to DP of 3. So DP of 3, so we can say this one takes 1 way to get to there, this one takes 2 ways. So how many ways to get to step 3? Well, we can take 1 step, and another step, that's 1 way. We can take 2 steps, and then 1 step. Or we can take 1 step, and then 2 steps. So that's 3 ways, right? So 3 ways. Now you can notice a pattern. Take these as base cases, right? So say those are base cases. In order to computate the maximum distinct ways that we can get from this point to step 3, we can simply add the previous 2 values together, or the previous 2 solutions, shall I say, together. And that is going to give us the answer for this position. And this is called the optimal substructure. So it can be used to calculate 4 now. So how many distinct ways are there to get to step 4? Well, it's the solution to the ways to get to step 3 plus the solution to the ways to get to step 2. So that's 5. And then for step 5, it's going to be 5 plus 3, which is 8. And that's the answer we're looking for. So time complexity for this algorithm is O of n, where n is the number of stairs that we need to go to. And then space is also O of n, because we're going to be storing each individual step or the solution to each individual step within DP array. So that DP, so we're creating this DP array. We're going to initialize DP of 1 is equal to 1 because there's 1 way to get to step 1. DP of 2 is equal to 2 because there are 2 ways to get to step 2. And then we carry out the loop. So we need to go up to and including the nth value, increment the for loop, and here we create the optimal substructure. So dp of I is equal to dp of I minus 1, so the previous step solution, plus dp of I minus 2, the solution to 2 steps back. And then we can return this value. So if you've done Fibonacci sequence before, it's pretty much the exact same as this, but just reworded, right? So they have the same optimal substructure. Okay, let's submit it. So you're given an integer array, coins representing coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coin. So here is an example. We have coins 1, 2, and 5, and the amount that we need to make is 11. The output is 3 coins. 3 coins are needed to make the amount 11. And those coins are 5, 5, and 1. Remember, we can have an infinite amount of any of these coins, so we have chosen 5 twice here, plus 1. Okay, so this is a very tricky question. There are a number of different ways that we can computate this answer. We can use a depth first search, recursive solution, we can use breadth first search, but because this question is asking for the fewest number of coins, so it's asking for an optimal, so anything like the fewest number, the greatest number, the highest amount, the lowest amount, usually is looking for the optimized approach of dynamic programming as the solution. So let's discuss DP. There are two possible ways of carrying out DP. There is a top-down, where you start from 11 and branch out and work your way down through possible solutions, or there is bottom-up, and bottom-up is the approach we're going to be taking. So bottom-up requires you to start at the smallest possible amount, so say we chose the amount of 0, and work out the solution of that amount, and then we'll work out the solution of the next value to that, so that will be 1, and then we'll work out the solution to 2, 3, 4, etc. So we're going to create solutions to subproblems, and then we can ultimately use previous subproblems in order to generate the actual solution to 11. So with our DP bottom-up solution, we need a DP array, and our DP array is going to store all the solutions to the values between 0 and 11. So we need our DP array to contain amount plus 1 values. So once we have created this, we need to initialize the DP array with a certain value. Now remember, from the question it asked us to return -1 if we couldn't find a valid solution. So if no coins would add up to the value. So say we had coins and we had an amount of 2. No coins will ever make up 2. So in this case, we need to be able to return -1. So what we need to initialize the DP array with is an invalid value. So if we initialize it with, say, positive infinity, and we initialize each and every value with positive infinity, then if at the end, say in this example, we have infinity at the end, we can say if DP at current amount is greater than the actual amount, then we can return -1. Else, return DP at current amount with positive infinity. So now that that's the DP array sorted, we can start adding values in here. So firstly, with this dynamic programming solution, we can add a base case to this. And the base case in this example is going to be DP at 0. So how many coins does it take to make 0? It's going to take 0 coins to make 0. So now we've updated the infinity with 0, and now we can carry out this process. So how many coins does it take to make 1? Well, we need to loop through the coins, right? So we're going to start off with 1. We're going to check. So the current amount of 1 is within coins array. So we can just say it takes 1 coin from the coin array to make the current amount of 1. Move along. So at 2, we can again loop through the coins array. So we can see that 2 is within the coins array. So we can just update that with 1 coin because 2 is here. That is 1 coin. We'll add it into the DP array. Now moving on to 3, let's check this. So DP at 3. If we start off and we look at 1, so we have taken the coin 1, so that counts as 1 coin. And we are going to add the remainder. So we're going to add the amount, the current amount, minus the coin that we just took. So -1 gives us 2. And the minimum amount of coins it takes to make 2 is 1. So that's 1 plus 1, which is equal to 2. So we can put this in here as a temporary value. Then we need to go across again to the second coin, which is 2. So that counts as 1 coin. And then we need to do the current amount minus 2, which gives us 1. And that is also 1. So that is equal to 2. And lastly, when we get to 5, well, the current amount minus the coin is less than 0. So we can exclude that. We can add that as an if clause. So we can say if current amount, which at this moment in time is 3, minus the coin, 5, is less than 0, then return. So now that we've done that, we can move on to 4. So DP at 4 is equal. If we choose 1, that counts as 1 coin. Then we have to do the current amount minus 1, which is equal to 3. So 1 plus 2 is equal to 3. We can add 3 in there as a temporary value, but we still need to check the other coins for a minimal. So we move over to 2. 2 counts as 1 coin. And then we do current amount minus 2, which is equal to 2. The smallest or the minimum amount of coins needed to make 2 is 1. So we add that on. And that is equal to 2. So that is smaller than 3. So we can update this to 2. Then we move on to 5. Current amount minus 5 is less than 0. So we don't include that. So now we can move along. So as you can see, there's a pattern here. And this is what's called the recurrence relation. So DP at current amount is equal to the minimum between dp at current amount or 1 plus dp current amount minus coin. So if we look at 5 now, we can see that coins contains 5, so we can just add 1 into there. So if we move on to 6, we start off with 1, so dp at 6 is equal to 1 plus 6 minus 1, so 6, so here we have 1 plus dp current amount minus coin. So current amount is 6 minus coin, so we've got 1. So we work out the dp of that, so that's 1. So that's equal to 2. We can add 2 as a temporary value and check the others to see if there's an even smaller value. So dp at current amount is now 2. So dp down here becomes 2. So then we move on to the next coin. We take 2, so that counts as 1 plus the current amount minus 2, which is 4. So that's plus 2, so that's equal to 3. So 1 plus dp at current amount minus coin is 3. Which one is minimum? 2. So we can keep this as 2. Okay, and then if we moved on to 5, 5 counts as 1 coin. 6 minus 5 is equal to 1. So that counts as 1 again. So 1 plus dp at current amount minus coin is equal to 2. So we can keep 2 there. And then we can carry out this process for the rest of the values. So dp at 7, if we choose 1, we have 1 plus 7 minus 6, which is 1. So that's 1 plus 1, which is equal to 2. We can choose 2 to begin with. We have our current amount at the minute, dp at current amount is equal to 2. If we choose 2, that's going to be equal to 1 plus 7 minus 2, which is 5. So that's going to be 1 again. So that's equal to 2. So that's 2. So the minimum is still 2. If we choose 5 now, that's 1 plus 7 minus 5, which is equal to 2. So that's again 1, which is equal to 2. dp at 8, if we choose 1, it's 1 plus 8 minus 1, which is 7, so that's equal to 2, so that's equal to 3. So current amount, dp is currently 3. So if we move over 2, that's 1 plus 8 minus 2, which is 6, so that's equal to 2, so that's equal to 3 as well. So those are the same. Then we move over to 5, we have, that counts as 1 coin, 8 minus 5, which is equal to 3, that's 2, so that's also equal to 3. So we add 3 in there. dp at 9, we take 1, so that's 1 plus, current amount is infinity. 1 plus 9 minus 1, which is 8, so that's 3, so that's equal to 4. 4 against infinity, which one's smaller? 4, so we can add 4 in there as a temporary value. So 4 becomes dp at current amount. This gets emptied. We move across the coin, so if we take 2, that's going to be 1 coin plus 9 minus 2, which is 7. So 1 plus 2 is equal to 3. 3 is less than 4, so we update here with 3, so that becomes 3. This is emptied. We move across to the next coin. We have 5, so that counts as 1 coin, plus 9 minus 5, which is equal to 4. So that's 2, which is equal to 3. 3 and 3, both the same value, so we can leave that as is. dp at 10, if we take 1, that counts as 1 coin, plus 10 minus 1, which is equal to 9, so that's 3, so that's equal to 4. So infinity against 4, which is smaller, 4 is, so we add 4 in there. So this becomes 4, this is removed. We move it over to the second coin, so that's 1 plus 10 minus 2, which is equal to 8, so that's 3 again, so that's going to equal 4. So 4 stays there. And then lastly, we choose 5, which counts as 1 coin, plus 10 minus 5, which is equal to 1 in the dp array, so that's equal to 2. So 4 against 2, 2 is the minimal. And lastly, for dp at 11, if we choose 1, that counts as 1 coin, plus 11 minus 1, which is 2, so that's equal to 3. So infinity against 3, 3 is the minimum, so 3 can go in there as a temporary value. This goes to 3, this is emptied. We move over to the second coin, so that counts as 1, plus 11 minus 2, which is 9, 3, so that's equal to 4. 4 is not less than 3, so we can forget about that. We move over to 5, that counts as 1 coin, plus 11 minus 5, which is 6, so that's 2, so that's equal to 3, and 3 is the same as 3, so we can keep that in there. Now that this array is full, we can just return dp at amount. And remember, we need to make sure that we have that if conditional logic, just in case this value is still infinity. So in the case of this example up here, if the last value is infinity, we need to return -1. So I'll show you that when we code this out. Firstly, let's discuss time and space complexity. So time complexity is O s times n, where s is the amount and n is the denomination count, and then space is O s, where s is the amount to change. So when writing this out, it doesn't actually take much code. So firstly, if we create the DP array, so we say array amount plus 1, because we want to have 0 up to amount, so we need to add that extra value. And then we need to fill it with an invalid value, so that's going to be infinity. We can set the base case for this DP solution, so DP at 0 is going to be equal to 0 because it takes 0 coins to make the value of 0. So we need to create that for loop. Current amount is equal to 1 because we've already carried out 0 up here. Current amount needs to be less than or equal to amount, and then we can have current amount plus plus. Now we need to loop through the coins, so coin of coins. If current amount minus coin is greater than or equal to 0, then we have a potential value, because remember, if it's less than 0, then we just forget about it because it's not a valid solution. Then we can say DP at current amount. So now we're going to start filling out that DP array, and that's going to be equal to the recurrence relation we created. So it's going to be equal to math.min DP at current amount for the current value within DP and 1 plus DP at current amount minus coin. So we're going to loop through the coins, we're going to check the coin, minus the coin's value from current amount, and we're going to add a 1 here. And this 1 here resembles the current coin that we have taken. And then to end off, we need to include the if conditional logic, which determines whether the value is equal to -1 or the DP add amount. So we need to return DP add amount. If that is greater than amount, so if it's infinity, we can return -1, else we can actually return DP at amount. Let's just check to see if that's worked. Okay, it's been accepted, let's submit it. So given an integer array nums, return the length of the longest strictly increasing subsequence. A subsequence is a sequence that can be derived from an array by deleting some or no elements without changing the order of the remaining elements. For example, 3627 is a subsequence of the array 0316227. So in the first example, we have this nums array and the output is 4. And that's because 2, 3, 7, and 101 is the longest common increasing subsequence. That is length 4. So because this question is asking for the longest, so a maximal, we should think about using dynamic programming. So basically, at each number, we want to work out the maximum subsequence at that position. So let's draw a DP array out, and we'll use the iterative bottom-up approach. We have this nums array here. We want this DP array to be the same length as this. Okay, great. We can populate it with those values. Now, at any one position, what is the minimum subsequence? So at any one position, what is the minimum length subsequence? So if we're at position 0 in here, what is the minimum subsequence, or what is the subsequence we can achieve at this point? Well, it's going to be 1, right? Because this is of length 1. It's going to be the same with 1. If that was on its own, that would be 1. If this was on its own, that would be 1. So we can initialize all of these values to 1, because at any of these values, the subsequence is never going to be 0. So this is our kind of base to start off with. So because we know 0 is already 1, and there is only one value here, we can start off at this position. So let's have a look. Is 1 greater than 0? So we're going to look at the previous values. Yes, it is. So what's going to be greater? Is it going to be this value here, 1, or is it going to be the previous value plus 1, which is equal to 2? It's going to be 2. So let's update this. Let's move on to the next one. So is 0 greater than 1? No, it's not. Is 0 greater than 0? No, it's not. So we can move to the next value and leave this as 1. Is 3 greater than 0? Yes, it is. So we can look at this value here and compare it to this value plus 1. So which is greater, 2 or 1? So we can update this to 2. Then we compare 3 to the value before that. So is 3 greater than 1? Yes, it is. So which is larger, 2 or this value plus 1? Well, it's going to be 3. So we can update that. Then we can compare 3 to 0. So 3 is greater than 0, so we choose the maximum between 1 plus 1 and 3. So we keep 3, here. Now that 3 has been checked, we can move to 2. So we compared 2 and 3. 2 is not greater than 3, so we leave it as is. We go back 1. So is 2 greater than 0? Yes, it is. So we choose the maximum between 1 plus 1 and 1 here. So we're going to update this to 2. So now would be a good time to write down the optimal substructure. So the optimal substructure in this case is dp at current. So the current value we're on is going to be equal to the maximum, remember this is pseudocode, between dp at prev, so the previous value within the dp, plus 1, and dp current. So let's go back to this. So now 2 is compared with 1. So 2 is greater than 1, so we choose the maximum between 2 plus 1 and our current value. So we're going to update this to 3. We compare 2 with 0, which is greater, 1 plus 1 or 3. So we leave 3 there. Now 2 has finally been looked at, so we can move on to 3. So we're at the last value. So is 3 greater than 2? Yes, it is. So we choose the maximum between 3 plus 1 and 1. So we can update this to 4. Is 3 greater than 3? No, it's not. Is 3 greater than 0? Yes, it is. So we can choose the maximum between 1 plus 1 and 4. So we leave it at 4. Is 3 greater than 1? Yes, it is. So we choose the maximum between 3 and 4. So we leave it at 4. Is 3 greater than 0? Yes, it is. So we choose the maximum between 2 and 4. So we leave it as this. And what we need to do is return the maximum value that is found within here. So in this example, the maximum value is found at the end, but it could be found anywhere within this array. So just watch out for that. And then time complexity for this. Well, as you can see, we loop through this nums array here. And as we're populating this dp array, we have to compare it to all previous values in nums. So there are 2 loops, one going forward, one going backwards. So time complexity is going to be O(n) squared. And then space complexity is going to be O(n), because we're using this auxiliary data structure to create this dp array. Okay, so let's create the dp array. So it's going to be new array, nums.length, and we're going to fill these values, we're going to initialize them with 1. Then we need to loop through from I is equal to 1, so we start at the first value. I is less than or equal to nums.length, because we want to go up to and include the last value. And now we need to loop backwards. So we loop backwards where j is equal to I, so j is at the ith value. J needs to be greater than or equal to 0, j minus minus. And if nums at I, so the current value we're on, is greater than nums at previous, then we can say dp at I is equal to math.max, dp at I, and dp at j plus 1. And then a quick way to loop through the values and find the maximum is to just use the spread operator. So math.max, and spread out the dp. Okay, let's give this a run. So given 2 strings, text1 and text2, return the length of their longest common subsequence. If there is no common subsequence, return 0. A subsequence of a string is a new string generated from the original string with some characters deleted without changing the relative order of the remaining characters. So the example ace is a subsequence of A, B, C, D, E. A common subsequence of 2 strings is a subsequence that is common to both strings. So in example 1, this is the example we'll be looking at in our solution. We have A, B, C, D, E, and as in the question, we have the longest common subsequence is equal to ace. Okay, so in example 1, we have text 1, which is A, B, C, D, E, and text 2, which is ace. The output is 3, so we're returning an integer, and the explanation is, well, ace is the longest common subsequence within both strings, and its length is equal to 3. So because this is looking for a global optimal, so the longest common subsequence, we're going to utilize dynamic programming. So for our DP array, we are going to have a 2D matrix. And with dynamic programming problems, we need to set a base from which we can build upon, because remember, dynamic programming is sub-problems or solutions to sub-problems until you reach the final solution. So we need to set the base of this. Now we've got ace, which is string of text 2. We've got A, B, C, D, E, which is string of text 1. And initially what we need to do is we need to set
the initial rows and the initial columns to 0. So this is setting that base within our dynamic programming, and then we can build upon this and start to look to see whether substrings are equal to one another, and if they are, we can start populating this DP array. Okay, so we have output down here, which is going to be the final solution. So we can start looping through this now. So we can check the strings. We'll start at this position here, because we've already populated these. Is letter A equal to letter A? Yes, it is. So with this, we take from the diagonal and we add onto that diagonal value. So this value here, we add 1 because this is a match. So that'll give us 1. We move along. Is A equal to B? No, it's not. So we take the maximum between the left value and the value above, which is 1. Then we move along. Is A equal to C? No, it's not. So we take the maximum from this position here. We do the same with D. We take the maximum from this position and this position. So that's 1. And again, we do the same with E. Okay, so let's move on to the next row. So is C equal to A? No, it's not. So we take the maximum. Is C equal to B? No, it's not. So we take the maximum. Is C equal to C? Okay, so we have a match. Now when we have a match, we take from the diagonal and we add 1. So this is going to be 2 now because we have 2 matches, right? We have the first match here, which is A and A, and we have the second match, which is C and C. Is C equal to D? No. So we take the maximum between this and this. Is C equal to E? No. So we add 2 into there as well. Okay, so we're on the final row now. E is not equal to A, so we take the maximum. E is not equal to B, so we take the maximum. E is not equal to C, so we take the maximum from 1 and 2. It's going to be 2. E is not equal to D, so we take the maximum, which is 2. E is equal to E, so we have another match. So we take the diagonal and we add 1. And that gives us 3. And all we need to do is return this as the output. So that is equal to 3. So in terms of the upper bound time and space complexity, time complexity in this is going to be OM times N, because we have a 2D matrix that we're looping through and we're populating each value within this DP matrix. It's going to take M times N operations, where M is the length of the first string and N is the length of the second string. And space, again, is going to be the same. So it's going to be M times N because we are occupying the entire DP array as extra space. Okay, so let's write this out. So let's create variables called M and N. That will be the length of both string 1 and string 2. Let's create the DP matrix. We're going to add 1 to M for the empty string, so we can create that base. And we're also going to do the same for N. And rather than just fill in the initial row and the initial column to zeros, we can simplify it to just fill in the entire DP array with 0. Now we need to loop through text 1 and text 2. We start off at 1 because we initially set the first row to 0. We go up to and including M. And we do the same for the letters of text 2. So if text 1, I minus 1, so the letter at text 1, I minus 1 is equal to text 2, j minus 1. So if the values are equal, we can populate the DP array at ij to the diagonal. So DP I minus 1, j minus 1, and we add 1 to it because we found a match. Else, if it's not a match, we'll populate that value within the DP array to the maximum between the left value and the value above. So I minus 1 j, which will give the value above, DP I j minus 1, which will give the value to the left. And for the output, we need to return the integer in the last position of the DP array matrix, which is going to be DP M N.
So you're given a string S and a dictionary of strings. Return true if S can be segmented into a space-separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times in the segmentation. So within our first example, we have the string LeetCode, and we have a dictionary containing the words leet and code. And can we create LeetCode from these segmented words? And the answer, of course, is true. And then if we look at example 3, we have cats and dogs. We have the dictionary containing cats, dogs, sand, and cat. Can we create this string using a sequence of words from the word dictionary? Well, no, we can't, right? Because if we use cats, we get up to here, then we have and, right? And is here, but then we don't have OG. It's the same if we use the other sequence. So if we start off with cat, we'd have sand, and again, we'd be left with OG. So that's not possible. So we return false. So there are a number of ways we can solve this. We can use DP, we can use recursion and memorization, or we can use BFS. And today we're going to be looking at the breadth first search solution. So how are we going to do this? Well, as a high level overview, we're going to loop through this string. We're going to start off at index of 0, and we're going to check all possible strings to see if we can find a word that is equal to one of the words within the dictionary. So we start off at L, we look to see if that's in the dictionary. It's not. Then we loop across. Is LE in the dictionary? No. Until we get to leet. Once we've found leet, we add the ending index into our queue, and then we shift off the queue, the next position, and we repeat the process. So we check all these positions until we find the word within the dictionary. And then in order to determine whether we found an entire sequence of words, we're going to compare string.length. So let's put string.length, which is equal to 8. If this is equal to the last index within our search, then we can return true. So for this breadth first search solution, we're going to have a visited set, which is going to contain the indices that we have visited. We're going to have a set dictionary. So we're going to store the dictionaries from this word in a set. And the reason we do this is because the set has O and lookup, and we are going to constantly be referring to the dictionary. So by storing it in set, we can improve the time complexity here. And like any breadth first search, we are going to have a queue. So this queue is initialized with the first index, and now we can carry out the breadth first search. So if we shift off of queue, the position of 0, in order to check the substring within this string right here, we need to use s.slice, right? s.slice. And in order to use s.slice, we need to remember that the second parameter passed into slice is non-inclusive. So if we get a substring by passing in 0 and 1 within this string here, the letter we're going to get from this is L. So if we go from 0 to 1, we get L. We check if L is in the set. It's not. So we check for LE. That's not in the set. We check for LEE, not in the set. We check for LEET. Now this, using string.slice, is going from 0 to 4. We have found this within the set. So now we make a termination check. And a termination check is to see whether we've reached the end of this string. So is this index equal to string.length? It's not. So all we need to do is pass this index right here into queue and carry on searching to see if we find another word within this string within set. So we look at LeetC, LeetCO, LeetCOD, and LeetCode. None are found within the set. So we can now add this value into visited and repeat the process. So we shift off of Q4 and we start here. So we look to see whether C is in set. Nope. CO. Nope. COD. Nope. CODE. This is within set, and the indices go from 4 to 8 to get this. And remember, we're saying 4 to 8 because string.slice, B is non-inclusive. This is within the set, so we can compare the index of the last value of this substring with the length of the overall string, and if they're equal, we can return true. And that's the case here. So let's have a look how this approach would play out for cats and dog. So we add 0 into the queue, the index of the first character within this string. We shift off of queue, value of 0, and then we start the loop to check whether the substring is found within the set. So we don't find anything until we reach cat, and that will be 0 to 3. So we can add the index of 3 within here. Then we search further. So we search cats, 0 to 4. That is found within the set. So we can add 4 in here. And then we search the rest of the string. See if we can find cats and none of these are found within set. Now 0 has been seen. It can be added to visited, and seeing as Q still has values in, we can shift off, look at index of 3. So if we start at S, we compare. So is S found within the set? No. Is SA? No. Is SAN? No. Is SAND? Yes, we have sand. So we can add the end index, which is going to be 7 here. We can add 7 within our queue. We carry on. So is Sando in there or is Sandog in there? Nope. So that is 3. 3 has been seen. It can be added to visited. Then we can look at 4. So we shift the value of 4 off of queue, start at index of 4. The only value from here onwards is and that finishes at 7 as well. So if we add 7 again, we have duplicates here. 4 has been seen, 4 can be added to visited, and then we can look at 7. So we shift off of queue, we start at 7. Can we find O in the set? No. Can we find OG in the set? No. We've reached the length of the string, so this doesn't return us with any results. So we can add 7 within the visited. Now we shift off of queue the value of 7 again. In order to stop duplicate values from being checked, we can add a query at the top of the BFS while loop to see whether visited has the current value we've just shifted off. If it does, then we can just stop this process. And now queue is empty. We've exited the BFS and we can return false. So time complexity for this one, BFS by nature is O of n, but as soon as we've created multiple loops within this, where we're looping through the entirety of this string, and then we're checking every single substring, this increases the time complexity to O n cubed. And then space is going to be O of n, where n is the value of indices that we store within the queue. So the first thing we need to do in coding this out is create the visited set. We also need a set that contains the values of the dictionary, so word dict. And we also need to initialize the queue for our BFS. Then we can start the BFS. So while queue.length, we shift off of queue to get the current value. So current is equal to queue.shift. Then in order to avoid duplicates, we check visited to see if it has the current value. If it does, we don't carry this out. Otherwise, we'll loop through from current plus 1, I is less than or equal to string.length because we want to go up to and including the last value of the string. And now we have to create those substrings. And the way we do that is we're going to slice. So we need to check in set if set has string.slice. We're going to slice from the current value to I. We need to compare it to s.length. So if I is equal to s.length, we can return true because we've reached the end of the string. Otherwise, we push into queue that index. Now at the end of this, we can add current into visited. And lastly, once this loop carries out, and in the case of cats and dogs, where we don't find a solution, the queue is going to be emptied. We're going to exit this while loop and we can return false. Give this a run. So given an array of distinct integers, candidates, and a target integer target, return a list of all unique combinations of candidates. Where the chosen numbers sum to target, you may return the combinations in any order. So the same number may be chosen from candidates an unlimited number of times. 2 combinations are unique if the frequency of at least one of the chosen numbers is different. So it's guaranteed that the number of unique combinations that sum up to target is less than 150 combinations for the given input. So we have candidates of 2, 3, 6, 7 with a target of 7. So we need to work out all possible combinations, removing duplicates of these candidates that add up to the target of 7. And the output is 2, 2, 3, and 7. There are only 2 combinations in this example. So for this solution today, we are going to be looking at the DP solution, not the recursive solution. So if you want to check out the recursive solution, then jump onto the other video where I explain that. Within the DP solution, we have sums. And these are all the sums up to target. So it's current target of 0, current target of 1, 2, all the way up to the target of 7. And then down here, down on the left side, we have candidates. So all the potential candidates that we can choose from. Now this DP array is going to be based on a 2D array, but it can be simplified into a single array. And that is what our code solution will show. But for simplicity and for readability, we're going to utilize this 2D array. So what this DP solution is doing is we're going through each individual sum, and we are working out the total number of ways from these candidates that we can make these sums. And by doing that, we can calculate the target of 7 by utilizing the solutions to previous targets. So initially, let's start off at 0. So we're at sum 0. Can 2 go into 0? No, it can't. So we can just leave this as an empty array. Can 2 go into 1? No, it can't. So we can leave this as an empty array. Can 2 go into 2? Yes, it can. But we also need to check previous sums, because dynamic programming is just utilizing the solutions of previously calculated sums in order to calculate the current sum. So we need to use the previous sums that we've calculated. So if we have a look at candidates, which is equal to 2, and the sum at 2, if we subtract candidates from sum, we get the value of 0. And we look in this to see whether there are any previous values which we need to add here first. But as we can see, it's an empty array. So we leave it empty, and then we just append onto it, or we just add on to the end 2. Now let's move on to 3. Can 2 go into 3? Yes, it can. 3 minus 2 is 1. This is empty. So 2 cannot make 3. We don't have a value in 1, so we cannot make 3 from this. So we leave this empty. Can 2 go into 4? Yes, it can. So 4 minus the candidate of 2, so 4 minus the candidate of 2 is equal to 2. And right here, we have the value of 2 in here. So let's add the previous value, which is going to be equal to 2. So that's this value here. And then let's add on this candidate here. Let's move over to 5. Is 2 less than or equal to 5? Yes, it is. So we know that 2 can go into 5. 5 minus 2, so 5 minus the candidate, is equal to 3. 3 is empty. So we cannot make 5 out of just 2. So we need to leave this empty. Let's move over to 6. Can 2 go into 6? Yes, it can. 2 is less than or equal to 6. So let's do 6 minus 2, which is equal to 4. As you can see, we have values in here. So we need to add these to this array first. So let's add the previous values of 2 and 2, and then add the new value, the candidate at position I. Then let's move over to 7. 2 is less than or equal to 7. 7 minus 2 is equal to 5. There is nothing within 5, so we cannot make 7 just from 2. Okay, let's move on to 3. So 3 is going to be empty here, here, and here, because 3 is not less than or equal to any of these values. Then at 3, 3 goes into 3. So we check at 3 goes into 3 exactly once, so we can add 3 in here. We move over to 4. 3 is less than or equal to 4. So we check 4 minus 3, which is 1. There is nothing within these arrays, so we cannot make 4 from just 3. So this stays empty. 5, let's have a look. So 3 is less than or equal to 5, yes. 5 minus 3 goes to 2. We have no value within this array, but we have a value within this array. So we need to add that to this array, so 2, and then we also need to add the candidate 3, which gives us the value of 5. Then we go to 6. 3 is less than or equal to 6. 6 minus 3 is equal to 3. We have nothing in this array, but we do have a 3 here. So we need to add that. So we add that first, then we add the candidate. And finally 7. Yes, 3 is less than or equal to 7. 7 minus 3 is equal to 4. So we have 2 and 2 in here. So we need to add that to the start of the array. We get to 6. So the only sums that are going to have 6 as a candidate within them are values that are equal to 6 or greater than 6. So all of these can stay empty. And then once we get to the sum of 6, we know that the candidate 6 goes into the sum of 6 exactly once, so we can add just 6. And then we move to 7. 6 is less than or equal to 7. 7 minus 6 is equal to 1. There is nothing within any of these arrays, so 6 cannot make 7 just on its own. So this stays empty. And then 7 is empty all the way up to the sum of 7. Upon which point 7 goes into 7 exactly once, so we can add that into this array here. And then our answer is going to be this section here. So when we return this, we'll get 2, 2, 4, and 7, which is the output that this question is looking for. Okay, so let's dive into the code and see what this looks like. Let's start out by making sure that the candidates are sorted, because this is only going to work if the candidates themselves are sorted in ascending order. So candidates dot sort AB A minus B. Let's create the DP array, which is going to be an array of arrays of arrays. And then let's loop through sum. So sum is going to be less than or equal to target. Sum plus plus. So we start off at 0 because we need to have that 0 case within our DP. DP at sum is going to be initially set as an empty array. We're going to have an array called combine, which is going to combine all the potential solutions for a given target. Then let's loop through the candidates. So I is equal to 0, I is less than candidates dot length. And here we can add the additional check. So we need to make sure that the candidates is always less than or equal to sum, because if it's greater than, we cannot make the sum from that particular candidate. So candidates at I is less than or equal to sum, I plus plus. So if sum is equal to candidates at I, then we know that that sum can be made exactly from one of candidates. So we just push that into combine. Else, so we need to check the previous values within DP and loop through those. So let prev of DP sum minus candidates at I. We need to stop duplicates. So if candidates at I is greater than or equal to prev dot length minus 1. So if it's greater than the last value within prev, then we can add it to combine. Otherwise, forget about it. So we make a copy of prev, and we also add in candidates at I. Then we need to set DP of sum equal to combine. So we update the DP of sum to equal the values which we have pushed into combine. And then we can just return DP at target. So the value we're looking for. Let's give this a run. Submit it. So you're a professional house robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. So given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. So in the question, what it's asking for is, out of this nums array, what is the maximum number that we can obtain from this, making sure not to include adjacent values. So the output here is 4, and the explanation is that we rob house 1, then we skip the adjacent house, which is this value, 2, and then we move on to 3, and we add those together. So 1 and 3 is equal to 4. So let's jump into an explanation. So with this question, what it's asking for is it's asking for a maximum. So it's asking for an optimal. And when a question asks for an optimal, what we should initially think of is dynamic programming. And in this case, we're going to be using bottom-up dynamic programming. So we're going to utilize the smallest kind of solution in order to work out larger solutions. So we're going to use solutions from subproblems in order to generate the overall solution. Now I'll show you how that's done. So with DP bottom-up, we need a DP array. And our DP array is going to be an array of each house. So let's say we have indexes 0, 1, 2, and 3. So we have 4 houses, which correlates to the houses that contain the cache. So we have 1, 2, 3, and 4. And we can just initialize these to 0. So the first step is to decide how much money can we steal from house 1. Well, we can steal 1, right? Because that's the maximum here. So we can set DP at 0 equal to nums at 0. Let's move along. So how much can we steal from DP at 1? So this value here, how much can we steal here? Well, we can either steal 2 or we can steal 1. But we can't steal both because they're adjacent houses. So we need to choose the maximum between the two, which is 2. So it's going to be max nums 0, nums at 1. Now here's where it gets interesting. What is the maximum we can steal at this point in time? So we can steal 3, and we can also steal the maximum achieved at 0 index, which is 1. Or we can just steal DP at index 1, which is here. And this breaks down and makes the recurrence relation, which is essentially what's going to allow us to solve each incremental problem until we reach the final solution. And that is going to be the maximum between nums at I plus dp at I minus 2, so the maximum at the non-adjacent house, or that's going to be compared with dp at I minus 1, so the adjacent house. So in this case, we have 3 and 1, so that's 4, compared to 2. So we're going to add 4 there. And on the last house, we can choose nums at I plus dp I minus 2. So it's 1 plus 2, so it can be 3, or it can be dp at I minus 1, which is 4. And we're going to choose the maximum here. So we're going to choose 4. And then all we need to do is just return this value. So dp at dp.length minus 1. So in the solution, we have a loop which loops from I is equal to 2 because we've carried out dp at 0 and 1 here. So this is going to equate to on. And then in terms of space, we are allocating space for this dp array, which is going to be the exact same length as the nums array. So that is going to be O of n as well. So in forming this solution, we need to look at the constraints to begin with, which is very important to do at the start of any question, just to see if we can resolve any edge cases straight away. And in this case, we have 2. So if nums.length is equal to 0, we need to return 0 because we're not going to steal anything if there are no houses to steal from. Now, if nums.length is equal to 1, we can just return nums at 0. So we can return the value that is within that house. So now we need to create the dp array. We can fill it with 0. Now we need to cover the base cases for this dynamic solution. And we said that dp at 0 is going to be nums at 0, so it's going to be the value at the first house. dp at 1 is going to be the maximum between the first house and the second house, because we can't have adjacent houses. And then we need to loop through the rest, so that I equal 2 because we've carried out 0 and 1. I needs to be less than nums.length I plus plus. So in here is where we add the recurrence relation. So that's going to be dp at I is equal to math.max. It's going to be equal to nums at I, so the current value plus its non-adjacent house. So dp at I minus 2, so the maximum at the non-adjacent house, or dp at I minus 1. So it's going to compare the two, find out the maximum, and then lastly we can return dp at dp.length minus 1. Okay, let's see if that's worked. It's been accepted, let's submit it. So just an addition from House Robber, so if you haven't checked my video on that, please do so. So House Robber 2, we have a number of houses. Each house contains valuables, and we need to maximize the amount of valuables that we can steal from these houses. Now, we cannot steal from adjacent houses, otherwise it will set off the alarms. So we only are allowed to steal from non-adjacent houses. The catch is with House Robber 2, there is a cycle. So 2 is connected to 2 here. The value at the first index is connected to the value at the last index. So let's dive straight into the walkthrough. So previously with House Robber, we could carry this out quite easily by creating a dp array. At position at the first house, what is the maximum that we can steal from? Well, we can steal 1, right? At the second house, what is the maximum we can steal? Well, the maximum is between 2 and 1, so it's going to be 2. Then at this point, at 3, the maximum we can steal here is this value plus dp at this value or the previous value. So it's going to be 4, right? And then lastly, at 1, it'll be the same. So it'll be either the current value we're on from this house plus dp at the non-adjacent house, so 2, or the previous value. So they're both equal to the same. So it would be 3. And then we just choose the maximum values that we can steal from this house, which would be 4. However, now the houses are arranged as such. So if we repeat the process and we steal from the first house, we can get 1. From the second, the maximum we get 2. From the third, the maximum we get is 4. But then the last one, if we steal from this house, this is now connected to this one, which we've already stolen from. So if we steal from this house, we're going to set off the alarm. So a way around this is to create 2 dp arrays. So let's call this dp1 and let's call this dp2. And with dp of 1, we're going to steal from the first house all the way up to, but excluding the last house. And conversely, with dp of 2, we're going to steal from the second house all the way through to the last house. So let's do that. So with dp of 1, what's the maximum we can steal at the first house? Well, it's 1. What's the maximum we can steal at the second house? Well, it's going to be the maximum between the first and second house. So that's going to be 2. And then what's the maximum we can steal at the third house? Well, it's going to be this value plus 1, so the DP at the non-adjacent value, or it's going to be the previous value. So that would be 4. And then this last position is just going to be an empty value. Now for DP of 2, we're going to be stealing from the second house all the way through to the last house. So initially, we're going to have an empty item here. And what would be the maximum we steal from this house? Well, it's going to be 2, right? Because there's no previous values. What is the maximum we can steal from 3? Well, it's going to be the maximum between 3 and 2. So that's going to be 3. And then finally, at 1, what is the maximum we can steal here? Well, it's going to be this value plus the non-adjacent value within the DP array, or the previous value. They're both equal to each other, so it's going to be 3. Now we have 2 DP arrays. So what do we need to do in order to get the maximum between the two? Well, we're just going to look at this value and this value and choose the maximum between the two. So this is going to return us with 4. And that in a nutshell is the solution to house robber 2. So firstly, let's cover the edge cases. So if nums.length is equal to 1, we can return nums at 0. If nums.length is equal to 2, we can return the maximum between the two numbers. So nums at 0 and nums at 1. Then we need to create 2 DP arrays. So that DP1 equals new array, and it's going to be with the length of the nums. Same for DP2. And then we can create a function in order to compute the answers to DP of 1 and to DP of 2. So let's call it rob twice. So rob twice is called firstly, starting from the first house all the way up to, but not including the last house. And we're going to pass in DP of 1 nums. Rob twice is now going to be called for DP of 2. So this is going to start at the second house. It's going to go up to the last house. And we can pass in DP of 2 and nums. Then we can create the function. So rob twice, pass in I, nums length, DP, and nums. So in this, DP of I is going to equal nums at I. So this is the first value. DP at I plus 1 is going to be the maximum between the first value and the second value. So max DP at I nums at I plus 1. And then we can loop through. So j is equal to I plus 2 because we've already taken care of I at 0 and I plus 1. J is less than or equal to nums.len. And then it's the standard house robber dynamic solution. So dp at j is equal to math.max dp j minus 1 dp j minus 2 plus nums at j. And like we said in the walkthrough, at the end dp of 1 is going to equal something like 1, 2, 4, and then there's going to be an empty value, and dp at 2 is going to equal an empty value, 2, 3, and 3. So we need to calculate the maximum between dp at 1 at this value and dp at 2 at this value. So if we return math.max dp at 1 nums.length minus 2 and dp at 2 nums.length minus 1 and submit that, get our solution. So let's submit this. So we have a message containing letters from A to Z, and they can be encoded into numbers using the following mapping. So A is equal to 1 all the way through to Z equal to 26. We can decode this in a number of ways. We can either take single digits or double digits. However, there is one catch, and that is 0, 6, or any values that start with a 0 are not considered valid options. So given a string S containing only digits, return the number of ways in which to decode it. So with the string of 1, 2, we can decode that in 2 ways. We can either take 12, which is going to be mapped to L, or we could take 1 and 2, which can be mapped to A and B. With example 3, there are no ways in which we can decode 0, 6 because there is a starting 0. So the solution is looking for all potential ways that we can map these values to their respective characters. We can do this recursively, or we can use dynamic programming. So let's have a look at the recursive solution. So if we start off with this string, we can either take 2, so we can take a single digit here, or we can take two integers. As long as these values don't start with a 0 and are less than or equal to 26, we can take them. They are valid options. So from 2, we can take another single digit, which would be 2, and then we can take another single digit to 6, and then this is one of our options. Also from 2, we can just take 26, right? Because it's less than or equal to 26. So this is another valid option. And then down this right-hand side, we have 22. We can take one more value, which gives us another valid option. So it's going to return us the value of 3. The only issue is doing this recursively is going to have a time complexity of something like this, an exponential time complexity, where n is going to be the length of the string. So by using dp, we can reduce this time complexity to something more like on. So let's look into that solution. So with this dp, we're going to have an array, and this array is going to be the length of this string plus 1. And we're adding 1 onto this because we want to set some base cases. Right, so if we can't find a possible position, we can set the base case this to equal 1. Also, if we have one integer only, well, this can also be set to 1. So we can have another base case added here. So now we can iterate through this string, starting from index of 2, because we've already carried out the base cases for dp at index 0 and 1, and we can look at the single and double values within this. So we've looked at the single value, we need to look at this value now. So the single value for this one is going to be 2, and the double value for this is going to be 2, 2. So as long as the single value is greater than or equal to 1 and less than or equal to 9, so we avoid the prefix of 0, and as long as the double is greater than or equal to 10 and less than or equal to 26, so this will be in the range, then we can add these two values from the dp. So is 2 greater than or equal to 1 and less than or equal to 9? Yes. So we add single value to dp at index of 2. Is the double value at this position 22? Is that greater than or equal to 10 and less than or equal to 26? Yes, it is. So we can add the double value from the dp to the index of 2. Now we move to the next position, so 6. So we have a single of 6, we have a double of 26. Is single in range? Yes, it is. So we add the previous value. Is double within range? Yes, it is. So we add the previous double value. And as you can see, we filled out the dp array. And if we just return the value at the end of the dp array, then we'll have the answer. And as you can see, time complexity is O of n, and space complexity is also O of n. So there's only one base case we need to cover here. And that is if the string at position 0 is equal to a 0. If that is the case, we can return 0. Because there are no possible solutions if the starting value is 0. Then let's create the dp array. And we'll fill those with zeros. Then we need to initialize dp at 0 with 1 and dp at 1. Then with dp, we iterate from 2 because we've already taken care of index of 0 and index of 1. We go up to and including the last value. Okay, so let's grab the single value. So it's going to be s I minus 1, but we need to convert this. We need to pass this into an integer. And the quickest way of doing that in JavaScript is just to add the plus sign. Then we can get the double. So double is going to be plus si minus 2 plus si minus 1. And then we just see if single and double are within range. So if single is greater than or equal to 1, so excluding all starting zeros, and single is also less than or equal to 9, then we can increment dp at I by the value of the previous solution we've gathered for the single. And if double is greater than or equal to 10, and is less than or equal to 26, then we increment dp at I by the previous double solution, which is I minus 2, and then return the last value, so dp s.length. Give this a run. So there is a robot on an m by n grid. The robot is initially located at the top left corner, grid at 0.00. The robot tries to move to the bottom right corner. So m minus 1, n minus 1. The robot can only move either down or right at any point in time, given the two integers m and n. Return the number of possible unique paths that the robot can take to reach the bottom right corner. The test cases are generated so that the answer will be less than or equal to 2 times 10 to the power of 9. Okay, so we need to work out all possible paths to get from the start to the end by only traversing the graph going down or right. So going all the way right and down could be 1, going down all the way right could be 1, going down 1 and then all the way right and then down 1 again could be 1. So there are in total 28 possible solutions here. So it's asking for all possible solutions. So that suggests that we could use dynamic programming to work this out. So say we have this example, it's a 3x3 matrix. We want to find all the possible unique paths from this point to this point, and we can only go down or right. So with dynamic programming, what you do is you break down the problem into incremental chunks. So you break it down into sub-problems. So we will have overlapping sub-problems, and then you use the solutions to previous sub-problems in order to work out new solutions until we get to the final solutions. So they build upon each other. Initially, let's think about this. So how many ways can we get to the position at index 0, 1, this position here, from this point? Well, there's only one way, and that's this way, right? So we can add 1 in there. How many positions or how many ways can we get to O2? Well, there's only one way, and that's here, right? So we come from the left because we're only allowed to move right. Now, how many ways can we get to this? Now, how many ways can we get to position 1, 0 of this grid? Well, there is, again, only one way, and that's coming from up here. And how many ways can we get to this position? Well, it's 1 again, right? So this is our base case for the dynamic programming. We can say that initial row is all set to 1 and initial column is all set to 1 because there is only one way of getting to that position. And then from this, we can compute the rest of the answers, right? So we know at this point that the unique values are going to be coming from this point and this point, because remember, we can only move right and down. So it's going to be taking the maximum from this point and the maximum from this point, and it's going to be adding them together. So we can add 2 in there. We can do the same here. So we add left and above. That's going to be equal to 3. Down here, we're going to do the same here. So we're going to add 2 and 1, which is 3. And then here, we're going to have 6. And that is what we want to be returning. So with this DP solution, we worked out the base cases, which is setting the columns and the rows at index 0 to 1, and then using that information to computate the solutions at each individual point. So time complexity for this algorithm is OM by n, because we're traversing every single value within the grid. And then space complexity is also OM times n, because we're storing these new values within this DP array here. Okay, so let's create the 2D DP array. So array from, array m, new array n. Now this will create the 2D array with rows equal to m and columns equal to n. And then we can initialize the rows at index 0 and the columns at index 0 to 1. So we need to loop through the DP grid that we just created. So we're looping through the rows here. We set DP at I of 0 is equal to 1. And then we loop through the columns of the DP grid we created, and we set those to 1 as well. Now it's just a case of looping through the rest of the DP grid and filling in the values with solutions to previous problems. So let's get that done. So we set I is equal to 1 because remember we filled out rows and columns at 0 with 1. So we start off at index of 1. I is less than dp.length. So our optimal substructure here is going to be dp at ij is equal to dp I minus 1, so the row minus 1, and j, so that's going to be going up, plus dp I j minus 1, so that's going to be going left. And then we can return the last value within the dp matrix we just created. Okay, let's give that a go. Submit it. So you're given an integer array nums, you're initially positioned at the array's first index, and each element in the array represents your maximum jump length at that position. Return true if you can reach the last index, or false otherwise. So off the bat, it seems like a pretty straightforward question, but it's actually pretty tricky. So we have a nums array here, 23114, and it returns true because from the start, from this index here, index of 0, we can reach the last index because, so 2 can jump either to 3 or to 1, 3 can jump all the way to 4, 1 can jump to 1 and then to 4. So it's going to return true because we can start at the 0th index and we can reach the last index. Now, a second example returns false because 3 can jump to 2 to 1 to 0. 0 can't go any further. 2 can jump to 1 or 0. 0 can't jump any further. And 1 can only jump to 0. Again, it cannot jump to 4. So let's look at this problem. So we have a nums array here. Now, you may be thinking to use like dynamic programming or something like that, but the solution isn't actually as complicated as dynamic programming because we can use a greedy algorithm. So a greedy algorithm is an algorithm that makes locally optimal choices at each step in the hope of eventually reaching the global optimal solution. So what I mean by that is, with this example, if we, instead of looping through forwards and check to see whether this one reaches here, here, and so on and so forth, let's start at the end and work our way backwards. So we know that the target is equal to 4 because that's the index we're trying to get to. Now at this position, we can reach here. If we move back from this position, excluding all of this here, can we reach this index from this one position? Well, yes, we can, because if we just add 1 here, this is going to take us to this step. So we can essentially from this use a greedy algorithm and just update the target to 3, because all we need to do is reach 3 from this starting position now, because this can reach the end position. So target is now equal to 3. We move back again. Now from this position, excluding this, can we reach 3 from here? Again, we can. 2 plus 1 is equal to 3, right? So this position is going to go here. So we can update target to 2. At this stage here, 3 can either go to 1, 1, or 4. So that definitely can get to this index here. So again, we can update the target to 1. And then at this position here, we need to look whether we can reach index 1 from here. So it can go either here, or it can go to this position. So we can reach index 1. So we can just update the target to 0. Now in order to return a Boolean, we just need to return if target is equal to 0. And if it is, it'll return true. If it isn't, it'll return false. So say we have the second example. We know that the target is equal to 4, and we're just going to update that. So at this position, 3 and 0, can we reach this position here, excluding all of this? No, we can't, because we only have a 0 here. This can go nowhere. So we move back again. At 2, can we reach the target of 4? Because we haven't updated the target still is 4, so we have to reach 4 from this position. This can only go here, so no, we cannot reach that either. Move back a step. Can this position reach the target? So from this position, we can only go to index 2 or index 3. We cannot reach index 4 again. So moving back again, can this position reach this position? Again, we're going to have trouble because it can only reach 2, 1, and 0. So this cannot reach the last index either. So is target equal to 0? Nope. So it's going to return false. So time complexity here is O of n, where n is where we're looping through this nums array where we have to traverse the entire array, and we do so backwards, and then space is O1 constant space because we aren't allocating any extra space in this algorithm. So to code this out, there isn't much to it. We declare a target, which is nums.length minus 1. So it's the last value. Then we loop through the array backwards. And here is where the greedy property is set. So if I plus nums.I is greater than or equal to target, then we can update the target to equal I. And then what that will do is it will constantly update the target throughout the iteration of the nums array until we reach the last value, so nums at 0, and we can return where target is equal to 0. So let's give this a run. Okay. So given two integers a and b, return the sum of the two integers without using the operators plus and minus. So simply we need to add a and b together without using these operators. So for this question, we are going to be using bit manipulation. And over here is a bit reference grid where I have the integers mapped to their respective binary representation. So if we wanted to add 1 and 2 together using the bits, we'd have 0 and 1, 1 and 0. If we added those together, we'd get 1 and 1. So 1 plus 2 is going to be equal to 3. But how can we do this without using the plus operator? So we have to get a 1 when comparing 1 and 0 and 0 and 1. And what bitwise operator can we use? Well, we can use XOR. So XOR looks for a difference in bits. So if we have 1 XOR 0, 0 XOR 1, this is always going to return 1. If we have the same values, this is going to return 0. So we could use this. So 1 XOR 0 is going to give us 1. 0 XOR 1 is going to give us 1. So that's the first part. But the thing is when we start looking at this, we compare 1 and 0 and we XOR the least significant bits first. So the rightmost bit. How are we going to move to this bit afterwards? What bitwise operator do we know that moves to the left? Well, we could use left shift, right? If we left shift by 1, it's going to remove these bits, and then we'll be looking at these bits. But what happens if we want to add 1 and 1 together? We have 0 and 1, 0 and 1. We know for a fact that 1 plus 1 is equal to 2. So that's going to give us this as the answer. But as you can see, if we XOR these, this is going to give us 0, and this is also going to give us 0. So the output using the XOR operator is going to be 0. So what operator do we know that compares bits, and if they're both the same and equal to 1, returns us with a 1? Well, that's going to be the AND operator. So AND looks to see whether 2 bits are 1s. If we have 0 and 1, this is going to return us 0. 0 and 0, this is also going to return us 0. So we can use this. But what we need to do with this 1 is we need to carry this over, as opposed to leaving it there. So if we carry it over and add a 0 in here, then we get the correct answer. So the steps we need to perform to carry this out: firstly, we're going to have a while loop. Secondly, we're going to check if we need to carry over any values. So we're going to use the AND operator for that. Then we are going to use the XOR operator. And finally, we're going to shift left. So time complexity for this algorithm is going to be optimized. We're going to have an O1 time complexity here because each integer contains a 32-bit, and then space complexity is also going to be O1. So there's very little code to this question. Let's initialize the carry variable, and then while b doesn't equal 0, we're going to have carry is equal to a and operator b. A is equal to a XOR b, and then we need to shift left. So b is equal to carry shift left by 1. Then we just need to return a. Submit that. So write a function that takes an unsigned integer and returns the number of 1 bits it has, also known as the Hamming weight. So with example 1, we have n, which is a representation of bits, and as you can see, the number of 1 bits is equal to 3. So we have this bit representation here of 0s and 1s, and we want to return the amount of 1s we find in here. So we can clearly see that there are 3, so we're going to be returning 3. But how do we do this? And more specifically, how do we do this in O1 time complexity? So we have 1s, and when we look at bits, we always look at the least significant bit first. So how can we determine whether this one right here is equal to a 1? Well, if we use the AND operator and we compare it to a 1, so we grab this bit, put it on this side, we compare it to a 1, this is always going to return 1. If we had 0, so in the case of this 0, we compared it to 1, this is going to provide us with 0. So we could have a global count variable which starts off at 0, and if we compare this with 1 and we get a 1, we can increment this count to 1. So we've incremented the count to 1, and we need to move this pointer, right? So we need to look at the next bit within the sequence. And how we do that? So we have 0, 1, 0, 1, 1. So if we shift right by 1, we will get 0, 1, 0, 1. And then the least significant bit is now at the correct position. And then we can repeat the process. So we look at this 1, we compare it to 1, we have a 1. If we have a 1, we increment count, and then we shift right again. So now we're at this bit. We compare to 1, we have a 0, so we don't increment count. We shift right, we get to this bit. So this is now the least significant bit. We compare with 1, we have 1, we increment count, and then we shift right. So now we're at this bit. Now n is equal to 0, and if we're using a while loop, we can exit this when n is equal to 0. And time complexity for this is going to be O of 1, and space is also O of 1. Okay, so let's code this out. So if we set count to equal 0,
and we create a while loop. So while n doesn't equal 0, we'll declare a variable to keep this simple. So it is 1, and we'll add the AND operator. So we're comparing n, the least significant bit, with 1. And if they're both the same, then we have found a 1, and we can increment count. Now what we need to do is shift right. So n shift right 1. And then finally, we can return count. So this will run through. It'll look at the first bit, or the least significant bit. It'll check if it's equal to 1. If it is, we'll increment count. So we increment count to 1. We shift right. So we look at this bit. It's equal to 1, so we increment count and we shift right. Then we look at this bit. It's equal to 0, so we don't increment count, but we shift right. Look at this bit, increment count, shift right. And now n is equal to 0. So we exit this while loop and we return the count. Let's give this a run. Submit it.
So you're given an integer n, return an array answer of length n plus 1 such that each I, where I is greater than or equal to 0 and less than or equal to n, answer I is the number of ones in the binary representation of I. So we have n equal to 2. The binary representation of each value, 0 up to 2, is as such. So we need an array as our output. The ones in the binary representation of 0 is equal to 0, right? There are no ones within this binary representation. In 1, we only have 1 bit. And in 2, we also have 1. So we're looking for the ones in the binary representation of the values from 0 all the way up to and including n. And we need to return an array as the output. Now what would happen in the case where we have n equal to 8? Well, let's have a look at that. So here we have the binary representation of all values from 0 up to and including n. And if we pay close attention to the 2 least significant bits, we have 0, 0, 0, 1, 1, 0, 1, 1. Once we reach this point, as you can see, they repeat. So we have 0, 0, 0, 1, 1, 0, 1, 1, and then they would repeat again over and over. So what is changing between each of these? Well, we're updating the most significant bit. So let's briefly discuss what the most significant bit is. So we have a most significant bit here, 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 and here. So what is changing between each of these values when the most significant bit is updated? Well, it's changing by a factor of 2. And that makes sense, right? Because a bit is a power of 2, essentially. So if we start at 0, right, there are no ones within this section. However, when we move to 1, we have 1 bit. So it's going to be 1 plus, we could assume that's plus the previous answer, which would suggest using DP. Right, so if you make a DP array from 0 up to and including 8, this DP array is going to be the representation of all the ones within the binary representation of each value from 0 up to and including n. We can initialize the 0th index to 0 because we know that there are no ones within the binary representation of 0. And now we can try and work out our optimal substructure. So if we do 1 plus dp of I minus 1, this will give us the correct answer for 1. So we can update our DP array at index of 1. However, if we use this for the value of 2, we're going to get 2, right? But we only have 1, 1. So this cannot work. So let's think about this. The only thing that has changed is the position of this 1. So we've updated the most significant bit. And we said when we update the most significant bit, we times by a factor of 2. So if we initially have a variable called most significant bit, actually we'll call it offset. If this is set to 1, when we change the most significant bit then, or when we change this offset, we need to update this value. So if we times that by 2 to give us the new offset, or the most significant bit, then in order to get a bit of 1 using dynamic programming, we need to add the value from dp of 0. So one way of doing that would be to take the index that we're on, which is 2, minus the offset, which will give us 1. And like we said, this optimal substructure is wrong. So let's implement this. So at position 1, if we do dp of the index we're on minus the offset of this position, well, like we said, the offset was 1 to begin with. I at this position is 1. It's going to be 1 plus dp of 0. That works out. So that's going to give us 1. Let's see if it works out with 3. So it's going to be 1 plus dp of 3 minus the offset. So that's going to be dp of 1. So 1 plus the dp of 1 is 1 plus 1, which is equal to 2. So now we're at the value of 4. So we're in the DP array, we're at index 4. We can look at the binary representation. What's happened here? Well, we've updated the most significant bit. And how can we check for this update? Well, we said a bit is a power of 2. So if we get the current offset, we times it by 2. If this is equal to the current index we're on, then we've updated the most significant bit. So we have to update the offset, and the offset will equal the current index we're on. So we can update that to 4. Now, by using this optimal substructure of dpi minus offset, it'll be 1 plus dp of 4, so the index, minus the offset of 4, and this is going to give us the correct number of ones within this binary representation. And then we can repeat the process. And then for 8, we make the check. So we look to see whether 4 times 2 is equal to this index of 8. It is. So we update this offset to equal the index, and then we add it to the optimal substructure we created, which is 8 minus the offset, which is going to be 1. Add that in there. And then we can return this dp array as our output. And this is how we'd calculate the solution of counting bits in ON time complexity. Let's first create the dp array. It's going to be n plus 1. And we need to fill it with zeros, right? Because we initially need to set the index of 0 to 0. And the easiest way of doing that is to fill all values to 0. We need the variable offset, which is going to be the most significant bit. Then we need to create the loop. So I is going to be equal to 1 because we set the base case for index of 0, where it's equal to 0. I is less than or equal to n because we want to include the last value. So within this, the first thing we do is check to see whether we've updated the most significant bit. So it's going to be offset times 2. If that is equal to the current index we're on, then the most significant bit has been updated. So we need to update the offset to equal the index we're on. Then we can write out the optimal substructure. So dpi is equal to 1 plus dpi minus offset. And all we need to do is return dp, and this should work. Submit it. So given an array nums containing n distinct numbers in the range 0 to n, return the only number in the range that is missing from the array. So here we have a nums array 3, 0, 1. We have a range of 0 to n, so 0 to 3, and we want to return the missing number. And we can easily see that the missing number is 2. So a straightforward solution would be to convert this into a set. So we'll have a set. We add 3, 0, and 1 to the set. So we loop through the range from 0 to n. Remember, range is 0 to 3. We loop through this range and we check at each index whether this is within set. And remember, set has a property called has. And we can check whether it has 0, 1, 2. And if it doesn't have that value, then we are just going to return that index. Time complexity for this will be on, and space complexity will also be on, because we're utilizing a set data structure in this. However, a follow-up for this is, can you implement a solution using only O1 extra space complexity and ON runtime complexity? Now let's dive into that. So for this solution, we are going to be using bit manipulation, and more specifically, we are going to be using the bitwise operator XOR. So let's briefly discuss what XOR does. So if we have 2 bits, so let's say we have 0 and 1, and we XOR those, right? And we use the caret symbol to represent XOR. If these values are different, then it's going to return us 1 bit. If they're the same, it's going to return us 0. So what XOR does is it just looks for a difference in bits. So it sets bit to 1 if only one of the 2 bits is 1. So why is this useful in this question? Well, let's look at it, right? We have the numbers 0, 1, 2, and 3 for our range. If the values are the same with XOR, so we have 3 XOR 3, this is going to return us 0, right? Because binary representation of 3 is equal to 1, 1. So if we have 1, 1 XOR 1, 1, this is going to give us 0, 0. Remember, because XOR is always looking for a difference within the bits. So this is going to return us 0. So the values in here, the same values cancel out when using XOR. So 3 is going to cancel out with 3, 0 is going to cancel out with 0, 1 is going to cancel out with 1, and then we're just going to be left with 2, which is the answer we're looking for. So how are we going to solve this programmatically? How are we going to implement this within the code base? Well, we have the indices of these numbers, right? And the indices themselves are missing one of the values from the range. So the range, remember, is 0 to n. So in this case, it's 0 to 3. So what we can do to begin with is set a variable. Let's call it XOR. And we can initially set this to the value of the range that we're missing, which is going to be 3. Because we know for a fact that there's always going to be 1 integer missing. So let's set that to 3. So now we loop through the nums array. We XOR this value with the index and with this number. Let's go ahead and do that. So 3 XOR 0 XOR 3, 3 XOR 0. So the XOR of 3 is 1, 1. 0 is just going to be 0, 0. This is going to return us 1, 1 because there are two differences here. So this cancels out, right? So we remove the 0. Now 3 XOR 3, let's have a look. Well, 1, 1, 1, 1, as we said before, is just going to return us 0. So this is going to return us 0. We can update XOR to 0. Now we've looked at these. So we move along, we compare this value, XOR it to this value and this value. So 0 XOR 1 XOR 0. Now it doesn't matter what order you carry this out in. We could XOR 0 and 0 together, which are going to cancel out. And then we're just going to be left with 1. So we can update XOR. Now we've seen these. We move along. 1 XOR 2 XOR 1. So again, these cancel out and we're left with 2. So we update XOR. We've seen these and we exit this loop and we just return XOR. And then time complexity for this one is going to be O of n because we're looping through the nums array. And space complexity is going to be O of 1. Let's declare XOR. This is going to be equal to nums.length. So for the first example, this will be equal to 3. Then we loop through the nums array. And we update XOR to XOR, the caret symbol for the XOR operator. We're going to be comparing that with I, and then we're going to compare that with the nums at I. And this will return us the value that we're missing. Let's give this a run. So all this question is asking is for us to reverse bits of a given 32 bits unsigned integer. So as you can see in example 1, we have this 32-bit integer and we need to reverse it to give us this output. And we will be using bit manipulation for this. So we have this 32-bit integer and we need to reverse it. And usually with bit manipulation, we always look at the least significant bit, which is a good place to start because just like reversing a string, with this, we're going to be taking this and adding it to the front. And we'll do that for each one until all the bits are reversed. So how can we tell whether this bit right here is a 0 or a 1? Well, if we compare 0 and 1 or 0 and 0, what operator is always going to give us these values? Well, it's going to be the AND operator. So if we compare 0 and 1, we will always get 1. If we compare 0 and 0, we always get 0. So using the AND operator, we can easily find the least significant bit. So step 1, find the least significant bit. Step 2, now that we have the least significant bit, we need to reverse it, right? We need to add it to the front here. And what operator do we know that will shift that 0 to this position over here? That would be the left shift, right? So we could use left shift. But how many are we going to shift it by? Well, for this first one, when we're looping through this string, we want to add it to the first position, right? So we're going to shift it by 31 because it's a 32-bit unsigned integer, but we also want to subtract I. And the reason for this is, so if we move this to the front, when we move to this bit, we want to add this here. We don't want to be adding it to the front, so we need to subtract I from this because I is going to be incremented and then that will allow us to reverse these bits correctly. So step 2, left shift. So now that we've shifted this least significant bit to the front, we need to create a result from this, right? So if we initially set our result to say 0, when we shift this bit over, what operator do we know that can compare to this and always give 0? Likewise, if we had a 1 here, what operator would we use to return us with a 1 here? Well, we could use the OR, right? So 0 or 0 is going to give us 0. 0 or 1 is going to give us 1. So for step 3, we're going to update the result. And the result is going to equal result or the value of 2. So the value of this. Actually, what we'll do is we'll call this x and we'll update this to x. So this will update result. And the last thing we need to do, 4, is we still have this last bit here, the least significant bit. We need to remove this, right? So that we can get this as our next least significant bit. So the simplest way of doing this is just to shift right. If we shift the least significant bit, it'll remove it from this 32-bit integer. And then we can just repeat this process, right? And time complexity for this one is going to be O1, and space is also O of 1. So let's code this out. Let's declare result, set it to equal 0. Then we loop through the 32-bit integer, So it's going to be I equal to 0, I is less than 32, I plus plus. We need to get the last bit, and we said that the operator we'd use is the AND operator. Then we need to reverse that bit, and we can store it in a variable. Let's call it rev bit. So it'll be last bit, left shift 31 minus I, so that we reverse it in the correct order. And then we need to update result, right? So result is going to be equal to result, and we're going to use the pipe, so the OR operator, and we're going to OR the rev bit. Then lastly, we need to remove that least significant bit, so we need to shift right. And one thing I forgot to mention in the code is that we need to convert the result to an unsigned 32-bit integer. And in order to do that, we're going to shift right, and we are going to return this. Let's give this a run. Submit it. And there you go. Don't forget to like, comment, subscribe, and I'll see you in the next one.